Good morning, my dear NEET warriors. The time has come for the next 16 hours, and you guys, I hope, are ready for the challenge. And I saw last lecture almost till 3 o'clock. Students who were ready, students who were writing, making notes, and studying for the entire 11th standard marathon of physics, chemistry, and biology. And that Josh was a really commendable, and kudos, hats off to all the students who either live or recorded watched the marathon completely. And now today, it's the turn of 12th standard, and already thousands of students are ahead in the race just because of this marathon. Every lecture that you attend, every session that you make notes of, every problem that you solve, every lecture that we conduct, make sure that your marks are guaranteedly going to improve. It ensures that your ranks are going to be higher from the previous day. So, my dear warriors, get ready. It's the time for the 12th standard marathon, starting off with physics, then zoology, then chemistry, and then botany. Well, of course, the limitation is never from our side. YouTube says that we cannot take a live marathon more than 12 hours. That's the technical glitch or limitation. So that's the reason why we have made two parts. So do not forget to check out the part number 2, which will follow up after this session from 5 o'clock or 6 o'clock. Good morning, Honeymotion, Nisha, Patarchad, Dinesh, Aruna, welcome Nandana, Bunty, Chintu. Hello, Shruti. Hello, Disha. Welcome, Nisha. My God, so many students. Hi, Kalesh. Hi, Sasi. Welcome, Emperor. Nice to see you all. Hi, Janani. Good morning. Let's begin with the class with full Josh, full energy. Thank you for the lovely hearts. Hi, Mona. Good morning. I hope you guys are great. And Shreyas sir is fully energetic, even though body has like given up, like, okay, Shreyas sir, you need to take rest. But I'm like, okay, no, students are there. My NEET students are there. My NEET students want to become a doctor. Just a matter of few more days. Let's work hard. So guys, if I can push myself, you too can push yourself. So let's begin with the class. Make sure you're liking the video and subscribe to the #1 NEET English channel in the country. Also, make sure that you download the notes after the session is over. The links will be there in the description box, right? So that's my biodata in case you want to take a screenshot and do whatever with it. Okay, great. Let's begin with electrostatics now. Okay, so what about electrostatics? Let's see. There are few major concepts in electrostatics, starting off with the concept of force between the two charges, which is very similar to gravitation in 11th standard, which is nothing but K charge 1 charge 2, K charge 1 charge 2 divided by R square. That is the force. And usually the questions of force can be like, example I'm giving you. Imagine there are like two charges over here. Maybe there is a charge of 3q, there is a charge of 2q, and something like this over here, 2q, and maybe there is another charge over here of capital Q, and the question will be something like, what should be this distances, so that the net force, on Q is 0. So if I want that the net force on, let's say, Q is 0, what should be the distances or what should be the ratio? So very simple way of doing these questions. First of all, see guys, this particular 3q charge on this particular q charge will give a repulsive force. So this is the force due to 3q. Like charges will repel. If these are opposite charges, they will obviously attract, and the force due to the negative 3q charge, negative 2q charge will be on this side. Because the net force is 0, they should balance out each other. So this force will be equal to this particular force. Okay, this particular force. Now the force due to negative 2q will be Coulomb constant, and then you have 2q, and then you have q, and then divided by the distance, let's say it is y square. Similarly, due to the 3q charge on this charge will be k into 3q multiplied by capital Q divided by the total distance, which is nothing but x plus y the whole square. That is how you're going to solve the problem. Kk is the Coulomb constant which will cancel, Q capital, Q small will cancel. So 2 divided by y square will be 3 divided by x plus y square. Now you can take the roots on both sides. So root 2 multiplied by cross multiplied with x plus y will be root 3 cross multiplied with y after taking the square roots on both sides. So you can just say this is root 2x. This root 2y, take it on the other side. So root 3y minus root 2y. So therefore y is common and this is root 3 minus root 2. So that is a root 2x, of course. So therefore x divided by y will be root 3 minus root 2 divided by root 2. So that is the final answer for x by y distance. That's how you can solve it. Yep. Okay, great. Perfect. Good morning. Yes, we'll be doing oscillations waves also today. Thank you for all the love, Ashu. Thank you so much. Thank you, Sasi. Good morning, Harshat. Yep. Thank you, all the warrior pandas. Thank you. Yeah. NEETpedia is worth it. Thank you so much, Janani. And those of you who do not know about NEETpedia, please check out the description box later on. You will see lot of quality content, mind maps, formulas, revision sessions, for problem solving, PYQs, test papers are there in the NEETpedia document. So make use of it completely. Okay, so that is about the force. K is your Coulomb constant. Remember, the value of K is 9 multiplied by 10 to the power 9, which is also 1 by 4 pi epsilon naught. Okay, the next one concept comes as electric field, which is due to a point charge given by KQ divided by R square, KQ divided by R square. And the questions can be something like, there is one charge over here, let's say Q, another charge over here, let's say 2Q, another charge over here, let's say Q, and this vertex is there. What is the net electric field at this particular location? Assuming that these are on the vertices of a square. So these kind of questions are again very common. So what do you do in such cases? Sometimes the charges can be negative also. Maybe this charge is negative, this charge is also negative. So what do you do in these cases? So all you have to do is, see guys, this particular negative charge and this particular negative charge will give an electric field which is attractive in nature like this. So let's say I call this as E1, and this electric field due to the 2Q charge will be basically like this. So let's say I call it E2. So the resultant of all these three electric fields will give you the net electric field. So this kind of questions can also come in gravity, where masses are given and you have to find the net gravitational field at a point. So first of all, what will be the value of E1? E1 is the electric field due to the negative charge. Magnitude wise, it will be K into charge divided by the distance, which is the side length square. This E1 is also going to be the same in magnitude because of the side lengths and the charges being same. What about 2Q? So this electric field due to the second charge will be K, charge is 2Q. Do not forget the diagonal length is root 2A. Yes, that is one common mistake many people do. They write it as A. No, it is root 2A, which is the length of the diagonal. So the diagonal length will come over here, which is root 2 times of A, the whole square. So now we know E1, we know E2, and I think solving the problem will be easy. 2 will cancel because root 2 square is 2. So it will become KQ by A square coincidentally. So now we have three vectors. One vector is here, one vector is here, and another vector is here. So first of all, what you do is take care of these two perpendicular vectors, because both of them are KQ by A square only. This is also KQ by A square. So the result of these two vectors will be over here. So what will be the resultant, guys, of these two? It will be root 2 times of that. So root 2 times of KQ divided by A square. This vector, the E2 vector, which was KQ by A square, will stay as it is. It will stay as it is. Now take care of these two vectors because they are directly opposite of each other. So always while solving vectors, try to see which are the easy ones which can be solved first, and then slowly add it with the remaining vectors. So I solved the easy ones first. The resultant was exactly opposite to KQ by A square, the third vector. So now out of these two, root 2 is more than this guy, 1. So the resultant will obviously come in this particular direction. So it will be root 2 minus 1. Rest every term is the same. So it will become k cube divided by a square. So these are some of the questions which can come in electric field, resultant electric field. Is that right? Very good. Now you can go from force to electric field or electric field to force via this particular equation. How are they related to each other? Let's have a look. So if you want to go from here to here or from here to here, guys, the formula is basically force is equal to charge multiplied by the field. Force is nothing but charge multiplied by the particular field. So say for example, you might be given that okay, there is let's say some kind of electric field over here, and maybe there is an electron or a negative charge over here. So negative charge q is there, and it has been thrown with certain speed u over here, making some angle theta. So if there is an electric field over here and the charge has been thrown in that particular electric field, what happens is that charge will experience an electric force. Force will be always in the direction of the field or opposite to it. When it is a negative charge, it will always be opposite. So the magnitude of this force will be the magnitude of this charge multiplied by the field. It is definitely opposite to the field, because since it is a negative charge. If it was a positive charge, then the force would be exactly in the direction of the field. Now this force is always acting down. You have thrown it with some speed. So this looks like a projectile motion problem where gravitational force is downwards and you're throwing the projectile at an angle. So the projectile will basically go like this and the force will always remain constant. So you can just solve it like projectile motion problem, and now you can find the acceleration. Acceleration is force divided by mass. So it will be nothing but charge into field divided by mass. So this acceleration is just like your acceleration due to gravity. Yep. So this entire thing will accelerate downwards, and you can now use it like acceleration due to gravity. So say for example, the question was, what is the time that it takes to reach over here exactly on the opposite side? What is the time that it takes? So the answer will be 2 times u times sine theta divided by, instead of g you will put a, which is nothing but QE divided by m. So that's how you can solve the problem. If the question is saying that can you find what is the height of this? Well, the height of this will be u square sine square theta divided by 2g. But g will be now this thing, acceleration, which is nothing but QE divided by m. So that's how you can solve the questions where electric force is being required to solve the problem. Yep. Is this absolutely clear, my dear warriors? Vanakkam. Endariki namaskaram. Namaskara, everyone, and all the students. Welcome. Yes, namaskara, vanakkam. Thank you so much, guys. Okay. Now, moving ahead from force and field, let's go to potential energy also now. Let's go to potential energy and potential. Potential energy between the two charges. What's the formula? It's K. You have capital Q, small q, but instead of R square, you will have R over here. That's the difference. Okay. And the manner in which you can relate the force and the potential energy, how you can relate both of them, is this formula. F is negative du by dr. You can use this to relate potential energy on one side and force on the other side. So say for example, simple questions like this, or even complex questions can come. Say for example, you have 3 charges, one is q, negative q, one is q, another is 2q. Find the total potential energy of the system. So what will you do, my dear students? Obviously, when the potential energy of the system is asked, multiple terms will come. Say this side length is given to me, a and a. So potential energy between any two charges is k q q by r. So there are 3 such pairs. Form all that pairs which you can get in that system. If there are 5 or 6 charges, take two charges at a time, make those pairs, those couples, and then find their total potential energy by adding their energies. So these two guys will be nothing but kq into negative q divided by the distance, which is a, plus these two people will be kq into 2q divided by a, and these two guys will be nothing but k into negative q into 2q divided by a. As you can see, kq square divided by a is common. From here I am getting -1, from here I am getting +2, from here I am getting -2. +2 and -2 just cancelled out. So answer will be nothing but minus kq square divided by a. So this is what the answer will be. Now what they can also do is they can make you say that, okay, I'm changing the potential energy and all those things. If such questions come, remember the change in the potential energy is nothing but the work done by the external force, which is also negative work done by the electric or that conservative force, by that electric force, gravitational force, conservative force, whatever it is. So say for example, they tell you that, listen, what I've done is, right now maybe that particular system was like this. So now they say, what is the work done externally and what is the work done by electric force if the side is basically made two times, if the side is made example two times. Yep. So uh very good, Krishna. Very good, Chintu. Very good, Purnani. Very good, Aditi. Guys, please keep answering. See, few students are answering, but I want everyone to have a page, rough book, something. Even a newspaper will do, but keep solving it. Don't just attend like that. Please solve it. Then only it will enter your head. Okay, even if you are feeling like, okay, I do not understand it, but still I'm copying it, it's okay. You will anyways get the notes. The point is not the notes or whether you are getting this lecture later on recorded. That's irrelevant. Still, it has to enter your head. So keep scribbling something. Keep scribbling whatever Shreyas sir is doing. Okay. If the side length is doubled, then what will happen? The original potential energy, I just calculated it over here, minus kq square by a, minus kq square by a. So final energy, the side length will double. So it will become kq square by 2a. So from this we can find delta u, which is final minus initial. So it will be minus kq square by a minus kq square. Sorry, this is 2a, kq square by a. So this will become plus. So 1 minus half is half. So it will become half of, or basically it will just become kq square divided by 2a. That is what it will become. Minus minus is plus. So this is 1, this is negative half. 1 minus half is plus half. So that is why it is half of kq square by a. So that is your delta u. If somebody asks you what is the external work done, so that is anyways delta u. So it will be again external work done is kq square by 2a. Work done by electric force, that will be negative of delta u. So it will be negative of kq square by 2a. That's how you can solve it for the work done by electric force. Now, after potential energy, this particular formula, I'll show you the application in the next thing. Okay. After potential energy, you have potential, electric potential, which is having the formula of kq divided by r, kq divided by r. So things like this, my dear students. Say we had, say we had things like this. Say we have a charge here, we have a charge here, say we have a charge here, and let's say this is q, this is 2q, this is minus q, and let us just say this is on the vertices of a square, and you have to find what is the net potential over here. So in order to solve this particular problem, the potential due to all the things will come together. So first term will be potential due to q, next term will be potential due to 2q, and last term will be potential due to negative q. What is the potential due to q? It will be nothing but k charge divided by only the side length, which is, let's say, a. Next, due to 2q, it will be k 2q divided by this distance. What is it, guys? If this is a if this is A, this is A, what is this distance? A diagonal, Pythagoras, you use it, it will be root 2 times of A. So it will be nothing but root 2 times of A plus K into negative Q divided by A. So this and this will cancel and I will be getting K 2Q divided by root 2A. If you want root 2 cancels, it will become root 2 KQ divided by A. So that is the answer for the potential on the last vertex. Is that right, everyone? Yes, root 2 times. Root 2 times. Perfect. Excellent. Now that you have understood it till here, moving ahead, my dear students, you can also relate potential and potential energy by this particular formula, and the formula goes like this: delta U. So if you had to relate these two, you can relate it like this: delta U is always charge times the potential difference. Delta U is always the charge times the potential difference. So say for example, the question goes like this. Say for example, question goes like this: there is a potential of minus 3 volts, like this, and maybe this is a potential of plus 2 volts, or let's say plus 6 or maybe plus 7 volts. Chumma, this is, let's say, 0 volt. And somewhere what happens is you take a charge like this, of minus 3 or minus 4 microcoulomb, and you are taking it like this over here. In this particular process, the questions asked are as follows: what is delta U? What is work done externally? What is work done by electric force? Any of these one questions can come. So how do we solve this particular question? Okay, so first of all, let's have a look, guys. You're taking this charge from one potential to another potential, so definitely potential difference is there. Potential difference will give you potential energy difference, just like I showed you over here in this particular formula. Change of potential causes change of potential energy, and the relation is multiply the charge with the potential difference. Okay, so what do we do? Delta U is nothing but charge multiplied by potential difference. So it is final potential minus initial potential. Charge is 4 microcoulomb. Final potential is negative 3. Initial potential is plus 7. So it will become 4 micro. 3 and 7, that is going to be basically 10. So it is going to be minus 10. So it is going to be minus 40 microjoule. This is potential energy. So minus 40 microjoule. How many of you wrote minus 40? Yes, just check. It should be final minus initial. I have gone from here, understand, to here. Oh, and the charge was negative, my bad. Yes, the charge was negative. So the answer will be positive. The answer will be positive. It was negative 4. So minus 4, if I put it, it will become plus 40 microjoules. Now, if the question was what is the work done externally, it is delta U only. So delta U value means 40 microjoules of external work is done. If conservative work is asked, then it will be negative delta U. So it will be minus of 40 microjoule. That is how you solve these questions. That is how you solve this kind of questions. Is that absolutely clear? Okay. Moving ahead. Okay, this relationship is done. Now this one, how are these two related to each other? Well, simple thing, just like this only. Electric field is negative dV by dr. That is how they are related. Just to give you an example of this particular type of question, my dear students, observe it carefully. Say your potential is given as minus 3x square plus 4y minus let's say 7 volts, minus 7 volts. Question is find the field. This kind of questions can come. Sometimes it can only have x, it can have only y, anything is possible. But when it has x, y, z, two or more variables, then you have to find the derivative with respect to x, with respect to y, with respect to z separately. And whenever you take derivative with respect to, let's say, x, treat y and z as a constant. And when you take derivative with respect to y, treat x and z as a constant. So that's what you need to do. I'll show you. So E is dV by dr with a negative sign. But here we will have three components because x, y, z are there. So Ex will be negative dV by dx. That is very important. Electric field on the x direction. So negative derivative of voltage, which is nothing but minus 3x square plus 4y minus 7, guys. So minus minus will become plus. So derivative of x square will become 2x. Derivative of x square will become 2x. Y is a constant, so constant's derivative is 0. 7 is anyways a constant, it is 0. So when you are differentiating with x, all variables other than x will be constants. So this will be nothing but 3 into 2 is nothing but 6, so 6x. Same way, electric field in the y direction is negative rate of change of voltage with respect to y. So observe this, minus d by dx of minus 3x square plus 4y minus 7. So this is a constant, so ignore it, it will become 0. It will just become 0. 4 number comes outside, so only the derivative of y with respect to y will be there. 7 is a constant, so 0 anyways. So dy by dy is 1, so the answer is 4. Now, if you think about what is Ez going to be, just think about Ez. Ez will be minus dV by dz. There is no z only in this equation. So the answer will be anyways 0. So the total electric field will have only two components. One is 6x I cap and the next one is nothing but, oh sorry, I think I missed that minus sign over here. Yeah, there was a minus sign. Remember, this minus sign was there. So this will become minus 4. Yeah. So this will just become nothing but minus 4 J cap Newton per coulomb. That is it. That is the answer. Yeah, minus 4. Is that clear? Yep. Yep, Purani. I just ended that minus sign. Thank you. Vidyarthi T. Yes, shows that you guys are very attentive. Very good, Krishna. Yes, Hema. Yes, Piyush. Very good. Very good. EZ is 0. Great. 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 Awesome. So moving ahead over here. So we have seen force, potential energy, voltage, field, and their different relationships with respect to each other. Now, there are different geometries and which also come via Gauss's law. We'll talk about it. We'll talk about it over here. Few more things which I can add over here. Where did it go? Regarding voltage and field especially, remember, if these are two potential lines, this is V1, this is V2, then your electric field which is there always goes from higher voltage to lower voltage. Electric field will always goes from, if this is high, this is low, always goes from high voltage to low voltage. Not just that, the electric field lines are always going to be perpendicular to the potential lines. They are always going to be perpendicular to the equipotential lines. Keep this in mind. Always this is going to be true. Okay. Now, now basically your Gauss law and all of that. So before Gauss's law, let's talk about electric flux. Electric flux, this particular quantity is directly proportional to the number of field lines cutting through an area, cutting through an particular area. So let's say, for example, we have a surface like this, then that surface area is A. We define an area vector which is always perpendicular to that surface. Let's say I call that area vector as A like this, and let's say the electric field is piercing through it like this, so this is E, this is, let's say, theta. Then the electric flux symbol is phi, is given by E vector dot A vector, which is EA cos theta. EA cos theta. But if you have a curved surface or a closed surface or something like that, let's say, so say for example, something like this. This is a three-dimensional object. This is a completely closed figure. So maybe some electric field lines are coming out of it, some are going inside, some are going out, some are coming in, anything can happen. So I'm just showing some random thing, and inside of that there could be some charges. Inside of that there could be some charges. Let's say the charges inside of it are plus, minus, 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 plus, something like that. These are some charges which are there inside of it. They are all total charge which is there inside. Okay, some charges there inside. There could be some outside charges also, minus, plus, minus, plus, minus, minus, plus, minus. So these are all outside the surface, outside the surface. So any such closed surface, any such closed surface, what is it called? Any such closed surface is called as a Gaussian surface, is called as a Gaussian surface, is called as a Gaussian surface. Then the total flux of a closed surface is given by integration, not just the dot product, because the field will be different, area vector will be different. So it is electric field dot producted with the area vector at every single point, and closed surface means you have to put this integral. And Gauss law says that, and Gauss's law says that this particular total flux of a closed surface is nothing but the total charge which is there inside, the total charge which is there inside divided by epsilon naught. So the total charge which is there inside divided by epsilon naught. So that is nothing but cyclic integration of electric field dot the area vector. Now please remember, the RHS only depends on the inside charges, but on the left hand side, whatever this particular quantity is there, this quantity electric field which is there, this quantity depends both on inside and outside, depends on in and out, both inside and outside, both charges, but the integration only depends on the inside charges. So that is the funny part over here. Okay, cool. Shall we go ahead? All right, all right, all right, great. Good morning everyone. Thank you ZK Warrior for all the love. Yep. Now, based on Gauss's law, you get different geometries and their potentials and their fields and all those things. Let's see it one by one quickly. Ready, guys? So the first geometry coming up on your screen is of a infinitely charged wire. Infinitely charged wire. So this wire is infinitely long and it has lambda coulomb per meter. That is the linear line charge density per unit length. How much charge is there? So the charge is basically completely on that wire. The charge is basically completely on that wire. And now you are essentially standing at a distance r from it and you're trying to measure the electric field because of it. If it is positive, it will be outside. If it is negative, it will be inside. It will be nothing but 2 times Coulomb constant times lambda divided by r. It is inversely proportional to r basically. It's just inversely proportional to r. Next geometry, my dear students, is basically a sheet of charges. This is example, a sheet, okay, and that sheet has charges like this. Yes, this sheet has charges like this. Okay, so it has something called a sigma, which is nothing but the charge per unit area, charge per unit area. Then the electric field lines which come out of it are always going to be parallel. So that is the only geometry which gives you uniform electric field. This is uniform because they are parallel, so the intensity is the same. It is just sigma by 2 epsilon naught. It is just sigma by 2 epsilon naught. That's it. Yep. Next important geometry, my dear students, is if you have a conducting surface. If you have a conducting surface, then the charges are always on the surface of the conductor, never inside. So the charges are only there on the surface, never ever inside. And the electric field lines will always come out from the surface of the conductor and always perpendicular to it. Always perpendicular to it. That is how it will look like. So assume that this is a conductor. Assume that this is a conductor. So electric field lines are always perpendicular to the surface and always outside of it. Inside the electric field is zero. Keep that in mind. Inside a conductor, the electric field is zero. All of this comes via Gauss's law only. The just outside electric field on the surface is sigma by epsilon. No 2 over here. Here, when a sheet is there, then it is by 2. But when the field only comes on one side, then the number 1 will come instead of the number 2. Here 2 is there because both sides it is going. So think of it like that. Yeah. So only sigma by epsilon naught field will be there for a simple conductor. For a simple conductor just outside of it. Inside anyways, there is no field at all. Very good. Very good. Awesome. Awesome. Yes, the potentials are constant. Yep, very good. Awesome. Guys, I want you to smash that like button right away right now. I'm just seeing how many students are liking the video, etc. Come on, smash it right now. Everyone, come on. Okay, very good. Very good. Very good. Cool. Let's move. Next geometry, guys, is of a shell. Next geometry is of a shell. By the way, I think I had to mention this over here. Inside the potential is constant. Yeah. Inside potential is going to be constant throughout the surface of the conductor. But outside the potential will not be constant, obviously. Okay. Talking about the next geometry, which is basic a shell, and the geometry after that will be a solid sphere which is uniformly charged. By the way, the same formulas are also applicable for gravitation, just in case if you are wondering. So the charges over here are distributed uniformly. Please note it. Here, the charges are only on the surface, nowhere else. Okay, so that's the difference. Now, even if there is a solid conductor, remember, it will behave like a shell because for a solid conductor, the charges will go out and the charges will be only on the surface of that conductor. So a solid conductor behaves like a conducting shell or just a hollow sphere. But this can only happen with an insulating sphere or a non-conducting sphere where the charges might not be able to move freely around and they are compelled to stay there as it is because it was charged uniformly by manufacturing. Okay, so keep that in mind. So let's say the charge on it is Q and the radius of this guy is basically R. Radius of this guy is basically R. So talking about the field outside versus inside. So when you are outside, the field is just like a point charge. So it is K Q divided by R square. Even the potential is just like a point charge. So it is K Q divided by R. Same logic applies over here. So if you are at a distance R from it, the electric field is K Q divided by R square. Potential is K Q divided by R. That's it. But when you're inside, things change definitely. So let's say you are inside over here. So when you are inside, the potential is same as that on the surface. So it is KQ divided by the radius of the shell, whereas the field obviously is going to be 0 for a shell. Inside a shell, the field is everywhere 0. Keep that in mind. Very, very crucial. But here it is slightly different. It is not 0 because charges are there even inside. So when you are inside, the electric field is given by kq small r divided by this radius of the sphere cube, and the potential, the electric potential inside is given by kq, and then you have over here something minus, and then here something minus. Okay, and we have over here basically 3r square, and here we have 2r cube, 3r square, 2r cube, and then just put over here small r square. That's it. So this is the formula for the electric potential inside a uniformly charged sphere. This is a slightly complex formula, but that is something which you should remember. Everyone, Pakka? Yes. How many of you remembered this formula of electric potential? Yes. How many of you remember this formula? Electric potential. Very, very important, guys. Many people forget it. Many people forget it. Please keep this in mind. Yeah. Great. Cool. So let's go. Let's go. Let's go. Very good, Surva. Very good, Dinesh. Awesomeness. 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 Great. Cool. So let's go. Let's go to the next one. Last geometry, I think we have covered almost everything. Line charge done, sheet done, this done. Okay. I think only one thing is remaining. Arc. Yeah, if you have an arc which is charged, very rarely they ask it, but if they ask you, then at least you should know the formula. So you can do it directly. This is theta. So lambda again is given, which is the charge per unit length, charge per unit length. Then the electric field which is there, electric field will act like this, exactly bisecting it, and it is given by 2k your lambda divided by the radius, whatever is the radius, and here you will have sine of theta divided by 2. That is what the answer will be. 2k lambda by r into sine theta by 2. That's it. Okay, that is again very, very important, my dear students. 2k lambda by r and in sine theta by 2. Very good. Who is this? Inchan. Awesome. Warrior Pandus. Very good, Aditi. Excellent. Most wanted criminal, Nandu. Awesome. Warrior Pandu. Welcome. Okay. Great. So this is also done. This is also done. Gauss law also done. Potential, everything also done. Now let's go to what is it? Some important properties of conductor which I would like to tell you. See, guys, first of all, we have already discussed that in what is wrong with this? My God, it hanged. Okay, one second. Let it to cool down. Finally, it's back. Okay. See, guys, if you have a conductor, if you have a conductor, keep this in mind. Always the electric fields are perpendicular to the surface. Maybe later on they may not be, that's okay, but at the surface they are. And inside the electric field is going to be zero. Inside the electric field is going to be zero. We also said the potential inside is going to be zero, but outside the potential surfaces, equipotential surfaces make lines like this. Almost they are the shape of the object only. So these are the equipotential lines. So these are the equipotential lines around the conductor. Also important, the charges are only on the surface of the conductor, they are never inside. The charges on the conductor are only on the surface, they are never ever going to be inside the surface. But what if the the conductor has some cavity inside of it? If the conductor has some cavity, something like this inside of it, still you will see the conductor's charges will be only on the outer surface, irrespective of the size of the cavity or the number of cavities. There is no field inside. there is no field inside at all, no matter where you go. Okay, then important thing is, if you take a conductor, and you bring some external charge from somewhere, let's say you bring some external charge from somewhere, then you will see that the charges will get induced on the conductor. So this will become positively charged, this will become negatively charged. The negative charge being closer has more attraction, the positive charge being farther has less repulsion. So you will see that there is a net attraction over here, net attraction over here the moment you bring some kind of charge on a conductor. So these charges are then called as your induced charges. They are called as your induced charges. These induced charges are only on the surface, keep that in mind. They are never inside the bulk, and still you will see no matter what you do, electric field inside will still be zero. Electric field inside will still be zero. They will always try to cancel out the field. All these are very, very important properties. Also keep in mind, electric field lines always originate from a positive charge and terminate at a negative charge. Okay, always. They can never originate from negative and they can never terminate on a positive. Very important. And wherever the field lines are very, very densely located, the field is going to be strong at that place. Like over here, it is going to be definitely strong. But wherever the field lines are far away from each other, there the electric field will be weak. Keep this also in mind. Now, next is dipoles. The next is basically electrical dipoles. So dipoles are nothing but two equal charges of same magnitude but of different signs. That's all. So let's say I talk about an electric dipole like this. This is, let's say, a negative charge. Let's say this is a positive charge. Then if this is negative q and let's say this is positively q charged, okay, and the separation between them is, let's say, L, okay, then the electric dipole moment is a vector quantity which is nothing but any one of the charge multiplied by the separation. This is your electric dipole moment. Keep this in mind. Okay, now this electrical dipole moment will create electric field and electric potential around it. So say for example, you take any electric field line which will go like this, any of the electric field lines which will go like this, and at some location you want to see what is that electric field exactly. So let's say this is the distance at which you want to find that electric field over here. So this particular electric field will be given by K into that dipole moment which is there, into, say guys, this particular distance is making some angle over here. Let me call it theta. This position is making some angle with the dipole moment. I will call it theta. So Kp root of 3 cos square theta plus 1, the whole thing divided by r cube. R cube, keep in mind, not r square, r cube. And similarly, at this particular point, this electric field will be making some angle, let's say alpha, so that tan of alpha will be given by whatever tan theta is there, the whole thing you divide by 2, not theta by 2, it's tan theta's half is tan alpha, the angle made by the field vector with the position vector. Lastly, the electric potential at that point, the electric potential at that point is given by K, okay, keep this in mind, dipole moment, and just put cos theta, that's it, cos theta divided by r square, Kp cos theta divided by r square, that's it. Okay, if the charge is present inside the cavity, then there will be electric field inside, and as well as what do you say, I'll show it to you maybe here. So say for example, you take a conductor like this, and let's say you put a charge here. Then there will be induced charges, like there will be negative over here, more negative here, and as you go far away, less negative. These are all induced charges, and an equal amount of induced charge on the outside. Equal amount of induced charge on the outside. Yes, electric field will be there here. Electric field will definitely be there over here, as you can see. But here, the electric field will be zero in the solid part of the conductor. Again, the electric field will start from here. That is how the diagram will look. Okay, that is how the diagram will look. So again, outside the electric field will be perpendicular. Only in that solid part, electric field will be absent. Okay, that's how it looks when there is a charge inside the cavity. Is that okay? Perfect. So potential done, field done, and angle also done. Now, please keep in mind there are two special positions over here. One is called as the axial position. That means this line. So this is also called as the axis of the dipole. And in the axis of the dipole, theta is either 0 degree on this side, or if you go on to this side, then you will see theta will be nothing but 180 degrees. So that is the field on the, sorry, that is the axis of the dipole. And if you see the field on the axis of the dipole, put theta is 0, cos 0 is 1, 3 plus 1, 4, root of 4 is 2. So it will become 2 kp divided by r cube. That is the field on the axis. The other line is the equatorial line, which is basically like this. This is called as the equator. This is basically called as the equator. And on the equator, theta is basically plus minus 90 degree. So you will see, especially the electric field on the equator, put theta is 90, cos 90 is 0, 0 plus 1 is 1, 1's root is 1. So it will just become kp divided by r square, and the potential on the equator will be 0 because cos 90 is 0. So on this line, anywhere the potential is going to be 0. Keep this in mind. So that's how you solve the questions on dipoles. Lastly, you have what do you say? Dipole inside somebody else's electric field. Dipole, this is a dipole, electrical dipole, which is there in somebody else's electric field. Somebody else is giving some electric field, maybe like this. And let's say this is the angle over here. Okay. Okay. Then this dipole, positive charge will experience a force, negative charge will experience a force. Positive charge will experience a, what is happening? Positive charge will experience a force, negative charge will experience a force. The net force, my God, what is this? The net force acting on it will be 0. The net force on it will be 0, but definitely there will be a torque acting on the dipole. So that net torque which acts on the dipole is given as a cross product. Magnitude also I will tell you. The cross product is dipole moment cross the electric field. Cross the electric field. So it is nothing but P into E into sine of theta. PE sine theta. That is the torque acting on that electric dipole because of the electric field's forces. It will create a coupled torque. There is also an energy associated with it, and the energy associated with it is negative. Yep, it is negative. Yes, there is a dot product over here. The dot product is of the electric dipole moment, which is nothing but P vector, and the electric field vector. So it is minus PE cos theta. Minus PE cos theta. Lastly, three special cases of this. Three special cases of this. First case where the electric dipole moment is aligned. Next case it is perpendicular. Next case it is 180 degrees. All the three cases, guys, let's have a look. So here theta is 0 degree. Here theta is 90 degree. Here theta is 180 degrees. 180 degrees. First of all, this case. If you notice over here, the torque will be PE sine 90. This is basically the maximum torque. But energy wise, minus P cos 90. Cos 90 is 0. So this will be 0 energy. So this is going to be 0 energy with maximum torque. The first case, over here 0 degree, sine 0 is 0, so the torque will be 0, potential energy will be minus P cos 0, which is just going to be negative PE. Here cos 180 guys is also 0, sorry, sine 180 is 0, so torque will again be 0. Potential energy will be minus P cos 180. Cos 180 is negative 1, negative into negative, positive. So energy will be positive PE. Now, wherever torques are 0, they are conditions of equilibrium. But here potential energy is least, negative. So this is nothing but stable equilibrium. This is stable equilibrium. And this one, potential energy is maximum, although the torque is 0. So therefore, it is said to be in unstable, it is unstable equilibrium. Unstable equilibrium. The same things will also repeat in magnetism. I will not go in detail so much over there. Okay. Lastly, the concept of dielectric and all of that, and then we'll slowly go to capacitors, my dear students. So if you have any material, and let's say this is the external electric field, this is basically your external electric field E naught, this is external electric field. Then inside the material there is dipoles which are formed, which give electric field in this particular direction. So these are your induced electric field due to polarization of molecules, and dipoles are formed. So therefore, when you get the net electric field inside, when you try to find whatever is the net electric field, this is going to be the net electric field magnitude wise and vector wise. What will it be? Magnitude wise and vector wise. Well, vector wise, it is obviously the vector sum of external field and the induced field but magnitude wise, obviously they are opposite, so it will be the subtraction of it. So it is E naught minus the induced electric field. This net electric field is always going to be, this net electric field will be compared to the external electric field be some k times less. So it is k times less. This is called as the dielectric constant. So the field intensity reduces k times. So this is called as the dielectric constant of that particular medium, and from this formula, if you want, you can find out the value of E induced also. Yes, you can find out the value of E induced also, which is just going to be external field 1 minus 1 by K. So that is what the formula will come out to be in case you try to do it. Lastly, you should also know that permittivity of any medium, is a dielectric constant into permittivity of free space. Yes, this is permittivity of any medium. Permittivity of that particular medium. This epsilon naught was your standard value, 8.85 10 to the power minus 12. This is your dielectric constant. You can use this for potential energy, potential, force, field, any formula. Remember that 1 by 4 pi epsilon naught. That epsilon naught will now be replaced by k epsilon naught, just in case of any medium being present. Yes. Okay. Now also keep in mind, if it is an if it is an conductor, what is the dielectric constant? Yes, what is the dielectric constant if it is a conductor? Think about it. Inside a conductor, the net electric field is 0. That means this should become 0. So K will become infinity. So when K is infinitely large, the inside electric field will become 0. That means the induced field is completely cancelling the external field. So the net field is 0. Okay. Yeah. You cannot have K less than 1 also, in fact. Yeah, K is always more than 1. That's what you will see. Going to capacitors concepts, guys. Let's go. Okay. Capacitors concepts. So any two conductors any two conductors which are charged, like this, and there is some voltage difference between them, then that charge is directly proportional to that voltage. That constant of proportionality is called as capacitance. And symbolically we will show it like this. The energy stored, the electrical energy which is stored in that capacitor is half CV square or Q square by 2C, or basically half Q into V. The electrical energy which is stored inside the capacitor is given by half CV square Q square by 2C, or basically half QV. Very, very important again. Now, also keep in mind, if you have a capacitor like this, okay, and there is a switch over here, there is a battery over here, there would be some internal resistance like this. So the moment you close the switch, the work done by that particular battery will be nothing but how much energy will be stored in that capacitor plus some kind of heat loss. So it so happens that for this particular circuit, the energy stored is nothing but half CV square. Heat lost is also half CV square. The work done by battery will be CV square. So keep this in mind. 50% of the energy is lost, 50% gets stored, 100% is delivered by the battery. Very, very important concept. Many questions are there. Yep. Next important thing. Yes, the parallel plate capacitor, which is the most commonly used capacitor. So if you have something like this, the parallel plate capacitor, the electric field will be between the two plates of the capacitor, guys. The electric field will be between the two plates of the capacitor. This particular electric field which is between the plates of a parallel plate capacitor is nothing but any one charge divided by 2a, sorry, not 2, just a epsilon naught, q by a epsilon naught, that is the field between the two plates. But because the plates are oppositely charged, there will be also a force of attraction between the plates because the plates are oppositely charged. So maybe this plate is positively charged, this plate is negatively charged. So there will be a force of attraction between the plates. Force between the plates, the force of attraction, this is going to be attraction between the plates. This is charge square by 2a epsilon naught. So that number 2 comes, square also will come on the top. Keep this in mind. Next important thing, my dear students, after this, okay, yes, what is the capacitance itself? Yeah, the capacitance is given by epsilon naught a divided by d. But sometimes some spacing might be covered with a dielectric. So what to do in that case? So this is if it is made of air, but what to do if it is having some dielectric slabs, etc. in between? So let me take a capacitor like that, and let's say guys, this part is with some medium, then this part is with some another medium, okay, then maybe this particular part is with some another medium, okay, and maybe this part is with some another dielectric. So many such slabs can be there in between. So what to do in that case? Observe the formula. I'll give you a simple trick because many people remember it in very complicated ways. The net capacitance is epsilon naught. A is the area of the plates divided by sum of many things. What are the sum? The first distance, whatever is there, d1, divided with the dielectric constant. Next, whatever distance is there, d2, divided by the dielectric. Next, whatever distance is there, do that and till the last term. So d1 by k1 plus d2 by k2 plus d3 by k3, you just do it in the denominator, you will get the net capacitance of such a capacitor. Isn't it easy, guys? Very simple. Yeah. Gautam, the session will go until night 1 o'clock, 2 o'clock. It's divided into two parts. It's a 16 hours plus marathon. We planned it for 16 hours, but it went for almost 18 hours on first day. Baswa sir was there till 3 o'clock almost. So my dear students, this is going to be a long marathon. I hope you have come prepared with that mental state, because if you think that this is going to be done in 1 hour, I don't know which channel is trying to do entire syllabus in 1 hour or 2 hours. All the best. Please go there. Marks will also be like that only. So we are taking those efforts because we want to give you all the concepts in one single video. Oh, 3:30. Oops, sorry. 3:30. My bad. I said 3 o'clock. My bad. Okay. Moving on, guys. Moving on to the next concept. Yeah, that was the capacitance when your slabs are in placed one after the other. Next is, sometimes they will ask you, but it's not usually going to be there. It's not even there in the syllabus. Chumma, I'm giving this to you. Just by chance they give it. Cylindrical capacitor. Cylindrical capacitor. Cylindrical capacitor. The formula is 2 pi epsilon naught length of the cylinder upon log of outer radius by inner radius. That's the formula. If it is a spherical capacitor, this can come. The formula is 4 pi epsilon naught 1 by r1 minus 1 by r2. Don't try to remember what is r1, what is r2. It is the radius. Just try to make it positive. Whether it is inner or outer, doesn't matter. Just try to keep it positive. And if it is just a conducting sphere, so this is also called as an isolated spherical, just a spherical. This is isolated. There are no two spheres concentric, just one isolated spherical capacitor. Then the capacitance is 4 pi epsilon naught multiplied by the radius of the sphere. That's it. So these three data points you should definitely know. Also, one thing you should know, maybe I can put it here only, the energy stored inside an electric field. So let's say, for example, electric field lines are going like this, and somebody decides to choose a small volume of it over here, then the energy stored per unit volume, the electrical energy which is stored per unit volume, which is also called as the energy density, is given by half epsilon into electric field square. So half epsilon into electric field square is the volume's energy which is there inside a small volume over there. How much electrical energy stored per unit volume. Keep this in mind. Okay. Next. Next. Keep this in mind, guys. If capacitors are connected one after the other, so in series, basically, if they are in series, then the net capacitance, use like the parallel formula 1 by C1. Many students make a mistake over here. The total charge in each one of them is going to be the same. Yep, it is going to be the same. The total voltage is just the addition of all the voltages, that is in series. But the same thing, if it is in parallel, okay, then if it is in parallel, then the net capacitance is just the addition of the capacitances, just like resistors in series. It is opposite formula. The charges won't be the same, rather the total charge stored will be Q1 plus Q2 plus like that till Qn. In fact, the voltages will be the same, V1, V2, V3, etc. They will be definitely the same. So this is something which you should again know. Some special cases of this, like for example, this one. This diagram 100% is a capacitors in parallel only. So this is disguised form. So many times they will disguise the diagram like this. So this is basically capacitors in parallel. Then sometimes this kind of question will come where you will have again 3 capacitors here, but this branch has a capacitor, even this branch has a capacitor. Then this is disguise of Wheatstone's bridge arrangement. So actually speaking, it is capacitors like this. So this capacitor over here is, sorry guys, this is this particular capacitor which is there in between. Okay, and this is nothing but a Wheatstone's arrangement which can be further broken down into just forgetting this capacitor, just this and this. Now these are just two capacitors in series and their combination is in parallel with each other. This is nothing but a balanced Wheatstone bridge. This is nothing but a balanced Wheatstone bridge. And when it is a balanced Wheatstone bridge, if this is C1, this is C2, this is C3, this is C4, that means this was C1, this was C2, this was C3, this was C4. So C1 by C2 will be C3 by C4. You can forget the capacitor in between. All these are disguised forms which usually come. Yeah. Okay, great. Perfect. Shall we go ahead, my dear students? So all these things you should definitely know. And one more thing, guys, if there is a circuit and the switch is just closed, just closed, and there is a capacitor in there versus a circuit where the switch is closed for a long time. So basically it is in steady state, that is long time, after a long time of closing the switch. How the behavior alters, keep it in mind. So the capacitor, when it is just closed, behaves like a simple wire, but after a long time, it behaves like if it is cut somewhere. That means it behaves like a open circuit. So in that branch of the circuit, the current will not flow. So the current in that particular branch will be zero. In this particular scenario, obviously, if it is like a wire, current will definitely flow, my dear students. Current will definitely flow in this particular case, but here there is no current which will flow in that branch of the circuit where capacitor is connected. Keep this in mind. All right, very good, awesomeness. Okay, so many things done over here in capacitors. I don't think we have left anything. Just remind me if in case I have forgotten to tell you anything, I'll tell you that. Let's go on to current electricity. Let's go on to current electricity, my dear students. Ready for it? One second. Physics will be 4 hours, maximum till 1 o'clock. Yeah, today we have gathered a good pace, so I think we'll be able to do most of it. Don't worry. Okay, so quickly, guys, if this is a wire and it is carrying some current, this has some cross section. Cross section is A. Then there is some quantity called as current density. Okay, this current density is nothing but the current per unit area, where the current is the total charge which flows per unit time. Total charge which flows per unit time, which is also number of charges which flow per unit time into the each charge value. Also, if the total charge has to be found, it is integration of current with respect to time from T1 to T2, or you can also find the area under the current versus time graph. Okay, next, When you apply a voltage, obviously the charges begin to move. It is the electrons which begin to go in the exactly opposite way like this. So these are your electrons which are moving with a particular speed called as the drift speed. So what's the formula for the drift speed? NVIDIA. Current is basically NVIDIA. So I is equal to number of charge carriers per unit volume, VDE into basically A. Please remember this. N stands for number of free charges. That means how many free electrons are there per unit volume. That is what the particular formula is going to be. Current is equal to NVIDIA. They also keep colliding with each other. Very frequently. So every time they collide, they are free, they are relaxed before the next collision. So there is a relaxation time, and that is given by E, and there is an electric field also which is set up like this. This is the electric field which is set up within the conductor. Okay. So there is electric field also within the conductor. So E divided by your mass of the charge multiplied by every time it collides between the next collision, what is the time interval? That is called as your relaxation time. Relaxation time, again a very important term which you should definitely know. Then you also have the mobility of the electrons. Mobility, yes, you also have the term called as mobility of the electrons, the mobility of the charge carriers given by the symbol mu, which is nothing but how much drift speed is there per unit electric field. How much drift speed is there per unit electric field. Very, very important. Yep, very good. Excellent. All these things, formulas, very, very crucial. By the way, this same formula, if you rewrite it in a slightly different way, it is going to be I is equal to J is a vector quantity dot producted with the area vector, guys. So this same thing can be converted like this, but with a dot product. In case the area is not perpendicular, it is making some angle, then area vector will make some angle. Current density will always be in the direction of the current. Area can be taken anything. You can take any area. So then you will take it like the dot product, like how you do it in electric flux calculations. Yeah, very good. Then mobility is done. Okay. Yeah. Then comes the next quantity over here, the electric field which is there. Electric field which is there is nothing but rho into J, is nothing but something called as rho into the current density, rho into basically J. This rho is nothing but your resistivity. It is nothing but your resistivity. If you take rho on the other side, it will become conductivity. So it will become sigma. That's it. Is equal to electric field. Sigma into electric field is nothing but your current density. So now this is called as your conductivity. Keep in mind, conductivity is 1 by rho, or rho is 1 by conductivity. One and the same thing, inversely related to each other. Okay. Sir, will increasing the temperature drift speed increases or decreases? So when you increase the temperature, what will happen? Think about it. When you increase the temperature, what will happen? Then the number of collisions will increase. So relaxation time will decrease. So if the relaxation time decreases, what will happen? The speed will decrease. Once the speed decreases, the current will also decrease and the resistance increases. Those of you did not get it, I will explain it over here. Okay. If temperature of a conductor increases, if a temperature of a conductor increases, what will happen? More collisions, more collisions, more collisions means what will happen? The relaxation time will decrease. If relaxation time decreases, drift speed decreases. If drift speed decreases, current decreases. If current is reducing, that means the resistance will definitely increase. That is what happens. Is this absolutely clear now? There should be no confusion whatsoever after this. Clear? Okay, very good. Excellent. I have put it in words. All these notes are very important. This is like your best revision material at the last moment. And I'll tell you what. See, many people ask, sir, give me topper's notes. What will you do with topper's notes? You will not understand what he has done. But you have attended this class. I have made this with my hard work in front of you. I'm making those notes in front of you. There are no books over here. There is nothing. It's all there in my head. Everything is coming out and you are gaining that knowledge. You are writing it down or you are absorbing this knowledge step by step. This is the best kind of material that you will get. It's not about how beautiful it is. It's not about how neat it is. No, it is not about that. It's because you have attended this class and you have made it step by step. You have absorbed it properly. That is why this is the best notes. Understand that. Okay, great. Moving ahead, any conductor will also have some resistance. We can also say this particular conductor may have some resistance associated with it. That particular resistance is rho into the length of the conductor divided by A. You can also write it as, very important, rho multiplied by L square divided by the volume. Divided by the volume. Very, very important for those questions where you stretch the rod or the resistance or the conductor. So when you stretch it, the volume remains conserved. So if you double the length, the resistance will become 4 times, not 2 times, because even the area will become half times. So usually people make mistakes. So whenever such stretching compression problems comes, use this particular formula, not this, because area will not be constant, but the volume will remain constant. Now, this formula is also similar to Ohm's law because one can say the applied voltage is equal to the current which is flowing through it, the current which is flowing through it into the resistance, I into basically your R. So V is equal to IR. This was nothing but your Ohm's law, and it is only valid for ohmic devices like conductors, diodes, semiconductors, vacuum tubes, and so many other devices do not obey Ohm's law. That means the resistance will not be constant. That means voltage will not be directly proportional to the current. The voltage current graph might be non-linear. Okay, that might be non-linear. Lastly, the temperature dependence of resistance, which I have already mentioned over here. We can put it over here, guys. The resistance of a device will be original resistance into 1 plus alpha into delta T. This is your coefficient of thermal resistance. Coefficient of thermal resistance. So as temperature increases, resistance will also increase. So that is another important thing. Okay. So this is Ohm's law. So only for ohmic devices. Only for ohmic devices. This is all clear? Very, very important slide. All the major formulas are there over here only. Okay. In terms of mass and length also you can do. So volume you can write it because density is mass by volume. So volume will be mass by density. So that also you can do. So those conversions, manipulations will come on the spot. Okay. Fair enough. Moving ahead, guys. Moving ahead over here. Very, very important stuff. Say for example, there is a resistance, there is some current in it, then definitely there is some heat which will be developed. There will be some loss which will occur for that voltage difference that you are given. So that power loss by the resistance can be given by any of these formulas. Voltage into current, which is also V square by R, which is also I squared into R. But if it is a battery now, there are two scenarios in it. Look at this. Current is going like this inside the battery or current is going out of the battery. In either case, this is basically discharging of the battery because current is coming out of the battery. Here current is going in, so the battery is getting charged. So this is the charging of the battery. So in this case, it is the power which is delivered by the battery. Here, that is power which is entering inside the battery. Either case, it will be E into I. voltage into EMF into the current. Keep this in mind. Very, very important. Power delivered by the battery. Sometimes it might not be a question of power, it could be a question of heat loss. So if the question is of the heat which is developed, so heat which is developed, it will be nothing but power into the time. So it will be nothing but I squared R into T. So sometimes the questions of heat might come. So in that case, use this particular formula. Okay. Next important thing, if you have a battery with some internal resistance connected to some outside resistance, then there will be maximum loss, maximum power in external load, which is basically R, external load, which is basically R, if 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 the internal resistance is equal to outside resistance. This is called as the maximum power theorem, maximum power transfer theorem, maximum power transfer theorem. Very, very important, my dear students. Keep this in mind. Lastly, regarding the bulbs, so usually you will have a bulb, which will be having a voltage and a power rating. There will be a voltage and a power rating. Whenever you get that, please remember, for that voltage, that is the power, if you change the voltage, the power will change. If you change the voltage, the power will change. So it is just like a resistor only. It is just like a resistor only. And we know that the power is nothing but V square by R. Therefore, R will be nothing but V square by P. And this is what will remain constant. This is what will remain constant for the bulb. So now, if suppose, if the voltage changes, if the voltage will change, then what will happen? Then even the power consumed by the bulb will change, but the resistance will remain the same. So whenever you get bulb related problems, remember the resistance has to be calculated first and then do the rest of the calculations, because resistance will never ever change for the bulb, assuming temperatures are not affecting it so much. So that is how you solve the problems. Lastly, you will see that the glowingness of the bulb, the glow, the intensity of the bulb, is directly proportional to the power being consumed. Is directly proportional to the power being consumed. More power, the bulb will glow brighter. For the same resistance, more current will give you more glow. For the same resistance, more voltage will give you more glow. As simple as that. Is that okay? Absolutely clear, my dear students? Right, perfect. So say for example, there is a bulb, okay, which is rated at 200 volts, 100 watts. Now, let's say it is connected, this particular bulb is connected with a resistance of something, so that this has to glow at, let's say for example, 50 watts. So the question is, what is the resistance which has to be connected, assuming this particular voltage now to which it is being connected is nothing but 300 volts. This is now 300 volts. So this is the question. This kind of questions can definitely come. Sometimes they might give you resistance, they might ask you what is the voltage, or they might give you resistance, they might give you voltage, they might ask you what is the power. All sorts of questions can come. So the rated bulb voltages and powers are given. Now the question is, the bulb is connected to a slightly different voltage with a series resistance. Now what is the resistance for this power to be consumed by the bulb? Treat it now like a simple resistor problem, but for that find the resistance. We know power is nothing but V square by R. Power is nothing but 100. Voltage is nothing but 200. Okay, by resistance. So resistance will be 200 square. Okay, so this will be nothing but 40000 divided by 100 cancels. So resistance is nothing but 400 ohm. Is that right? Resistance is how much? 400 ohm. Everybody? Pakka? Clear? Okay, now redraw the same circuit. Redraw the same circuit, but think of this as 400 ohm. This another resistance I do not know. The total voltage I know is 300 volts. Okay, perfect. This power I know 50 watts. So think about it. For that bulb, the power is V square by R, or basically I can say I squared into R. That power is 50 for this bulb. Current I do not know. Resistance is 400. So basically current square will be 5 by 40, which is nothing but 1 by 8, that is I square. So therefore the current is 1 by root of 8 amperes. Is that right? The current is 1 by root of 8 amperes. That same current will flow through the other resistance. The same current will flow through the other resistance. Is that right? And what do I do with it? Oh, nothing. So no use of that. What will I do? Nothing. So better to use V square by R then. So power is nothing but V1 square by resistance 1. Okay. So power is 50. Voltage I do not know. Resistance is nothing but 400. So V1 square is 5 fours are 20 and 3 zeros. 1, 2, 3 zeros. So that is V1 square. So 2 into 10 to the power 4. So V1 will be root of 2 into 10 to the power 2, which is basically 100 root 2 volts. 100 root 2 volts. That is basically your V1. Is that right, everyone? 100 root 2? Yeah? Perfect. But this voltage is across this. What will be the voltage across this resistance? The voltage across this resistance will be complete volts minus this volts, which is 100 root 2. 100 root 2. So that is the voltage across this resistance. Perfect. That is the voltage across this resistance. We got this particular voltage. I think we had got the current also just some time back, 1 by root 8 amperes. That is what we had just done some time back. So current into voltage, resistance is voltage. We can use that. So voltage is nothing but current into the resistance, whatever is there. So that is basically 300 minus 100 root 2 is 1 by root 8 multiplied by the resistance. So from this we'll get the resistance, whatever this is. So 100 will be common, 3 minus root 2 will be there, and into basically root 8. So that many ohms resistance is going to be required over there. Okay, so that's all. So that's how you can solve these kind of questions. Always find the resistance first, treat it like a series parallel circuit of resistors, and just solve it normally. So bulb problems are at the end of the day resistance problems only. They are at the end of the day resistance problems only. So these are the important things regarding the power of DC. Next thing, you might have batteries in series and parallel, resistors in series and parallel, everybody knows. So you have batteries in series versus batteries in parallel cells versus series cells. So when you convert it into one single battery with one single resistance, so that equivalent series versus equivalent series resistance, how much they are. Here, just add the EMFs, E1 plus E2 plus like that till En. Same thing for resistances, R1 plus R2 like that till Rn. But there is a catch here. Sometimes some of the batteries might be oppositely connected, wrongly connected. So the terminals might be deliberately interchanged or by mistake. So that's why we will put plus or minus. Why plus or minus? Because if it is in the same direction, then it will be positive, positive. They will keep helping each other, so they will add up. But if one of them is negative, only for that battery you put a negative sign. Don't put for all the batteries. So if let's say the sixth battery is opposite, so for the sixth battery, sixth term will have a negative whatever volts symbol. Is that okay? Resistances will not matter whether current goes like this or like this. Resistance is always the same. So do not put plus minus sign here. What about over here, guys? See, for resistance, it is just like before only. For resistance in parallel, just use this formula, resistors in parallel, 1 by R1 plus 1 by R2, like that till 1 by Rn. But for batteries in parallel, the effective EMF, there is a big formula over here. So what you should write, observe, E1 by R1 plus E2 by R2, like that till En divided by Rn. Here we have 1 by R1, 1 by R2, like that till 1 by Rn. 1 by Rn. This will be plus minus. This will be plus minus. In case one of the batteries is oppositely connected, that particular section will be negative. Rest all remains untouched. It will be positive. So that is the formula. See, in your NCERT, only 2 batteries are given. I am giving you for even 3, 4, 500 batteries also. You can use this particular formula. Okay, direct formula. E1 by R1, E2 by R2, E3 by R3 divided by 1 by R1, 1 by R2, 1 by R3. Add it. That's it. So that is cells in parallel as well as in series. Very good. Excellent. Moving ahead, you have some setups which you should know, like one of them is the meter bridge. Meter bridge, my dear students, the meter bridge, where you have a potentiometer wire and that is connected to some battery, maybe some rheostat like this over here. And yes, over here you have your unknown resistance usually, and here you have your known resistance usually. So this is R, this is X, and this is the contact point J, which can slide anywhere. And this length is, let's say, X from here to here. This is, let's say, L from here to here. This particular point which is there over here, that is called as the null point. And when that null point comes, if there was a ammeter or galvanometer over here, it will show null deflection. Null deflection. That means the current through it will be 0. So this particular bridge will be balanced. So this particular bridge will be balanced bridge, Wheatstone's bridge. It's based on the concept of Wheatstone at the end of the day. So the formula is also similar. This unknown resistance X divided by the known resistance is this particular small x divided by L minus X. This X is also sometimes called as the balancing length. Sometimes it is also called as the balancing length. X by R is equal to X by L minus X. Usually L is 1 meter or basically 100 centimeters, depending on which units you are using. Usually, that is why it is also called as a meter bridge. That is why it is also called as a meter bridge. Very good. Excellent. Next, your other electrical instruments. I know it comes in magnetism, but we'll do it here only. Okay. Galvanometer, guys. Galvanometer also, let's complete it here only. I know it is there in magnetism, but still, let's just do it over here. So this is basically your galvanometer. Galvanometer is a very sensitive device. It senses current. It senses current and it deflects. It usually measures in microammeters or milliammeters or even nanoammeters. Very, very small currents it measures, not very large currents. And that deflection, that particular deflection which occurs in that galvanometer is directly proportional to the current passing, is directly proportional to the current which passes, that small current which passes through that galvanometer. Usually it is very small. That constant of proportionality is very simple to remember. Remember basketball, like you have FIFA for football, IPL for cricket. For basketball, it is NBA. And basketball, you should never kick, and kick is always down. So denominator, so K for kick. So NBA by K. N is number of turns, B is the magnetic field, A is the area, K is the torsional constant of that spring. So this is the torsional constant of that spring which is there inside that galvanometer. N is basically the number of turns which is there. A is basically the area of that particular coil which is there. Very, very important, my dear students. Lastly, you have current sensitivity and all those things. So if you take theta by I together, theta by I, that is called as the sensitivity of that current, and that is nothing but same thing, NBA by K, NBA divided by torsional constant. And sensitivity of current is nothing but sensitivity of voltage multiplied by the resistance of that galvanometer. Just like V is IR, usually V is IR, I multiplied by R. Here I is V into R, sensitivity is V into R. So sensitivity wise, it is slightly opposite formula. Don't multiply current with voltage, multiply voltage with don't multiply current with resistance, multiply voltage with resistance to get the current for sensitivity. This is sensitivity. I is there in the denominator. That's why that reverse relationship happens. Keep these things in mind. Okay. Always there is a maximum deflection which can occur. So this is I max, which is full scale deflection current. This is the maximum current which can go for maximum deflection theta max. And then there will be maximum voltage across it, which will be given by I max multiplied by resistance of that galvanometer. No more voltage can go through that galvanometer. No more current can go. If it goes, it will burn. It will be destroyed. So never ever pass so much current. Okay. Now galvanometer can be used in two different ways. One as voltmeter, one as ammeter. So voltmeter, and then you have ammeter, voltmeter and ammeter, guys. Yep. So say for example, if you want to use it as a voltmeter, take that galvanometer, yep, and connect a very high resistance, a large resistor, a very large value in series. Okay, you take a large resistor, in series. That's it. This particular device is then your voltmeter. This particular device is nothing but your voltmeter. This is then connected to your circuit. Whatever device is there is over here, something like this. So this is your device. Across which you want to measure the voltage. And the voltage that you measure across this device is the same as across this combination. So if this is the maximum current which can go, then the maximum voltage range which you can measure will be the maximum current multiplied by the total resistance, which is resistance of the galvanometer plus that series resistance. Now please keep in mind that our voltmeter usually has a very high resistance, and it is connected in parallel to the device. It is connected in parallel to the device, but the resistor inside is in series. So series, parallel and high resistance. Keep this in mind for voltmeter. Similarly, for an ammeter, the galvanometer is like this. You usually bypass it with something called as the shunt resistance, which is going to be very small in amount, and that's it. That is your ammeter. That's it. That's your ammeter. So the current which comes in will be like this. This is probably the range of that current which will come. A very small current will go through the galvanometer. The remaining current, I minus Ig, will go through the shunt resistance. And this particular ammeter, it has very small resistance, but connected in series. It is connected in series. Ideal ammeter should not have any resistance at all. Connected in series, okay. If you talk about the formula, voltage across the galvanometer should be voltage across the shunt. Voltage is I into R, so it will be current into resistance. Current into resistance, that means I minus, but this I will be the range, maximum range that can flow. This will be Ig max, I max current. This will be also Ig max, the whole thing multiplied by the shunt resistance. So this is the formula. Don't have to by heart it. You can write it naturally. IR voltages will be same in parallel. That's it. Okay. Clear? Very good. Excellent. So these three devices, guys, potentiometer, sorry, not potentiometer, meter bridge, okay, and galvanometer used as a voltmeter or an ammeter. And how the how the galvanometer's formulas are, all these things, please remember it. Done, guys? Very good. Excellent. That's all that was there in your current electricity, ready for moving charges and magnetism, guys. After this, we'll take a small break because after that we have ray optics, wave optics, and modern physics. Let's go, guys. Full speed. I want to complete this because the formulas are very similar in magnetism. Okay, then we'll take a small break. Ready? Okay. First is your Biot-Savart's law. It says that if you have a wire and you take a small element of it, let's say DL, the current through that wire is I, and you are at a distance of R from it, like this over here. Let's say this is angle theta. Then the magnetic field due to the small element is mu naught by 4 pi I dl cross R divided by R cube. This particular value 10 to the power minus 7, and if you just want the magnitude of it, it will be nothing but mu naught I dl divided by 4 pi r square. Again, inverse square law, if you notice carefully. In the vector form, cube comes, but otherwise there is no cube, there is just square in it. That is your Biot-Savart's law, very, very important. The second law, which is very important, is your Ampere's law. Ampere's loop law. Everything is dependent on it, and Ampere's law and Biot-Savart's law are like Gauss's law and Coulomb's law. So let's say we have many wires going out in whatever, like this. Like this. These are some currents which are going up, down. You start from a point, let's say from here, and slowly start moving around it, and slowly go like this and come back to the same point. So this is an Amperian loop, or basically a closed path, you can say. And every time you move, let's say you move a small displacement dl, and at that particular point, just like there could be some magnetic field like over here, maybe there is a magnetic field like this at that particular point dB. Some other place magnetic field will be in some other direction, like that. So what you do is take the dot product of the magnetic field, take the dot product of that magnetic field with the displacement that you have undergone. Yeah, magnetic field with the displacement that you have undergone. Okay. Now you add them up. When you are adding them up, basically what you are trying to do is you are integrating it, and you are coming back to the same point, So that's why cyclic integration. So this is a cyclic integration of magnetic field with respect to the length. That answer is always going to be mu naught multiplied by the current which is enclosed. The current which is enclosed. Now you might be wondering, what the hell is this current enclosed? Well, all the currents passing within that loop, like this one, and this one. So all these currents, let's say I1, let's say I2, and let's say I3. This current, and this current are enclosed current. The currents which are not enclosed are this one and this one. They are basically outside. But keep in mind one thing, this magnetic field over here is due to both both inside both inside and outside, both the currents. It's not because of any one of them, but the integration only depends on the enclosed currents. Now, how to get the enclosed currents positive or negative sign? Use the right hand thumb rule, where you curl your fingers along the path which you have gone. Curl your fingers along of the right hand, along the path which you are gone. This is your right hand, you are going like this. The thumb will point in the positive direction of the current. So in this case, as you can see, for this particular example, the enclosed currents, positive is only I1. I1 is the only positive one. I2 and I3 are opposite to it. So minus I2, minus I3. That's how it goes. So use your right hand rule for getting the direction of the currents with positive, negative sign. Okay. Yes. Okay. Perfect. Perfect. Oh, Kirchhoff's law, I forgot. Okay, fine. I'll do it after this. Thank you for reminding me. Yeah, see, sometimes some basic things also we forget. Okay, going to Kirchhoff's law. I forgot the Kirchhoff's law, guys. So I'll just do it over here. So Kirchhoff's current law, it's based on charge conservation. Charge conservation. So if you have multiple wires coming in, going out, coming in, going out, coming in, going out, I1, I2, I3, I4, I5, it just says that the net current at any junction should be basically zero. So whatever currents come in should be the currents which go out. Like for example, I1 is coming in, I3 is also coming in, I5 is also coming in. What is going out is I2 and I4. So whatever currents go in should be the currents go out, because charges can't collect at any location. That is what Kirchhoff's current law is all about. Similarly, you have Kirchhoff's voltage law. This is based on energy conservation. Energy conservation. So what happens is, you can encounter many devices as you move across a circuit. Along some path, okay, and as you encounter all these devices, the remaining part of the circuit is not even shown. Chuma kept over here like this. Okay, so you are going along a path. So every device you will encounter some voltage difference. So the sum of voltage differences across every device that you get along a complete loop will always be zero. Sometimes say 2 volts increases, 3 volts decreases. So plus 2, minus 3, plus 5, minus 10, minus 7, minus 8, plus 11, plus 20. So when you add them up, totally you should come back to the same point. So the total voltage drop is going to be zero. And there is a sign convention for it. I'll give it to you very easily, guys. See, for a resistance and then for a capacitance, and what else is there? Then for a battery. So this is the positive, this is the negative terminal. So how does it go? See, always for a resistor, the current goes from high voltage to low voltage. This is high, this is low for a capacitor, positive, negative. This is positive, negative. So this is high, this is low. So everywhere, the left side in this case is basically the high side, and this is basically the low side. So whenever you go from high to low, it is negative. Low to high, it is positive. So if I go like this, when I am going through a circuit, I encounter a resistor, current is going. I am going in the direction of the current, it will be minus IR. If I get a capacitor, it will be, if imagine this is a capacitor, I'm going from positive to negative, it will be minus charge by the capacitance. If maybe somewhere there is a battery, I'm going from positive to negative, it will be minus E. The exact thing happens in the reverse direction. Maybe I was going like that, this resistor, I'm going against the current. So if I go like this, it is plus IR. If I go like this, it is plus Q by C. And if I go like this, it is again plus E. So that is the sign convention for Kirchhoff's voltage law. Is that clear? Is that absolutely clear? Everybody with me? Very good. Very good. Just say, for example, hmm, imagine this is resistance 1, this is E1, this is resistance 2, this is capacitance 2, this is resistance 3, this is capacitance 2, something like that. And maybe there is a current which is going over here, I1. Here maybe the current which is going is maybe like this, it is I2. Here no current will go, capacitor is there anyways. So let's say this current is I3. Here no capacitor, no current, okay. Nothing is there over here. So if you want, you can leave it blank, or maybe we can just add one more resistor just in case, R4, and I can just say the current is going like this, I4. Okay, so if I have to apply Kirchhoff's law, starting from this point, and I will go like this and come back. Okay, so I'm going to go like this and I'm going to come back over here. So see guys, first I'm encountering a battery, positive to negative. Positive to negative means what will happen? High to low. So it will be negative E1. So what will it be? Negative, whatever is that, negative E1. Here I'm going against the direction of the current from here to here. Against means positive. So plus I2 R2. Capacitor, maybe I'll assume the charges positive, negative, negative, positive, something like that. Okay. So here I'm going from higher potential to lower potential. So negative. So negative charge by the capacitance. Here I'm going in the direction of the current. So negative. So I3 R3. Then I encounter a capacitor, negative to positive. I'm going like this, low to high. So it will be positive Q2 by C2. Finally, I'm encountering this resistance, which is against the direction of the current. So positive. So I4, R4. And lastly, this current is in the same direction as I'm moving. So minus I1, R1. This is equal to 0. So that's how you apply Kirchhoff's law. Is this absolutely clear? Everyone? Everyone? Pakka? Okay. Great. Jojo, are you trolling me or what? 200 to 560, is it possible? What is today's date? When is the exam? Don't make jokes like that. I'm not trying to demotivate, but think no. How is it justified? So, are you making fun of the other students who are seriously attending the channel from last 1 year? No, right? So, it's okay. Take a drop, work hard. Next year, why 560? You will get 700. From 200 to 700, you can get. Why 560 in 10 days? So, you are telling in 10 days, 20 days, we can get 400, 500 marks extra. So, then that way, then I mean, studying for 1 year is a waste. Then I'll study only for 1 month and I'll get 700 marks. So get that in your head properly. Okay, cool. So going to the remaining parts of magnetic effects of current, guys, quickly. Yep, all the important geometries. Let's go ahead with it. First of all, current carrying wire. It could be finite or infinite. So first let's take finite. So at a distance of r, okay, this is alpha, this is basically beta, this is the current. So the magnetic field, if the current is going like this, hold your thumb in the direction of the current, the magnetic field will be given by the curled fingers of your hand. So that will be mu naught by 4 pi current by r sine of alpha plus sine of beta. Now if it is a infinitely large wire, if it is infinitely large wire, please remember this was a finite wire. So if it was infinitely large, then what happens is alpha and beta both become 90 degree, and this particular magnetic field becomes mu naught I divided by 2 pi r. That's it. That's the only change. Next formula is, if you have a circular arc of some radius r carrying some current, then the magnetic field at the center, curl your fingers in the direction of the current, the thumb gives you the direction of the magnetic field. So that is given by mu naught I divided by 2r. That's it. See, the pi is there only for a wire. For circular objects, pi is not there. Keep that in mind. And what if it was not a complete circle? Let's say it was just an arc. If it was just an arc of current, okay, making angle theta, this is r, then again hold your fingers in the direction of the current, the thumb will give you the direction of the magnetic field. In this case it will be like this. So magnetic field will be same thing, mu naught I by 2r, just multiply it with theta by 2 pi. That's all. Just multiply it with theta by 2 pi. It's basically the fraction of the circle which you are multiplying it with. If it was a semicircle, theta will be pi, pi cancels, it will become half, so it will be half. So it will be half of the complete loop. So makes sense. So you always multiply it with a fraction of the complete circle. Last thing is, you are having a loop, again the same thing, but this is now in 3 dimension little bit. So this is your radius, there is some current, but this time you are on the axis of it somewhere over here. So this is on the axis of a loop. So then again curl your fingers in the direction of the current, the thumb points the direction of the magnetic field. So that magnetic field is very similar to this, mu naught I by 2, but here you will have r square and here you will have r square plus x square, the whole thing raised to 3 by 2. So raised to 3 by 2 is there, and that's it. That's the only change. So these kind of questions are very common in your examination. Yep. Moving on to the next type of geometry, guys. Let's go about it quickly. Yep. Next geometry is your solenoid. Yep. For a solenoid, inside the solenoid, the magnetic field is uniform. And it is mu naught Ni, where this N is number of turns. This is the number of turns per unit length of that solenoid. When I say length of the solenoid, I am talking about this length, not the length of the wire. It might have some N turns, but this is roughly a constant. I would say this is roughly a constant within the solenoid. But the moment you reach the ends of the solenoid, it becomes slightly less. So it will become mu naught Ni divided by 2. And the same magnetic field will go so far apart when you are outside, completely outside. The magnetic field will become negligible. It is zero when you are outside, very far away from the solenoid. So this is a little bit far away point. So you will see the magnetic field will just become zero. Is that okay? Fair enough. Magnetic field outside the solenoid will become 0. Yes, everyone? Now the same solenoid, if you wrap it around, it will become a toroid. I don't know whether toroid will be there or not there. See guys, this time in JEE means NTA made huge blunders. There were some 10 plus questions which are controversial already this year. Okay, 10 plus questions. Number 2, physics paper in CBSE was very tough. NTA, CBSE, brother sisters only, no difference. Like brother, like sister, like brother. So all these bros and sisses, what are they doing? Bro, full on crazy. They are torturing. Yeah, physics paper was a torture. CBSE, JEE paper was also good level in physics. So don't expect everything will be correctly in the syllabus. There might be. I hope it is not, but be mentally prepared. Some controversial question may come. Okay, some things will be like, oh, is it in the syllabus or out of the syllabus, sir? But this part is there, this part is not there. So can I say it is in the syllabus or not? So all such things can happen. Okay, so don't go hard and fast on it. So for a toroid, guys, so this is your toroid. The magnetic field will be trapped within the toroid only. The magnetic field will be trapped within the toroid. The magnetic field inside the toroid is the same formula. It is mu naught, but instead of length of the solenoid will now become what? The length of the toroid, which is 2 pi into r, and here you will have current. Yeah, here the r that I'm talking about is the radius of the toroid. This is the radius of the toroid. Okay, so that's how the magnetic field will be, which is there inside the toroid. Outside, obviously, there will be no field. Outside the toroid, the field is 0. Next, if you take if you take a bar magnet, if you take a bar magnet, this is, let's say, the south pole, this is, let's say, the north pole. This is having a negative magnetic charge, this is having a positive magnetic charge. Let's say the separation between them is L. Then it produces a magnetic dipole moment. Yes, it produces a magnetic dipole moment given by any magnetic charge multiplied by the magnetic length. So this is your magnetic magnetic dipole magnetic dipole moment. Keep this in mind. So the same magnetic moment is also produced by a loop of coil, a loop of current also, or many turns could be also there. That's okay. So this is a coil which carries some current that also behaves like a magnet. It will also produce north pole and south pole, and the magnetic moment which is being produced, the magnetic moment which is being produced by a loop of current is given by number of turns. This is not number of turns, this is north pole. Be careful. Number of turns into current into area. So this over here was north, this was south. This was the south pole. So this is an electromagnet, this is a permanent magnet. So this is the magnetic moment by a coil carrying current. This is the magnetic moment of a permanent magnet. Keep this in mind. Two different things, but the outcome is the magnetic moment. Okay, very, 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 very important. Yeah, this is like charges. Like in electricity, we have negative, positive charge. The south pole in magnetism is negative magnetic charge. This is positive magnetic charge. Okay, everybody clear till this point? Perfect. All right. Now, rest of the things are same, like the magnetic field lines, how will they look like and all of that. They will go like this, they'll come like this, they'll go like that, they'll come from here, they'll go like this, they'll come from here, they'll go like this, and they will come back from here. Same thing over here, guys. It'll go like this, like this, like this, like this. It'll also continue within the thing. They will go like that, like this, like this, like this. All these are the magnetic field lines because of the magnetic dipole. Now, when you have that magnetic dipole M, when you have that magnetic dipole M, so if I am standing at a distance of r from it, making angle theta, then the magnetic field which will come, then the magnetic field which will come at any location, again same formula guys, mu naught by 4 pi, magnetic moment will come over here. Yep, magnetic moment will come over here, and then you will have root of 3 cos square theta plus 1, the whole thing divided by r cube. Also, the angle made by the magnetic field, if I call it alpha, so tan of alpha will be tan theta divided by 2, and the magnetic potential will be given by mu naught by 4 pi. You will have magnetic moment over here divided by r square. Just like before, this will be the axis where theta is 0 and here theta is 180 degrees, and just like before, this particular line over here, is nothing but your equator. So theta will be plus minus 90 degrees. Okay, just like before. So all formulas are identical. That's what I want you to observe carefully. Is this clear, everyone? Shall we go ahead? Okay. Now what happens if you take a charge and place it inside a magnetic field? So we get Lorentz force. Once again. Okay. So we get basically Lorentz force. So if you take a charge, Q, and place it inside a magnetic field, let's say like this, and let's say the charge is moving with some velocity like that, making some angle with the magnetic field, then it will experience a force because of that field. The magnetic force which comes is perpendicular to the field also, and it is also perpendicular to the velocity, both. So this magnetic force is given by charge multiplied by V cross producted with the magnetic field. This magnetic force is perpendicular to the velocity, hence it will not do any work. It will not change the speed or even the kinetic energy. It neither changes the speed nor can it change the kinetic energy. It can only change the direction. It can only change the direction. Now, apart from the magnetic field, maybe there could be an extra force on it. So that same charge, which was, let's say, moving like this, okay, apart from the magnetic field, which created the magnetic force on it, maybe there is an electric field, maybe in some direction, maybe chumma like this, I'll say, electric field is over here. So there will be also an additional force in that direction, which will be the electric force. And we all know that the electric force is charged into the electric field. So then there will be a net force on it. This is called as the Lorentz force. So that Lorentz force, which is basically the net force, is nothing but the magnetic force plus the electric force. So if you add this, which is Q into basically E, plus this force QV cross B, you can take the charge common. Charge is there in both the sides. Okay, charge is there on both the sides. So you will have velocity cross producted with magnetic field added to the electric field, so that is the total force, which is also called as the Lorentz force. Is this absolutely clear, my dear students? Pakka? Yes, we should have questions practice. I agree. We will have questions practice marathon also. But questions practice will not keep it 32 hours. Like we'll split it in 12 hours. Okay. Because for questions, it's little bit more demanding than the theory revision. Theory revision, at least you are learning, okay, grasping, revising, checking notes, making notes. That's simple. But when it comes to problems, your brain will saturate after a point of time. I mean, we can do it, but the problem is you guys will get saturated. So we'll split it into little smaller segments. Not very small, but decently small, maybe 12 hours or something. Okay. Moving on. Where are we? Lorentz force is done. Now special cases that is there over here in Lorentz force. So first is that charge moving like this. Second time the charge going like this. Or third time the charge is basically at rest. Okay, the magnetic field is here, still there here. In all the three cases, the force will be zero. Why is the force zero? V cross B is zero. V cross B is zero. Here V is only not there. All the three cases, no force. So you will see it will move with constant velocity. It will move with constant velocity because the net force acting on it will be zero. As simple as that. Next case, let's say our velocity is perpendicular and the magnetic field velocity is perpendicular basically to the magnetic field, something like that. And then what happens is that particular charge performs a uniform circular motion, something like this. This is your magnetic field. So the charge will perform a uniform circular motion when it is perpendicular. So the radius of that circular motion is given by m mass into V divided by charge multiplied by the magnetic field, and the time period of revolution is 2 pi into m divided by charge multiplied by the magnetic field. Interesting thing, it is not dependent on the velocity of the charge. This is another important condition. The next condition, we will probably put it on, okay, we'll put it here only. Say that particular charge is projected at an angle. It is projected at an angle with respect to the magnetic field. Then that particular charge does something like this. This is called as a helical motion. The radius of such a helix, when you calculate whatever that radius of that helix, it is still the same thing. The radius is same as before, but instead of V, you will have something else. And what is that something else? You will have mv sine theta divided by charge multiplied by the magnetic field. That's it. You will have V's sine theta component. V sine theta will be over here. Just check this out. This particular component, this will be V sine theta. This component will be V cos theta. V sine theta will cause that circular motion. Time period will be the same. This time period, that is exactly same. It is independent of the speed. Now the last part over here is the pitch. So from one circle to the next circle, when you go one revolution, that is basically called as the pitch of the helix. That pitch is nothing but the V's cos theta component, V cos theta, multiplied by the time period of revolution, So that is how you calculate the pitch of that helix. Very important. Then you also have something called as the crossed field, which is used in velocity selector, Oh, by the way, sometimes if the question comes on the frequency, right? The frequency will be 1 by time period. This is the same as the cyclotron frequency. Cyclotron frequency. So the same formula can be used for cyclotron also. Don't break your head what is cyclotron. Just mark the answer. F is 1 by T. Whatever time period you calculate, reciprocal of that. That is cyclotron frequency. Don't break your head so much. Okay. So cross fields, what happens? If your charge is thrown with such a velocity that it goes undeflected in both magnetic and electric fields. So magnetic field, let's say, is like this. So the magnetic force QV cross B will be in this direction. So QVB force will be in this direction. The electric fields are, let's say, like this. So this is your electric field. So the force due to the electricity is downwards, which is Q into E. So if this is undeflected, that means the net force on it is 0. So the magnetic force will balance the electric force. And that happens when our velocity is basically the ratio of electric field divided by the magnetic field. So V is E by B, it goes undeflected. If any one thing is more or less, it will go like this or like that. So if it is not equal to E by B, then you will see either it will go up because one of the forces will dominate over the other. So this can be used to select the velocities. Only certain speeds will go undeflected, other speeds will go up or down. So this is the concept used in velocity selector. Correct. All right, great. Then we'll go with the currents. And the last few parts. Come on, guys. Okay. So if you have a current carrying conductor of length L, which is placed inside maybe a magnetic field, let's say a magnetic field like this. Okay. Inside a magnetic field. So IL cross B, length is here, cross it with B. That will give me the force on it, the force on a current carrying wire, force on current carrying conducting wire or current conductor is given by I is the current, L is the length along the current, cross product it with the magnetic field, IL cross B. Now, in case the wire is not straight, but let's say it is a curved wire, it is basically a curved wire, and maybe it is placed inside a magnetic field like this. It is placed inside a magnetic field. Replace it with a straight wire, but not an actual one, just imaginary one. This is your effective length. Then this is your effective length. So you will see that the force on the curved wire is exactly same as the force on the straight wire, and that is nothing but your current into length effective into your magnetic field, IL cross B. Yes, so that is exactly going to be the same. So examples like a semicircle is there, replace it with this. Something is there, just replace it with this. It's like displacement. It's just like displacement. Yep. Okay. This also means that if you, okay, we'll come to that later on, 1 second. But before we go ahead, we'll do just this part. If you have two wires which are parallel to each other versus you have two wires which are anti-parallel to each other, This is carrying current I1, this is I2, this is I1, this is I2. The distance between them is D. Well, if the currents are in the same direction, you will see that they will attract each other. And if the currents are in the opposite direction, you will see that they will repel each other. And the force of attraction per unit length is mu naught I1 I2 divided by 2 pi d, divided by 2 pi d. So this is for parallel wires. You should definitely know this. Very, very important. Now the extension of this is, what if you had a loop of current? What if you had a loop of current? Well, if you had a loop of current, so you had a loop of current. If you had a loop of current, then the effective length will be 0. Then the effective length will be 0. And let's say it is being placed inside a magnetic field, something like this. Then the net force on it, is always 0. So any loop carrying current placed inside a magnetic field, net force, no matter how it is, will be 0. Circular, square, triangular, anything. But it will definitely experience a torque. We had talked about magnetic moment some time back. It will definitely have a magnetic moment. Today, Shreyas sir is fast, board is slow. See, board is not even responding today. It's like, Shreyas sir, please stop. I can't handle so much of theory. Board is also saying, I am not able to handle so much of theory. See, it is not listening only. I am proud. You are better than my board. My students are better than my digital board. This is even a machine. So this proves that man is better than machine. And doctors hopefully will not be replaced by machines. See, digital board giving up. But doctors not giving up. Students are still there in the live class. Isn't it? Very good. Excellent. Cool. Just hold on, guys. Let me drink some water. Let's say the torque, guys. Yep. There will be a torque acting on it. That particular torque will be a cross product of your magnetic moment multiplied by the magnetic field, just like before. And the potential energy will be negative of the dot product between the magnetic moment and the magnetic field, just like before. All these things are same. Also valid for your bar magnets, everything. Great. Cool. Let's go. Okay. So I think in magnetic effects of current, that much only is there. I don't think anything else will be there over here. If anything else I have left out, please let me know. Let's go to magnetism and matter. All the important things I will just give it to you over here. Now I'll do one thing for magnetism and matter. I'll just give the formulas. There are some notes which I have for paramagnetism, diamagnetism, and ferromagnetism. I'll just attach it over here after the class. I had made it, so I'm not able to find it right now on the computer. Okay. Anyways, so I will just attach it later on. Okay. Yep. Perfect. So just important formulas in your magnetic materials which you should know. So again, just like in electrostatics, if you have magnetic material and you apply external magnetic field, oh my god, if you apply external magnetic field, then you have a term called as magnetizing field, so that is having a symbol of H, which is external field divided by mu naught. External field divided by mu naught. There will be induced polarities inside of this, which might oppose, which might be in the same direction. Who knows? It depends on the magnetic material. So there will be induced magnetic field inside of it. So that will give me something called as the intensity of magnetization. That will give me something called as the intensity of magnetization. Intensity of magnetization. So that is having a symbol of I. That is also a vector quantity. It is the induced field divided by mu naught. Okay. This is also the net magnetic moment of that material per unit volume. Sometimes that can also happen, and that net magnetic moment can be written down as magnetic moment of each atom multiplied by the number of atoms also. That is also something which you can do. That is the intensity of magnetization. So the net magnetic field might be less, might be more, depending on whether they are in the same direction or not. So this is your net magnetic field. So your net magnetic field is then just a vector sum, of your external field and your induced field. External field and your induced field. Okay. Then you also have something called as the susceptibility of the material. So we'll write about it. Susceptibility. This is that sus word, your Gen Z word. Susceptibility of that material. That X is given by your intensity of magnetization upon magnetizing field. That is your susceptibility, which is also related to something called as relative permeability. Relative permeability. That relative permeability, which is nothing but permeability of the medium upon permeability of the vacuum, which is also 1 plus the susceptibility. 1 plus the susceptibility. All these are very, very important formulas. All these are very, very important formulas. Okay. Very good. Excellent. Keep all these things in mind. That will be very much needed. Just to give you also an idea of, that Curie's law and all of that, that is also needed. See guys, Curie's law, very, very important for diamagnetic materials. For diamagnetic materials, what happens is relative permeability is more than 1, susceptibility is negative. You will see that the susceptibility with temperature will not change only, it will just be a constant. So it is independent. So it is basically independent. It is not affected only, independent of it. But the moment you take a paramagnetic material, that means, oh sorry guys, I made a mistake here. This was supposed to be less than 1, my bad. Relative permeability is less than 1. For paramagnetic, relative permeability is more than 1. Susceptibility is small positive number. Positive small number. Okay. Then what happens is, if you draw the graph of susceptibility versus temperature, that particular graph goes like this. Yes, and that susceptibility is some constant divided by temperature. This is some Curie's constant. So it is inversely related. More the temperature, susceptibility decreases, it becomes less magnetic in nature. The last one is ferromagnetic. ferromagnetic, they are permanent magnets, ferromagnetic materials whose relative permeability is much larger than 1, and X is a very large positive number, large positive number. So for such things, you will see, if you draw the graph of susceptibility versus temperature, it is very large until a certain temperature called as the Curie temperature, and after that, that particular graph becomes like this, it becomes paramagnetic. So after Curie temperature, the the ferromagnetic material turns into paramagnetic nature. So that is called as the Curie's temperature. Keep this in mind. Okay. Lastly, one more graph is there over here. All these graphs very important, guys. This is magnetic field and this is your magnetizing field. This is your net magnetic field. So first let's talk about diamagnetic. For diamagnetic materials, how does it look like? For diamagnetic materials, that particular graph is something like this. It's a two-way graph, like that and like this. So it is a temporary magnet, and they will weakly repel the external field. So that is why it goes negative when H is positive. If H is negative, B will be positive. So that is how the graph goes. Yeah. So that is how the graph goes. So it repels. So when H is positive, B is not positive. The same direction you will not get the field. You will get it in the opposite direction, guys. So that is the crazy thing. So it will oppose the external field. That's what happens. Whereas over here, you will see for your paramagnetic materials, it is like this. Yep, it is basically like this. So it is again two ways. It is again a temporary magnet only. It is again temporary for paramagnetic material, and it weakly attracts. It attracts weakly for some time. As soon as you remove the external field, it will stop attracting. But for ferromagnetic material, the graph is something very different. The graph is not even linear. The graph is something like this. But the moment you remove the external field, some field still remains. So it will remain over here. And when you reverse it, it goes here. It can go like this. It can go like this. It can go like this. And it can even come back over here. So the graph is not the same while going and coming. It is something like that. So this is also called as a for a ferromagnetic material. Ferromagnetic material, it is called as a hysteresis loop. Hysteresis loop. So that is how it is. Also, the area which is enclosed within this particular loop, which is there, the area which is enclosed within this particular loop. Yep. What is this area going to give? This particular area is going to give me the energy loss per unit volume. Energy loss per unit volume. Last thing over here, this particular height which is there, I can mark it maybe like this. This is also called as your retentivity. Retentivity, how much is retained when H is removed, and this is how much H you need to reverse it. So to reverse it and remove the magnetic field B value 0, so this is called as coercivity. 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 Yeah, this is coercivity, that is retentivity. Is that clear? Very good. So all these graphs I have given to you, all the important formulas, some more theory points I will add it up in the notes. Okay, great, great, awesome. I think after this we will take a break. Yeah, after electromagnetic induction, few things only are there. Few things only are there in electromagnetic induction. It is not much. It will hardly take me 10 minutes. Okay, let's go to electromagnetic induction. So your Faraday's law, Faraday's law, which says that if you have a loop and there are some magnetic field lines piercing it like this, so there is a flux which is associated. So the magnetic flux phi b is nothing but the magnetic field dot producted with the area vector, with the area vector. Yes, and this rate of change of magnetic flux d phi by dt, this d phi magnetic field by dt, the magnitude of it will give me the EMF which is induced in that coil, which is induced in that particular coil, and the current which is induced in that coil is the EMF which is induced in the coil divided by the resistance of that coil, divided by the resistance of the coil. Is this absolutely clear? So current is EMF divided by the resistance of the coil. You can also sometimes find the charge which flows. So the charge which flows in that coil in that time interval can also be found using this current is charged by time. Many times you will need it. Then you also have the Lenz's law. The Lenz's law, which is completely based on the energy conservation principle, my dear students, which says that if the flux tries to increase, then the induced flux will try to weaken it, and if the flux, one second, this flux tries to reduce, then the induced induced flux will become strong, will make it stronger. And every kind of motion is always going to be opposed. Example, say for example, this is the axis of that particular loop, and let's say you are bringing a magnet. This is north pole, this is south pole. You bring it here. This magnet is trying to come towards the coil. The magnet will be opposed. It will try to repel it. How will it try to repel? By Lenz's law. How will it try to repel by Lenz's law? The north pole of this coil should come here, south pole should come here. So the north pole should come there. Use your thumb from south to north. The fingers are curling like this. So the induced current, the current which is induced will be in this direction. Always try to do opposite of whatever it tries to do. If it is trying to go away, attract it. If it is trying to come close, repel it. If something current is trying to increase, try to decrease it. If the current is trying to decrease, try to increase it. Always the induced currents will produce fields in such a way that it will always oppose the changes in the flux. It will always oppose the changes in the flux. Keep that in mind. That is your Lenz's law. Now, you also get questions where motional EMF concepts are involved. So you might have, let's say for example, a rod like this, and a rod, let's say like this. Okay, this is some length L. This is moving with some velocity over here. This is moving with some velocity over here. This is moving with some velocity over, sorry, this is moving like this, maybe with some velocity like this. Okay, magnetic field, let's say, is like this, magnetic field like this, magnetic field like this. So there is some EMF which is developed in that particular rod. So that EMF which is developed is BLV. Here that EMF is 0 because velocity and length are parallel. Here you will see V and B are parallel. Here also the EMF is 0. This is the concept of motional EMF. This is the concept of motional EMF. So whenever a conductor moves inside a magnetic field, it behaves like a battery whose EMF is BLV or either 0. Only when all three are perpendicular, EMF is produced. Else, if one of them is parallel, then EMF is not produced. EMF is not produced. But the same rod, if I also rotate it, EMF is still produced. Observe this carefully. If this is a rod and I rotate it with some angular speed, this is basically the length and this is basically the magnetic field, then the EMF will be half B omega L square. Half B omega L square. Yep. So for a rotating rod, that is for a rotating rod, keep that in mind. The same concept of motional EMF also comes in eddy currents. So if you have, let's say, a conductor, if you have, let's say, a conductor and it is in motion, so there is EMF which is developed. That means small batteries which could be created. They will create small loops of currents. They could create small loops of currents like this. So these are called as eddy current loops. And because the conductor has some resistance, so what will happen is there will be some power loss, which is the current square, the eddy current square multiplied by the resistance of that conductor. So this power loss makes sure that all your mechanical energy gets converted into heat loss, some kind of heat loss. So if you move this conductor, it will slow down. So this principle is used in induction cookers or even braking systems of high-speed trains. So this is the concept of your motional EMF. Then next thing, ready guys? If anything parallel, it is going to be 0. Yes, sir, here I is anti-clockwise. I'm guessing you are asking about the eddy currents. Yep, here current will be anti-clockwise. If this was going away, it will be clockwise. It will always try to oppose it. All right. Next is basically what? Inductors. Yeah, let's talk about inductors now. So inductors guys. So for inductors, standard formulas, if you have an inductor L and there is some current through it, there will be some magnetic field which will be created by it. So that magnetic flux is proportional to the current and that proportionality constant is called as inductance. It is called as inductance. The energy which is stored inside the inductor is half Li square. This is the energy. Which energy? Magnetic energy inside that inductor. The same magnetic energy per unit volume, also called as the magnetic energy density, is half magnetic field square by mu naught. Then that same inductor will behave like a battery. So there will be some positive negative terminal. So the EMF which is induced within that inductor across the terminals will be negative L di by dt. Many questions come on that. Current changes this much, time is this much, inductance is how much, EMF is how much. Many questions are there on the inductor like this. Very important formula. Lastly, inductance of a solenoid. If you take a solenoid, what is the inductance? The inductance is mu naught n square a into the length of the solenoid. So this type of questions also definitely can come. Same way, just like you have self-inductance, you can also have mutual inductance. So imagine one coil over here. Sorry. And another coil over here. So this is probably current 1. It is creating its own magnetic field, which is going over here. Some of the magnetic field lines are going over here. Some of the field lines are just escaping it. And there is obviously current which is created in the secondary. So the flux which passes in the secondary coil is proportional to the current in the primary coil. That constant of proportionality is called as mutual inductance. Same way the EMF in the secondary coil is negative, just like L di by dt. It is minus M di di by dt. Very, very important. All these are very, very important things, guys. Very, very important things. Okay, perfect. Then there is also a term called as what is the maximum mutual inductance possible with two inductors of L1, L2 inductance. We'll come to that also. So maximum mutual inductance with two inductors that is always going to be root of that is always going to be that value, maximum value that you can get is always going to be root of L1 and L2. This is the maximum value that you can get. Anything else will be always lesser than that. Usually that factor is also sometimes called as the coupling factor. So if it is less, then maybe some factor like half, or maybe it is 1/3, or maybe it is 2/5. So some number will come because it is lesser than the maximum value. That number is often called as the coupling factor. If you talk about a solenoid, inside a solenoid, then the mutual inductance of concentric solenoids, concentric solenoid, very similar to this. Here it will be mu naught N1, N2, and then area of the inner coil and length. That's it. So this is the formula for concentric solenoids. What is the mutual inductance? Very similar. Instead of N square, there is N1, N2. Lastly, what if inductors are in series? If they are in series, just add them. L1 plus L2 will be your effective inductance. And if they are like this in parallel, then 1 by LP will be 1 by L1 plus 1 by L2, just like resistors. So that is the main thing which is there in inductors, guys. Nothing more, nothing less. Yep, correct. Very good. So that's the major thing in your electromagnetic induction. I think we can also do alternating current. I'm a little bit greedy now because we have a couple of things left. So I'll just hurry up without break maybe. Sorry, guys. I'll have to go constant. Yeah, because then I want to finish this on time because I know last time it became little late. We will try to finish it as soon as possible. Okay, alternating current quickly. Let's have a look. So, what is it? Voltage and current. Okay, so there is a AC generator, AC source. This is AC source. It produces some voltage and produces some current. Voltage and current may not necessarily be in the same phase. That's what you see in AC circuits. So the voltage might be like V naught sine omega t plus phi, and maybe the current is like I naught sine just omega t. Here, what are these values? This V naught and I naught. These are your maximum values, or you can call it as the peak values of the current, or you can also call it as the amplitudes. You can also call it as the amplitudes of the voltage or the current. They might have some kind of phase difference. So as you can see, this is your phase difference between the voltage and the current. So that's why their maximas and minimas are not coinciding. If you draw it in the phasor diagram, it becomes even more evident. So if the phasor of the current is like this, the phasor of the voltage might be like this. In this case, the voltage is ahead, so I am putting it slightly in the front, and this is basically your phase difference. This is basically, this thing over here is your phase difference. Yeah, and both of them will rotate with a common angular speed omega. So this is nothing but your phasor diagram, where you understand about the phase differences between different elements. So this is your phasor diagram, and always whenever you draw phasor diagram, the length of these things which are called as phasors is always the amplitude. So V naught, I naught, usually you take the amplitudes as the length of these phasors which rotate with the same angular frequency as over here. Yep. So this omega is also 2 pi f. And if you talk about the voltage amplitude for an AC generator, this V naught is magnetic field into area of the coil into angular speed into number of turns. So this is basically the concept of AC generation. AC generation, the maximum voltage depends on the magnetic field, area of the coil, angular speed of the coil, and the number of turns. BA omega n, born. Okay, so this is very important. Remember it, guys. Perfect. Okay, now comes the other things like RMS and average. So whenever you want to find the average voltage, it is nothing but V1 plus V2 plus Vn, the whole thing divided by the number of turns, also given by integral V dt from 0 to time period by time period. Similarly, you also have RMS voltage or RMS current, which is root of first value, second value, third value, nth value square added divided by n under the root, which is also the root of integral v squared dt from 0 to t, whole thing divided by t. For a regular sine wave, the average voltage will be 0, and the average RMS voltage or RMS current will be maximum voltage or maximum current by root 2. Please remember, this is only and only going to be true for sine waves only, for sine or cosine waves only. If the wave is maybe like this, or like this, or maybe it is like this, then this is not the answer, guys. This might not be the answer. You have to do it by integration or by some other logical thinking. Okay, keep that in mind. Great. Next thing. For LCR circuits, quickly let's go about it. LCR circuits, you have inductor, you have resistor, and let's say capacitor over here. This will give you some voltage and there is some current, let's say I naught over here. This is some current which will be common in all of them. This is that common current which is there. Now that voltage which is given by the source is across all the three elements together, but across every single element the voltages will be different. Maybe across this it is VL, across this it is VR, across this it is basically VC. How it goes is, in the phasor diagram, if you notice, the current phasor is always drawn horizontal. The current phasor is always drawn horizontal. The voltage across the resistor is always in phase with that. So you will see voltage across the resistor is always like this. The voltage across the inductor is ahead of the current by 90 degrees. The voltage across the capacitor is behind the current by 90 degrees. So you can see a phase difference of 90 degrees for current and voltage for capacitor and inductor. And when you find the resultant of three vectors by normal vector addition, you will probably get the resultant like this. Needless to say that this particular height of this triangle will be obviously VL minus VC. The base will be VR. Why is this VL minus VC? Because this vector and this vector, if you subtract, VC will go away, so it will become VL minus VC. That's all. And then this thing will basically become your phase difference, which is the same phase difference which we spoke about over here. Yeah, the phase difference. So this will be your phi, of course. Okay, so this will be your phase difference. Okay, so that is how you draw your phasor diagram. Now, each of these voltages, for example, voltage across the resistance will be nothing but the current multiplied by the resistance itself. Same way, I can write voltage across inductor, voltage across capacitor, and of course the total voltage across the circuit, which is V0. Every single component, because in series it has the same current, I can write it as I0, I0, I0 everywhere. But the resistances of each devices are different. For inductor, it is called inductive reactance. For capacitor, it is called capacitive reactance. For the total circuit, it is called impedance. This XL, will come to it on the next slide. Hold on, don't worry about it. We'll come to it. This XL, XC, they are called as your reactances, and this is obviously called your impedance, which is the total effective resistance of the circuit. Impedance. Yep. Very, very important. From this vector diagram also you can see one more thing, that this V0 square is nothing but this base, which is VR square plus VL minus VC the whole square. VL minus VC the whole square. Is that right? Everybody can see that hypotenuse is base square plus height square. As simple as that. You can also similarly draw the resistors. You can similarly draw the resistors in the phasor diagram. Like this is resistance, then this is inductive reactance, then this is capacitive reactance. You take the vector sum and you will get basically the total impedance of the circuit, which is basically Z. This will be XL minus XC. Again, just like before, this thing over here is your phase difference. Needless to say, V0 is over here still. You will notice that again, just like over here, impedance is your hypotenuse, base is basically R, and the height is nothing but XL minus XC whole square. So actually AC circuits is always geometrical problems than anything else. If you realize that, you will be able to solve the problems easily. Otherwise, you will be wasting a lot of time. Now, when you have to find the reactances, what are the formulas? XL is omega L and XC is 1 by omega C. That is the major formula, which you should know. If you talk about the phase difference constant, so you can use cos, sine, whatever you want. For example, you use tan phi. It is opposite by adjacent. So it will be VL minus VC by R, which is also XL minus XC divided by R. Is that right, everyone? You can also write cos phi, sine phi, whatever you want. It's endless, like how you want to solve this. Now, the power which is consumed in this circuit, is either given by Vrms current RMS multiplied by the cos phi, which is also called as the power factor of the circuit. You can also write it as I RMS square multiplied by the resistance. Please understand that reactances don't cause power loss. They don't cause power loss. They just oppose alternating current. They don't cause any loss, they just oppose. Resistor opposes also and causes losses also. It is more evil. Reactances just oppose, but they don't cause any loss. Okay, it's like I want to go out for a party. Your parents say no, and they also give you one slap. Thup, sit. That's it. Damage also, loss also, and they said no also, oppose also. Okay, so that is resistance. But reactance will be like, no, you should not go. That's it. Simple. No beatings, nothing happened. Cool, everyone got it? Yeah, see, these kind of examples everybody gets. Okay, so having said that, let's also go about resonance. Yes, okay, a lot of things, guys. Okay, at this point of time, even I'm wondering how I'm able to remember all these things. Resonance. Very few teachers in the country, I can tell you, who can teach you like this on a plain board, without books, without anything, without breaks. I'm telling you, we can count those teachers probably on fingertips who can teach you without wasting your time, continuously, without any books, all from the head, right from the heart, to make you a topper, to make you rise from below average and take you above average. Very few teachers. Yes. See, I'm not the only one, of course, but I really feel that I'm proud that I'm doing this, and I wish I had teachers like this during my time. Moving on, resonance. In a LCR circuit, if you draw the graph, yo, come man. This is your frequency of the source, AC source. This is the net current in that circuit. This is the net current in the circuit. Thank you, Aditi. Thank you, Aruna, Christina. Thank you. Thank you so much, Disha, Jion. Thank you, Mona. Thank you, Jintu. Thank you, Krishna. Vidyathri. Thank you. Thank you so much. Thank you, guys. Okay. Okay. Great. So what is it? Resonance. If you draw the graph looks something like this. The graph of how your current changes with different frequencies. There is a particular frequency for which the graph becomes maximum and you get maximum current. Yeah, you get maximum current. That phenomena, when that happens, is called as resonance. Every other time the current is less, power is less, everything is less, and this happens when your omega equals to 1 by root LC, which is the natural frequency, is matched. Natural frequency is matched. It is said to resonate, and you will see a lot of things. First of all, XL will be equal to XC. Therefore, the impedance, check this out. If XL equals to XC, Z will be directly equal to R. Z will be directly equal to R. Not just that, you will see that your voltage across the inductor and voltage across the capacitor will be equal. So if these two are equal, V0 and VR will be equal. So the total voltage will be across the resistance only, because they are going to just cancel each other out. just like this is also going to cancel each other out. Also, that maximum current which will be there, this particular maximum current which will be there, it will be the total voltage by the impedance, which is also the resistance, because impedance just became the resistance. Okay, you can use Z or R, anything will do. Z also you can use, or you can use R, one and the same thing. That's the maximum thing. Also, apart from this, few more things. Cos phi will become 1, or phase difference will become 0. That means voltage and current are going to be in the same phase. And the power factor has become 1. So you will see also the power is also going to be maximum in the circuit. Power is also going to be maximum, current is also going to be the maximum. So this is what happens in resonance. Yep, keep this in mind. Very good. Next important thing over here is about, I think, transformers. So for transformers, it is very simple, guys. It is based on the principle of mutual induction. Number of turns are N1, number of turns are N2. This is primary, this is secondary. Okay, this is your transformer. This is your transformer. Okay, so it so happens that the number of turns on the primary upon number of turns in the secondary is voltage of the primary, voltage of the secondary, and this also equals to I2 by I1. It is reverse. This is only if it is 100% efficient. 100% efficient, meaning input power is output power. That means current 1 here, current 2 here, and of course V1 into I1 is V2 into I2. Otherwise, it could be some loss which is happening, maybe 30%, 40%. So accordingly, you will have to adjust this equation. But other than that, it is always equal. So if it is not, let's say 80%, so 80% of input power is output power. So 8 by 10 number will come. So this will not be exactly equal to I2 by I1. So some number might come over there. Okay, very good. Yes. Thank you so much, guys. Yeah, I would be very happy if you can make it 500 likes before I finish my session. So without wasting any more time, let's go to ray optics quickly. Ray optics, quick formulas, guys. I will compare it with mirrors and lenses together, actually. So for mirrors on one side and lenses on the other side. Starting off with how the focal length itself is calculated. So here the radius of curvature is double the focal length, but here 1 by focal length is relative refractive index of the lens by the medium minus 1. Here you have 1 by R1 minus 1 by R2, which is called as the lens maker formula. Then with regards to the power of the lens, the power of the mirror is minus 1 by F. The power of the lens is just 1 by F. Then let's talk about the general formula for finding image distance, object distance, etc. Here it is 1 by V plus 1 by U is equal to 1 by F. Here it is 1 by V minus 1 by U is equal to 1 by F. That is what it is. Next, the magnification which happens height wise, that is the height of the image upon height of the object. Here it is negative V by U for mirrors. The same magnification, which is height wise magnification, is just positive V by U. That's it, positive V by U for lenses. Then the longitudinal magnification, which is along the principal axis, which is the length of the image by length of the object, is negative V square by U square, which is also velocity of the image upon velocity of that particular object. In case of lenses, the same longitudinal magnification, which is length of the image upon length of the object, is just positive v square by u square, which is also velocity of that image upon velocity of that particular object. So you can see more or less it is very similar, just a small change in the signs. Here, if somewhere minus is there, here it is not there. Here, if minus is there, here it is not there. So just a small change here and there. Okay, keep this in mind. Great, very good. Moving ahead, guys, moving ahead. Now, if you have a flat surface, if you have a flat surface and a ray of light comes in like this and refracts over here, this is angle of incidence, this is angle of refraction, maybe this is medium 1, maybe this is medium 2, maybe over here the light is traveling with a speed c1 with a wavelength lambda 1. Here the speed of the light is different, wavelength is also different. So what does Snell's law say? It says light is going from medium 1 to medium 2. So that is the refractive index of 2 by refractive index of 1. That is also equal to nothing but sine of the angle made by the normal in the first medium by sine of the angle made by the ray with the normal in the second medium, which is refracted angle. That is also equal to the speed of light in the first medium upon speed of light in the second medium, but the frequency never changes. So you can put lambda 1 by lambda 2. Anyways, had you put frequency also, it would have anyways got cancelled out. That is what it is. This also tells me one more thing. This is also equal to 1 by 1 by 2 mu 1. So 1 mu 2 is mu 2 by mu 1, 2 mu 1 will be mu 1 by mu 2. So they are reciprocals of each other as well. So this is a very important relation which relates almost every single thing over there. And now, in case it so happens that you are in a dense medium, yes, imagine this is your dense medium, okay, and the light falls in such a way that it is just able to graze the surface. Had it been much smaller than that, it would have definitely come out of it. Anything more than that particular angle, the light is not able to come out. It gets basically total internal reflected. This is your critical angle. That critical angle's sign is given by 1 by refractive index of the dense medium with respect to the rare medium. So this is when that critical case occurs, when the refracted ray is almost parallel to the surface. Any angle more than the critical angle, the light will be reflected internally. So sign of the critical angle is 1 by the refractive index. Keep this in mind. Now, also, if the surface is curved, then the formulas slightly differ, something like this. So if it's a curved surface with some radius of curvature, let's say like this, with some radius of curvature over here, center of curvature over here, okay, the object is over here. Maybe I'm just saying the image is over here. So maybe the rays of light might have gone like this, might have got refracted and come over here. So this will be your object distance, this will be your image distance. So the formula goes like that. If this is first refractive index, this is the second refractive index. Mu 2, mu 1, same thing, mu 2, mu 1, put equal to, put minus, here put denominator separately, here put a common denominator. That's it. Now start writing down the things. Here it is image distance, here it is object distance, and finally here it is radius of curvature. That's all. So this is how you can find where the image is formed based on where the object is for a curved surface refraction. Keep this in mind. Lastly, the magnification formula. The magnification, the height of the image by height of the object formula is V by U only, but you divide this V with mu2 and divide this object distance with mu1. So that is the formula for magnification of the image on a curved surface refraction. Again, very important. Next guys, what is next? Apparent depth concept. Yep, apparent depth, apparent height concept. So if you are looking at depth, apparent depth or apparent height, the formula is h by mu, or it is basically mu into h. When to use what? Observe carefully. In this case, the observer is in a rare medium. In this case, the observer is in a denser medium, So that's when you use this. And the object over here isn't dense. This is like bird seeing the fish, and this is like fish seeing the bird. So the object is in the rarer medium. So then the apparent distance is more. If you are the fish and looking at the bird appears farther, so you multiply. If you are the bird looking at the fish appears closer, so the height reduces. So this mu comes below. Next thing, over here, if you take a glass slab and the observer is over here, then the entire world behind him shifts. So this is called as the apparent shift. So if the thickness of the slab is T and the refractive index is mu, that particular shift which occurs is T into 1 minus 1 by mu. So that is the shift which occurs. Everything behind the slab shifts by this amount. If you have multiple slabs or multiple layers of liquid, each layer will cause this much amount of shift. Keep this in mind. This is your shift which occurs, and another shift which can occur is this kind of shift, where you had, say for example, a ray which was coming, it got refracted like this and it came out like this. Originally it was going like that. So there is a shift which is formed over here. That particular shift is called as lateral shift, and that lateral shift is given by, again, if this thickness is T and this is mu, again let's say we are told this is the angle of incidence, this is angle of refraction. It is nothing but thickness into sine of I minus R divided by cos of R. So that is the formula for lateral shift. Direct questions can come. Yep, very good. Excellent. Try to revise all the formulas, guys, with me. Okay, next thing for prisms. Next thing is for prisms. This is your prism. This is your angle of the prism. Let's say this is the light which comes, gets deviated and again deviated over here. So the light goes like this. This is angle of incidence. This is angle of emergence. These are the two internal angles, R1 and R2, right over here. Okay, what are the different formulas? First, the angle of prism is just simply R1 plus R2. Next, sine of I1, sine of just incident angle by sine of R1 is sine of emergent angle by sine of the other refracted angle, which is also equal to the refractive index of that particular prism. Snell's law, basically. Okay, just Snell's law. The ray originally was supposed to travel like that. So you can see that the ray finally got deviated by some angle. Deviation angle is nothing but incident angle plus emergent angle minus the angle of prism. prism. Now the graph of the deviation versus the incident angle when drawn comes out to be, that graph comes out to be something like this. So there is a location where the deviation is obviously minimum. So I can just call this as delta minimum. This happens when your incident angle is equal to emergent angle. R1 will be equal to R2. All these conditions are met. It is completely symmetric. It is completely symmetric relation. And this delta minimum can be found using this formula. Mu is equal to big 1 over here, and on the top you will put sine of, and here also sine of by, and this number 2 will also come. On the top you have delta minimum over here along with a plus delta minimum, you just have a over here. So mu is sine a plus delta minimum by 2 upon sine of a by 2. This is what you get for prisms. But if you have a special case which is called as a thin prism, which is called basically a thin prism, when you have a thin prism, then the deviations are almost same whether it is minimum or any other. This graph becomes very flat. All the deviations are similar, and that is just simply angle of prism into refractive index minus 1, only for thin prisms. Only for thin prisms. Okay, keep this in mind. Very, very important. Also, what happens is when you pass white light and it passes inside some medium, it splits into different colors, and it's the violet which deviates the most. Array, my god. This is some medium, guys. Some random medium in which it is going. So it is the violet color which deviates the most. Then yellow color, not so much. It is average color. Red is the least. So this is because they have different refractive indices. This phenomena is also called as dispersion. We all know that. This is called as dispersion of light. And the yellow color refractive index is actually the average of the refractive index of the red color and the violet color. Keep that in mind. So it is actually the average. So violet has the highest refractive index, yellow okay, red has the least. So deviation for violet is the most, red is the least. That is the phenomena of dispersion. These things you should definitely remember, guys. Okay, cool, awesome. Next, let's go to oscillations and waves, direct formulas quickly. Guys, let's do it. For oscillations, for a simple harmonic motion, for a linear simple harmonic motion, you will see the force is basically that particular force is nothing but minus k times of your x. Similarly, in your angular simple harmonic motion, you will see it is the torque which will try to pull you back with a torsional constant, let's say c, and angular displacement, let's say theta. That is the major difference. Yep. Here you can say x will be amplitude sine omega t plus phi. Here theta will be maximum angular displacement sine omega t plus phi. Few things will be common though. like omega will still be 2 pi into f, which is also 2 pi by the time period of oscillation. That is still going to be the same. Other equations which follow, like V is equal to A omega cos omega t plus phi. This particular thing over here, this is nothing but the maximum speed which occurs, A omega. Many problems use it, and this happens at the mean position. That means x equals to 0. Same thing is true for here. I'm not repeating it again. Again, velocity can also be written down as amplitude root of, sorry, not amplitude, omega root of, this omega root of amplitude square minus x square. This is another formula without time if x is given. Next formula, acceleration is minus a omega square sine omega t plus phi. And this particular thing again, that is the maximum acceleration, and that maximum acceleration magnitude is a omega square, and it happens at the extreme positions. At the extreme positions, that means x is plus or minus a. The other formula for acceleration is, you can use minus, you put omega square and then put x, minus omega square into x. That will also give you the acceleration. All these are the most important equations, guys. Yep. You also have the differential equation of SHM and all of it. We'll come to that now. Okay. Yep. Let's go ahead. Let's go ahead. Let's go ahead quickly. For a spring mass system, for a spring mass system, the time period of oscillation, is 2 pi under root m by k, and the equation for differential equation will look something like this: m into second derivative of x with respect to time plus your spring constant into your x will be equal to 0. So this is related to the spring mass system. Equivalent spring constant, I have done it in lecture 1, part 1, day before yesterday. Springs in series behave like resistors in parallel. Springs in parallel behave like resistors in series. That part I have done already, so please check that out. Okay. It is independent of gravitational acceleration, and so this is important, doesn't depend on g or any constant force. Like for example, if you make this vertical, still it will have the same time period. It's not like gravity will change the time period, or even if you apply a constant force. Next type of system is your simple pendulum. So length is there and it oscillates. So that's your simple pendulum situation. Simple pendulum. So in this case, the time period of a simple pendulum is 2 pi root of what? Length of the pendulum by gravity. Here it is independent of the mass. Here it is independent of the mass. Now please remember, this g can change. So I will put g effective, because we know in the lift problems, g can become g plus a, g minus a, all those things which I have told in pseudo force lift questions. Just check that part 1. If you have forgotten where it is, it's right over here. Yeah, this part 1. Where did it go? Here. Yeah, this particular video. Just go somewhere in Newton's laws. I have done it. Okay, somewhere in Newton's laws, somewhere. Oh yeah, I might have done it. Yeah, FBD, everything I've done. Yeah, so all these things I have done it over here. Okay, yeah, I think I just missed that. Somewhere here it is. Just before here. Yeah, see this lift problems. Yeah, okay, cool, perfect. So this is what you need to do. And remember, for seconds pendulum, time period is 1. So for seconds pendulum, the time period is 2 seconds. My bad. Time period is 2 seconds. Okay, so that is another important thing which you should definitely know. Okay, So this is done. All right. Next is compound pendulum. Next is compound pendulum. Compound pendulum, where you might have some disk or something which is hanging over here. The center of mass can be here and they are at a distance of d. Then the time period of oscillation is 2 pi under root moment of inertia I over here upon mgd. Moment of inertia upon mgd. This is another formula. And torsional pendulum, guys. Torsional pendulum. Torsional pendulum, which looks like a rod connected to some object. You are rotating it, it oscillates. So this case, the time period is 2 pi under root. See this constant which was there, right? C will come over here, that constant of proportionality. So it will be 2 pi under root a moment of inertia by torsional constant. This is your torsional constant. Torsional constant. That same C which was there over here. Constant of proportionality. Okay, guys? All these 4 pendulums, please remember. The one is spring mass system, one is this, and one is this. Okay? Very direct. Great. Okay. Now that this part is done, let's have a look at waves together. Okay. That is always better to see waves as a unit. Okay. So in general, any wave, let's say it's a transverse wave. So this is, let's say, a transverse wave. It is a transverse wave. Let's say this is the amplitude, and as it goes, the equation of the transverse wave will be given by y is equal to a sine. You can write omega t plus minus kx, or you can also use a cos kx plus minus omega t first, but anything. So many possibilities are there. So all these things. Basic terminologies over here. K is nothing but 2 pi by the wavelength. Omega. Okay, so this omega and k we are talking about. This k and omega. Omega is 2 pi f, which is also 2 pi by time period. Okay. Next thing is the wave speed. How is it related to them? The wave speed is obviously frequency multiplied by wavelength, which is also omega by k, which is also omega by k. Keep this in mind. Next, if it is by chance plus over here, plus means the wave is going in the negative direction, and if it is minus by any chance, then the wave is traveling in the positive direction of x. So it is exactly opposite. Okay, so that is how the sign convention goes. Now the same thing we can also do for your pressure wave, which is nothing but your longitudinal wave, which is nothing but your longitudinal wave. So imagine here there is compression, then there is rarefaction, and again there is compression, again there is rarefaction, and again there is compression. So again there is rarefaction. Okay. So this is basically your pressure wave, which is nothing but your longitudinal wave. Longitudinal longitudinal wave. Here, the pressure changes periodically, and delta P is pressure amplitude. Pressure variations are PM. Same thing, you can use sine or cos, anything will be okay. Kx plus minus omega t plus minus kx, depending on whatever is your convenience or whatever is there in the option. This is your maximum pressure. So this is also called as pressure amplitude. Pressure amplitude, keep this in mind. Okay, these are your excess pressures. This is your excess pressure or pressure variations from the normal pressure. So this is how it changes. Even the displacement, any particle that you take will go back and forth like this. It will be doing SHM. So the equation of that particular SHM, displacement of any particle, will be SM, but this will be cos kx plus minus omega t. If this is sine, this will be cos. If this is cos, this will be sine. The thing is, there is a phase difference between them. Yeah, there is a phase difference of 90 degrees between them. So that's why they will not be ever same. Displacement and pressures have a phase difference of 90 degrees. Keep that in mind. And these two are also related to each other. And the formula is Pm is equal to bulk modulus into this same K, which I have written over here, Bk, that same K, angular wave number, into your maximum displacement, BKSM. So this formula is also very, very important, my dear students. Okay, now that was for longitudinal waves. Similarly, we also have obviously electromagnetic waves. We similarly have electromagnetic waves. So let's say the electric field is like this, then the magnetic field will be, let's say, like this. Yeah, so that is magnetic field, and this is obviously your electric field. So how will the equations look like? Well, the electric field will be maximum electric field. You will have sine kx plus minus omega t. Okay, and the magnetic field will be nothing but B naught sine. Same thing. If this is sine, this is also sine. If this is cos, this is also cos. If this is kx, this is kx. If it is omega t, it will be omega t, like that. Okay, so that is how the formula goes. And keep in mind that always electric field cross producted with the magnetic field will give you the speed of light. Speed of light is in this direction, will be parallel to the speed of light. If you draw it in unit vectors, it is better. So I can make this as E cap, I can make this as B cap. That will be equal to your C cap. Always. Electric field is up, magnetic field is towards you. You will see the thumb is going in the direction of the speed of light. So this is another important thing. Okay. This expression is valid everywhere. Okay. This expression is valid everywhere. Wherever you see K, right, it is valid. Like omega is here also, K is here also, K is here also, omega is here, omega, K, K. These expressions for speed, everything are valid everywhere. Cool till this point. Shall we go ahead? Okay. Now for a transverse wave, what is the speed of the wave in general? For transverse wave, what is the speed? It is nothing but root of tension divided by mu. For sound in solid, it is root of Young's modulus by density. For liquid, I need some space over here. So for liquid, it is root of bulk modulus by density. For gas, after the Laplace correction, it is gamma RT divided by molecular mass. Gamma RT by molecular mass. For light, the speed of light is 1 by root of permeability of free space up into permittivity of free space. That is the formula. Okay, that's the major difference in all three of them. Clear, guys? Okay, perfect. Then we also have the power of a wave for transverse. So the power of transverse wave, the power of a transverse wave is half mu v a square omega square. Then you also have intensity of a longitudinal wave, intensity, which is nothing but half pm square by density into the speed, pressure amplitude, that same pm, pressure amplitude square by density into the velocity. Then you also have the intensity of electromagnetic wave, intensity of electromagnetic wave, which is nothing but half epsilon naught, and then you have E square, right? Just check this out, half epsilon naught into E square. Yes, no, I think that is energy density, energy per unit volume, energy per unit volume. Sorry guys, I think I made a mistake over here. Mhm. Why am I forgetting this? Okay, anyways, so I think it is energy. I'll just add this number later on. Okay, I'm just not able to remember it at the moment, but okay, okay, I'll add that. I'll also put up radiation pressure, radiation, radiation pressure, guys, radiation pressure of electromagnetic wave, radiation pressure of electromagnetic wave. Yeah, so the radiation pressure of an electromagnetic wave is given by that pressure is having two forms. First is intensity by C, or it is 2 times intensity by C, depending on whether the surface is absorbing in nature or whether it is reflecting in nature. And if it is transmitting it completely, then the power or pressure is basically zero. It will not create any pressure, it will just pass through it. If it is absorbing, it will be 2 times. If it is if it is absorbing, it will be 1 time. If it is reflecting, it will be 2 times. Is that okay, everyone? Clear? So all these are again very important formulas in your waves chapter. Now basically I think some specific formulas like for light waves, YDSC, what are the important formulas? First of all, fringe width is a lambda d by d, lambda d by d. Angular fringe width is just lambda by d. This is your fringe width. This is your fringe width. This is angular fringe width, angular fringe width. Okay. Then the coordinate of any maximas, the coordinate of any maximas is given by n times of beta, whereas the coordinate of any minima on the screen, any minima on the screen, let's say what the first minima. So yes, it will be n plus half into beta. N plus half. First minim, sorry, n minus half, my bad. N minus half multiplied by beta. Yeah, so that is the formula. And in general, the path difference in YDSC is small d sine theta when d is much larger than small d. For a single slit, for a single slit, diffraction which occurs, how is the formula going to look like? Well, the location of minimas is usually asked. So the y coordinate of the minima is lambda d, yeah, lambda d divided by a. This a is basically the slit width. Keep that in mind. This is the slit width. Very important. And you can also put n over here on the top. Yep. So you can put n times lambda d by a. First fringe, first minima, second minima, third minima is having the same formula like YDSC maxima. So there is a change over here. Just like this was n lambda d by small d. See, this was for maxima, right? For single slit, it becomes for a minima. Be careful. Yeah, the maxima formula becomes the minima formula. So the minima formula obviously will become the maxima formula, but with a small change again over there. Here this is n plus half, over here lambda d by a. Yeah, be careful over there. Yes. Is that right, everyone? Yeah. Yes, cool, awesome. Here also you have the width of central maxima formula, width of central maxima formula for a diffraction pattern, very similar but 2 times lambda d by a. That's all. 2 times lambda d by a. This is the distance between the screen and the slit. All these formulas again very, very important, guys. Then in general, when the waves will interfere, there might be some path difference. So the phase difference between the two waves is 2 pi by lambda into delta x, and those two waves might have certain amplitudes, and we have just obtained their phase difference. Let's say their amplitudes are a1 and a2. You add both these waves, and you basically get a resultant wave with a resultant amplitude. That is your resultant wave after superposition, after the superpositioning of interfering waves. So in that case, the resultant amplitude is actually the vector sum of the individual amplitudes, is actually the vector sum. Yes, so AR is actually root of nothing but A1 square plus A2 square plus 2A1 A2 cos delta phi. That is one important thing. And the resultant intensity, because if you see intensity always, where did it go? Intensity always is proportional to the square of the amplitudes. Every time, square of the amplitudes. So if you use that logic, you will see intensity is nothing but first intensity plus second intensity plus 2 root I1 I2 cos delta phi. And just keep this in mind, always intensity is always proportional to the amplitude of the waves square of the waves amplitude. Keep this in mind. Now in a special case, when there is constructive interference, when they are in phase, that means the phase difference will be 0, 2 pi, in general E1 pi, or the part difference will be 0, lambda, 2 lambda, in general n lambda. The resultant amplitude will be just A1 plus A2, and the resultant maximum intensity, by the way, this amplitude will not be any amplitude, this will be the maximum possible amplitude, will be root of I1 plus root of I2 the whole square. So delta phi, if you put 0, you can get it as this. Same way, if you talk about destructive interference, the amplitude will be minimum. It will be A1 minus A2. I don't know who is more, so put mod. And they are said to be then out of phase. So delta phi will be pi, 3 pi, 5 pi, basically odd number of pi. And your path difference will be lambda by 2, 3 lambda by 2, 5 lambda by 2, basically odd times the lambda by 2. And the intensity obviously is minimum. Same formula but with a minus sign. Root I1 minus root of I2 the whole square. That is what it is. Is that okay, everyone? So these are the formulas concerning interference. Last thing is your standing waves. So standing waves, guys, standing waves which are formed when two waves are interfering, moving in the opposite direction. The equation of such a standing wave is given by y is equal to 2a, you can use sine or cos, it doesn't matter, kx, and then again you can use sine or cos, doesn't matter, and omega t. So if there are three conditions in this, if you have string which is fixed at both ends, or a pipe which is closed at both ends, in that case any frequency is n times v by 2l. V is the speed of sound or speed of the wave on the string, n is your harmonic number, and the frequencies that you get are f, 2f, 3f, etc. This being called as your fundamental frequency. And you basically end up getting all the harmonics. All the harmonics. So this is when the string is fixed at both ends or pipe is closed at both ends. The same formula also is applicable also for the same formula is also for a string which is free at both the ends, or even for a pipe which is open at both the ends. The formulas are the same. Yeah, the formulas are definitely going to be the same. But when you have a string which is fixed and free, or a pipe which is closed on one side and open on the other side, then the formula looks like this for the frequencies. It is nothing but odd times V by 4L. And the frequencies that you get are F, 3F, 5F, basically only odd harmonics. Only odd harmonics. So for four things, the formula is same. Fixed at both sides, closed at both sides, free at both sides, and open at both sides. Okay, for all these things, it is going to be the same. Yeah, just few more minutes and we are done, guys. Yes, just few more minutes and we are done. Yeah. Okay. Last few formulas, only formulas we are looking at now. Yeah. So, dual nature of particles, photoelectric effect. Let's quickly have a look at it, guys, quickly. Energy, just few more minutes, 5 minutes more, and then we are done. Energy of photon is h into f, which is also hc by lambda. Okay, h is your Planck's constant, 6.6 10 to the power minus 34. Next is intensity of the photon beam is number of photons into hf, energy of each photon per unit time per unit area. This is the intensity of the beam. Next formula is the momentum. Momentum, do not use mass into velocity, rather it is h by lambda. Never ever use mass into velocity, that is wrong. Mass of that photon is assumed to be 0, that is at rest. There is no point of measuring it anything else. The speed of the photon is always assumed to be speed of light. The speed of basically light. Keep this in mind. Okay, the speed of the photon is basically the speed of light. Okay. Now, in the photoelectric effect, when light falls, this particular energy of the photon, okay, so here we were just talking about photons. Now we are talking about photoelectric effect. Yeah, energy of the photon will be equal to, remember, work function plus the maximum kinetic energy possible. Now that work function, I can also write it as h into f naught or hc by lambda naught. They are your threshold frequencies, threshold frequency or threshold wavelength. So photoelectric effect occurs only if the frequency is more than f naught or wavelength is less than lambda naught. Only then the photoelectric effect will occur. the energy of the photon should be higher than the threshold frequency. That maximum kinetic energy, the formula for that, I can write it as half m maximum speed square, or just E into the stopping potential. E into the stopping potential. That is very, very important. Next important thing is the graphs over here. Yep, very, very critical. Again, I'm drawing it. Current versus intensity. The graph of that is basically a straight line. This tells you that the current is proportional to the intensity of the light. Then the next graph is of this, where you have the voltage applied versus the current. That particular graph looks like this, and then it goes like this. So stopping potential is still the same no matter what the intensity is. So this is minus V stopping potential. Here this was less intense light versus this was more intense light. More intense light. So the intensity of the light will never affect the stopping potential. Keep that in mind. Okay. And lastly, this particular graph, this is again and again asked. That's why I'm drawing it for all of you guys, taking all the efforts. Yep, this is your threshold frequency versus the stopping potential. So it looks something like this. If you draw it, it is like this. For different metals, the graphs are in this particular manner. The slope is always the same, which is h by E. It is going to be the same when you draw it for stopping voltage versus frequency, but where it intersects the y-axis, that will be different. It will depend on the work function divided by E. E is constant, phi will depend on the material. So different materials, no matter when you draw, how you draw the graphs, they're always straight lines with parallel to each other with same slopes, but with different. This may change if material changes. If metal changes, basically, if the metal changes. If the metal is changed, then obviously this y-intercept will definitely change. So these things you should definitely know. Next thing is for particles, the dual nature, the de Broglie wavelength. So when a particle of mass m moving with velocity v, the de Broglie wavelength, de Broglie principle is nothing but h by p, which is h by mv, which is also h by root of 2 times mass times kinetic energy. All these formulas are valid. Only for an electron, the formula, you should better know it, 1.227 divided by root of the voltage difference by which it was accelerated, but this is in nanometers. So in general, if it was accelerated, that kinetic energy that it gets will be the charge multiplied by the voltage difference. But for an electron, if you substitute the mass, charge, h, everything, and convert everything in nanometers, this is what you get for electrons only. Keep this in mind. Okay. Remember, for particles, our energy, which is your kinetic energy, G is given by half mv square, which is also square of the momentum by 2m. That is what I have used over here. This is very likely used. Okay, cool. Oh, Telugu చూస్తావా? Telugu తెలుసు, sorry. Oh, nice. Telugu people are here. Welcome. అందరికీ నమస్కారం. Yeah, come on. Very nice. Very nice. Nice to see all of you guys. Okay, cool. So, what else is there? Okay, atoms and nuclei. In atoms and nuclei, what are the main formulas? Let's quickly go through it, guys. First is your Rutherford's approach. So in Rutherford model, the distance of closest approach formula is half mass of the alpha particle into speed of that alpha particle square is 1 by 4 pi epsilon naught gold nucleus Z or any nucleus into E into whatever is the charge of that alpha particle, which will obviously be 2 times of E, the whole thing divided by distance of closest approach. This is one important formula. For Bohr's model, the three formulas which are important are: number one, the electric force is the centripetal force. So it will be m into v square by r is 1 by 4 pi epsilon naught ze into e divided by r square. This is one formula. Second formula is your angular momentum is nh by 2 pi. Angular momentum is mvr. So that is equal to nh by 2 pi. Then the third formula which is important for Bohr is the energy difference between the orbits is the energy of the photon, and energy of the orbits is minus 13.6 electron volt divided by n square, and z square is also there, 13.6 z square electron volt divided by n square. Okay, maybe one orbit minus 13.6 z square into square electron volt, and this is nothing but hc by lambda, which is 1240 electron volt divided by lambda, which is in nanometers. So you can convert it into meters and all of that, and you will get 1 by lambda is Rydberg's constant z square 1 by n2 square minus 1 by n1 square. So this is the wavelength of the light which is emitted, which is useful for your hydrogen spectra. Keep that in mind. So uh, Lyman series, um, your N2, your final orbit will be 1 and it will be an ultraviolet region. Then you have your Balmer series, where your N2 will be 2. It is usually in the visible region. Then you have your Paschen, Lyman-Balmer Paschen series, where your N2 is basically 3. It is in the near infrared region. After that, P-fund bracket goes in the far infrared region. Okay. Next, the radius and the velocities and all those things. So using these formulas only, radius is proportional to n square by z. Velocity is proportional to z by n. And your total energy, which I have already written down over here, is negative 13.6 by n square z square in electron volt. Needless to also say that our kinetic energy is the negative of the total energy, and the potential energy is double of the total energy. Potential energy is the double of the total energy. All these formulas, please use it. All these formulas, please use it. Is that right? Okay, very good. Okay, what else? Semiconductors, there are not many formulas. Okay, nucleus formulas will quickly discuss, guys, quickly. Yes, first of all, atomic mass number is atomic number plus n. So if you have an element like this, usually you put atomic mass number over here, x over here. That's how you put it. Then the radius of the nucleus or radius of nucleus is r naught into this a raised to 1 by 3. But if you find the density of the nucleus, it is always a constant of any nucleus: gold, iron, lead, uranium, hydrogen, everything. It is always a constant. Next, you have something called as the mass defect, which is what you expect the mass to be minus what is real. Often, say for example, you have n number of, how many number of protons you will have? Z number of protons, and you had n number of neutrons. When they combine together, it should give you the mass of the nucleus. But when you actually measure the mass of the nucleus, it is slightly different. So that is called as the mass defect. And that mass defect is what causes the energy losses given by Einstein's equation. And the delta E is the delta M into C square. So this is Einstein's equation. Einstein's equation, guys. And if you express the mass in atomic mass units, you multiply it with 931, then the answer that you get, if this is in atomic mass unit, the answer that you get is in mega electron volt. Okay, the answer that you get is in mega electron volt. This particular thing also called as the binding energy. This is also called as the binding energy of that nucleus. Also, you get the Q value of a nuclear fusion or fission reaction, which is again delta M into delta M into 931. You can do that, or you can also say basically it is nothing but the binding energy of your product minus binding energy of the reactant. You also have something called as the stability of the nucleus, which is given by stability of a nucleus, which is given by what? The binding energy per nucleon. Yes, the binding energy that you get per nucleon, A. That is going to give you the stability of the nucleus. There is a beautiful graph for it, binding energy per nucleon versus that nucleus. Okay, that graph goes something like this. It goes up and it becomes like this. It is highest for iron. It is highest for iron. You should know this graph. Very good. These are the main formulas in nucleus. Radioactivity is not there. Only the alpha, beta, gamma decay is there. Alpha means two positive, two protons, two neutrons. Beta means one negative electron. Beta plus means one positive electron. All these things. These are the main things that are there in radioactivity. Apart from that, law of radioactivity is not there. Yeah, law of radioactivity of decay is definitely not there. So you should know those three reactions. That's enough. In semiconductor, you don't have any formulas. Basic formulas that you might have is like this: number of electron concentration, number of hole concentration is intrinsic concentration square. Resistance is voltage by current, but dynamic resistance is delta V by delta I. This formula is there. Then you might also have this formula. Conductivity is conductivity of electrons plus conductivity of holes, which comes out to be electron charge into mobility of electrons into number of electron concentration, same thing, plus same charge of the holes is E only, mobility of the holes into number of hole concentration. Usually mobility of electrons is much larger than mobility of holes. So this is your conductivity. This is your conductivity of a semiconductor. Keep this in mind. All these things very, very important. Any other formula that I'm missing, just let me know. In semiconductors, in logic gates, see, NOT gate means what it does is opposite. 0 becomes 1, 1 becomes 0. OR gate, what it does is whatever is the input, if any input is high, the output is high. Any one, 0, 1, 1 is high, output is high. 1, 0, output is high, that's it. Both are high, it is anyways going to be high. Then you have AND gate, whatever is the input, only if both are high, both are going to be high, the output is going to be high. The output is going to be high. If you add a NOT gate in front of a OR gate, so that becomes a NOR gate, and a NAND gate becomes when you add a NOT gate in front of an AND gate. They are also called as universal gates. They are also called as universal gates. And keep this in mind, if you take a NOR gate or basically a NAND gate, their behavior, yes, they behave just like a simple NOT gate. If you short it, they behave like a NOT gate if you connect these terminals together. Yep. So if you connect these terminals together, these two gates behave like a simple NOT gate, useful in many applications, many problems. You also have something called as a exclusive OR gate. Only if one input is high, then the output is high. That means 0, 0 will be low, 0, 1 will be high, 1 XOR 0 will also be high, but 1, 1 will be low, because only if one input is high, both are high, it will not work. That is your XOR gate. Many times you will see that. If you ask me, the mathematical operation for this will be, if you talk, y will be x bar, this will be y is equal to a plus b, here it will be y is equal to a dot b, and here it will be nothing but y is equal to a XOR b. XOR symbol is plus. Okay, and one formula, guys, in these things, which it's better if you know, a plus b, I will put it over here only, maybe, a plus b whole bar is a bar dot b bar. Yeah, the whole common bar will get separated, the plus will go with a dot, replace with a dot, and if you have a dot b whole bar, it will be a bar plus b bar. Dot becomes plus, the bar gets separated. All these formulas again useful in your logic gates. Okay, I think we have done most of the things. 99% we would have done. If anything else is remaining, I'll just let me know. We can probably do it as a problem in some of the mock tests. Okay, great. Yeah, it is called as a De Morgan's law. Perfect. So that's it, guys. Physics is done. Now it's time for biology. Let me just call up. Sorry, guys, I exceeded by half an hour. Let's connect with Gopika ma'am. Not sure whether she's there in the chats.
Let's start the class, students. So I hope all of you have watched the 11th, okay, class 11th complete marathon. Now we are going to do class 12. So let me already give you a disclaimer that we are going to start with the high weightage chapters, starting from sexual reproduction of flowering plants, then molecular basis of inheritance, human health and diseases, then biotechnology unit. Then if time permits, we'll come to reproductive health and evolution. As all of you know, reproductive health, max to max 2 questions will come. Evolution, 1 question or 2 question will come. So in case time does not permit us, let's actually finish the chapters that give us 9 questions, 5 questions, 8 questions. So let's finish all those chapters and then come to the low weightage chapters. Okay, yes, good afternoon, students. How is the energy? Is the energy high? All my GMAs are fully energetic after the lunch break. Okay, don't worry, today I'll give you a break. Okay, last time we couldn't give break, today we will definitely give you a break. Okay, done. Chalo, let's start. Okay, let's start. Got it? Okay, perfect. Okay, which chapter we will start? We will start with sexual reproduction in flowering plants. Okay, so I have already drawn a beautiful flower for all of you, so I can save all of your time. Okay, so all of you know this is a flower. Ma'am, why are you starting with the flower topic? Students, flower is very important for you to understand because we are going to talk about all the essential parts of the flowers that are going to ultimately, okay, do you think flowers are growing just so that Chintu can give it to Mintu? Not exactly. It is not for you to show or express your, feelings to someone. Flowers are being produced by a plant so that they can continue their sexual reproduction, right? They can continue their sexual reproduction. So if you look at this flower here, there are few parts to the flower, right? First, let's start with the first one. What is the first one called as? It is, okay, it is the stigma. Okay, it is the stigma. After stigma, what comes, students? Here I have labeled an anther, which is a bilobed anther. Okay, then we have filament. Okay, then we have filament. All of you, please tell me the parts. Okay, this arrow is pointing at petals. Okay, this arrow is pointing at petals, and this arrow is pointing at style. Okay, here, which arrow is this? Yes, sepals. Okay, this arrow is pointing at your ovary. Then this arrow is pointing at thalamus. And then we have ovules. Okay, just see if my labelings are correct. Okay, if I can properly see the arrow marks. Yes, tell me if my labelings are correct. Yes, excellent, excellent. So these are the labelings. Okay, stigma, anther, filament, petal, style, sepal, ovary, thalamus and ovules. It is not about knowing the parts of the flowers. The actual concept is knowing the essential and the non-essential parts. So if you look here, students, these two are the essential parts. Ma'am, what do you mean by essential parts? In your family, your mother and father is the essential parts. That means what? Or in our life, mother and father is the essential part. That means without them, we cannot live forward. Without them, we cannot be happy. Who are the non-essential parts? That means they're not, it's not like they're not directly involved in our life. They are involved in our life. They do give us happiness. It could be our friends or colleagues or cousins, right? Same way here also, what is going to happen? Your essential parts are going to be andretium and gynoecium, and this is what you're seeing here as andretium. Okay, this one what you're seeing here is andretium. Okay, and this what you're seeing here is the gynoecium. Now what does andretium have? Okay, andretium has many units of stamens. Okay, and what does a stamen constitute? An anther and a filament together. So this whole thing is a stamen. So many stamen, students, together forms the andretium, and what you are seeing here is an anther, and this anther is a bilobed. Can you see two lobes? Can you see two lobes? Is there any student who cannot see two lobes? Right? It is bilobed. Okay, all of you should keep answering, and as you understand a concept, I want thumbs up in the chat box. You can ask each other, how are you? Did you eat food? Will you come to this place to meet me? All that later. Okay, there are actual serious students, so don't disturb them. So please keep putting thumbs up in the chat box. Okay. Now, gynoecium, students. Gynoecium is made up of what? Stigma, style and ovary. Inside the ovary, there is going to be ovule. So gynoecium also is an essential part, and that is going to be the female reproductive part, and the andretium is going to be the male reproductive part. Done, done, done. Now, if you look at this non-essential part, they are not directly involved in sexual reproduction. So essential means the ones that are directly involved in reproduction, and non-essential means the ones who are not directly involved in reproduction but still help with reproduction, right? So if you look here, non-essential, you have the corolla. So I'm writing the words, okay? Corolla, and this is going to be what, students? Calyx. Okay, this is going to be calyx. So corolla constitute many units of petals. Okay, and calyx constitute many units of sepals. And what are sepals going to do? They are going to protect the bud. Okay, they're going to protect the flower in the budding stage. Okay, yes or no, clear to all of you? So corolla, petals, calyx, sepals, gynoecium and andretium, these are the four worlds that you're going to talk about. Now students, there's two lines mentioned in your NCERT, that is, if you look at the let's say this one, okay, filament and anther, please do understand that to the thalamus, okay, this is the thalamus. To the thalamus, your filament is at the proximal end and anther is at the distal end. Okay, whatever is here, whichever is close, okay, this is going to be the proximal end, this is going to be the distal end. Okay, in case the question comes, you should be in a position to answer. Clear to all of you? I hope that is clear. Now let's go to the main portion from where the questions are going to be framed. Okay, the main portion from where questions are going to be framed. Look here. So students, this is what I told you. This is the thalamus. Closer to the thalamus is going to be the proximal end, and away from the thalamus, who is going to be there? Anther is going to be there, the distal end. Okay, the distal end. And stamen is unit of andretium. Stamen has what? Anther and filament. Okay, now when we talk about anther, anther has so much more to study. It's not just that, okay, it's bilobed. We have sectioning of the anther, and we have to study the layers of anther, because inside the anther your pollen grains are going to be there. Pollen grains are going to have the male gamete, right? So it is a complete process of understanding the male gamete. So if you look at the anther, students, you can see two lobes, L1 and L2. These are the two lobes of the anther, and this anther, we understand that these people are bilobed. You understood that there are two lobes, so they are bilobed. Okay, now when you go into the anther, they are telling that one lobe has two thecas. Can you see the thecas? 1, 2, 3, 4. So that means what? They have 4 thecas. One lobe will have 2 thecas, so we call it dithecus. Okay, we call it dithecus. And this when before it becoming a pollen sac, we call it microsporangium. What do we call it? Microsporangium. And that entire process will be called as microsporogenesis, right, where we are going to form the male gametes. Now microsporangium will later mature to form your pollen sac. Inside the pollen sac, pollen grains are going to be there. So sporangium I can say, right? So there are 4 sporangiums, so we will call it what? Tetrasporangiate. Clear to all of you? Any doubts in this? Tetrasporangiates. Okay, yes. Now look here, students, when you take a dissection, okay, of your anther, if you take that lobe and you take a dissection of it, you are going to see something like this. Okay, now what is this, ma'am? I will tell you. See, look here. These are the sporangium that I spoke about. That means your microsporangium. This microsporangium is going to mature to form your pollen sac, and inside the pollen sac, the pollen grain is going to be there. So I want all of you to think about the flow. Okay, think about the flow. Now look here. This mic, yeah. Okay, now look here, microsporangium. Okay, these are 4 are microsporangium. Now I want to see what is inside a microsporangium. Okay, let's say Jayasurya is not happy that, okay ma'am, you showed me the microsporangium. He's like, ma'am, take a cross section of the microsporangium and show me, and I will tell you that there are 4 layers in the microsporangium. All of you answer me quickly in the chat box, which are the 4 layers of microsporangium. So to keep these 2 thecas together, we have a connective. So they can give you a diagram and they can ask you to label this. Okay, they can give you a diagram and they can ask you to label this. Clear to all of you? Yes or no? Okay, so these 2 thecas are connected with a connective. They are connected with a connective. How difficult is it to remember, right? They are connected with a connective. Clear to all of you? Now, the 4 layers. Which are the 4 layers, students? Yes, it is going to be elephant eats my tomato. Imagine you're a farmer who has a lot of tomato plantation, and elephant has come one day and it started eating your tomato. So, elephant eats my tomato. E for what? E for epidermis, E for endothelium, M for middle layer, T for tapetum. Now, it is important to know the function of all these layers. First 3 layers, that is your epidermis, endothelium and middle layer, are going to be the ones who are going to do the protection and dehiscence. Now, what is dehiscence exactly? Dehiscence means the ability to break open the anther. Students, if you don't break open the anther, how will the pollen grains get scattered, right? We need to make sure that this dehiscence happen. So, epidermis, endothelium and middle layer is going to do protection and dehiscence. On the other side, you have tapetum, who is the main part. Okay, tapetum is the main portion, that is main part. Why? Because that fellow is going to do nourishment. At the same time, he is also going to secrete Calais enzyme, whose function will be known later to us. Okay, clear to all of you? Yes, excellent students, excellent. So look here, epidermis is a single person, okay, single. Endothelium also is single, but middle layer is not single. It can have 2 to 3 layers. Tapetum is again a single layer. Now look here, these people are all going to do the job of protection, dehiscence, protection, dehiscence. This fellow is going to do the job of nourishment. Now, in the microsporangium, exactly at the center, there are some special tissues. What are those tissues? All of you tell me in the chat box. Those tissues are called as sporogenous tissues. What are they called as? Sporogenous tissues, which are present in the center, and they can mature to form the pollen mother cell or the microspore mother cell. Why, ma'am, we need all of this? Because we have to do microsporogenesis. Is this clear to all of you? Can I see thumbs up if you understood all of this? Yes. Tapetum is multinucleated or middle layer is multinucleated. All of you can tell me that also in the answer. Okay. Team also you can remember. Okay, instead of elephant eats my tomato, one student is telling team. Okay, but the spelling is a little different. It is team, T-E-E-M. Okay, so tapetum, you have to remember, but the order is different. That is why we do not prefer tricks like this, because if you need to know the order, okay, you need to know that the first layer is epidermis, then comes the endothelium. Okay, quickly answer in the chat box. Excellent, all of you understood. So that is what happened in your anther. Now the second portion from where a lot of question comes is about your microsporogenesis. Now you understood that in the middle there is a sporogenous tissue who has the ability to form pollen mother cell or microspore mother cell. Now what will a mother do? Right, they will undergo meiosis and they will go into the next level. Okay, so here you see, students, this sporogenous tissue will undergo division, or let's say it will undergo maturation to form microspore mother cell or your PMC, and these people are diploid. They will undergo meiosis and they'll form microspore tetrad. Now I told you one thing, that tapetum will release an enzyme. Come on, what is the enzyme? Okay, what is the enzyme? Come on. Come on, come on, come on, come on, come on. Answers quickly. What is the enzyme? I hope all of you smashed the like button. Okay, I did not check your attendance. I'm assuming that you people are good enough to mark your attendance. Okay, come on, mark your attendance, all of you, and also answer this question for all of you quickly. Let me see if all of you marked your attendance. All conjuice didn't mark your attendance. Okay. Okay. Yeah. Excellent, excellent. Calase enzyme. Okay. Now what happens, students? This mother, okay, very difficultly she did meiosis. But these kids don't want to separate. So here what is happening, students? These microspore tetrads are attached together and they are not ready to separate. If they do not separate, I cannot form ultimately pollen grains. Pollen grains are the gametophyte. Inside the pollen grains is my gamete. So how am I going to do the entire process? So this microspore mother cell will undergo meiosis and they are going to form microspore tetrad, and these microspore tetrads are attached together with the help of callose. Don't get confused. ACE is the enzyme. Calase is the enzyme. Callose is the one that is keeping them together. So tapetum will tell, don't worry, I have already made calase enzyme which will degrade, okay, this callose layer and make sure that the microspore tetrads are going to be separate, okay. So now students, look here, the microspore tetrads have got separated and each of the microspore tetrads are potential pollen grains, okay. Now question to all of you, what is a gametophyte? Okay, what is a male gametophyte? Is it the pollen grain? Is it the microspore tetrad? Is it the male gamete? What is a male gametophyte? This question has come and let me tell you, majority of the students have gone wrong, okay, because you don't have clarity while studying. Answer quickly. So tapetum released calase enzyme and the calase enzyme had degraded the callose layer which kept them together, and now each of the microspore has become into a pollen grain. Now how does this pollen grain look like? It has two layers, okay. Yes, excellent. The gametophyte is pollen grain. Inside the pollen grain, the generative cell will have the male gamete, okay. No, don't ever make this mistake after studying it from my class. Understood? I will come there and hit you people, okay. So come here, okay. This microspore tetrad, students, they will undergo mitosis and they will become a pollen grain. Pollen grain has two layers, intine and exine. Exine is the outermost layer which is made up of what? In the chat box, quickly, okay. So exine is going to be there. That exine is made up of something that you people are going to answer. Now intine is there. Intine is made up of what, students? Cellulose and pectin. Cellulose and pectin, okay, clear? Yes ma'am, clear. Cellulose and pectin, and they have two cells, okay, inside, vegetative cell and generative cell. Now from a PYQ point of view, what is the question that is going to come? Vegetative cell, what is the shape of the vegetative cell nucleus? You will answer that it is round shape. What is the shape of the generative cell nucleus? You will answer spindled shape, okay. Excellent. Sporopollen. Exine is made up of sporopollen, which is one of the most resistant organic matter ever to be found. It does not degrade with alkali, it does not degrade with acid, it does not degrade with temperature. Nothing can degrade it. And there is also one problem, that if a pollen tube germination has to happen and we have sporopollen who is like a very strong person, now how will Aditi go out? Okay, imagine Sumo is standing outside and Aditi can't go out. So what we have done, for Aditi to go out, we have kept a small door next to the Sumo itself telling that you please escape from here. So like that, there is a small opening, or not opening exactly, a small space where the sporopollen is absent, and that place is called the germ pore, from where your pollen tube germination is going to happen. Clear to all of you? So pollen grain has exine and intine. Exine is made up of sporopollen, intine is made up of cellulose and pectin. There is a portion where exine is going to be absent. That portion is called the germ pore, where the pollen tube germination can happen. Pollen grains have two nucleus, vegetative nucleus and generative nucleus. Vegetative nucleus, or vegetative cell has nucleus which is round, and the generative cell nucleus is spindle shaped. Now again, one more question to all of you. Who is going to have the reserve food material, vegetative cell or generative cell? Again, all of you answer. Got it, ma'am? Yes, excellent. Very good. Come on. Who is that, yeah? Sitting and talking. If I start calling your names, no, that's all. So come on, tell me, who is going to have the reserve food materials for the growing male gamete? Okay, growing male gamete. Come on. Exactly, because Tumo can't enter through the small door. We have kept a kuti door for Aditi to go out. Okay, Aditi will be very happy. Excellent. Vegetative cell is going to have the food reserve material. It is going to have more cytoplasm. So it will have all the food reserve material for the power generative cell that is growing and coming, who is going to have the male gamete. Clear to all of you? Done, done, done? Yes or no? So student, oh no, answer was here. Did you people copy? Tell me honestly, did you people copy from here? I asked you the question and I did not see the answer was here. Okay, I just hope that you did not copy. Okay, I trust you people. Pollen grains are the male gametophyte. Okay, yes. Now, megasporogenesis. So I hope microsporogenesis is clear to all of you. Pollen grain is clear to all of you. Exine, intine is clear. Vegetative cell, generative cell is clear. Pollen tube, germination is clear. Yes, all of you, pakka. Now can we go to megasporogenesis? So microsporogenesis done, anther is done. Now we will understand what is ovule and what is megasporogenesis, because these are the main two portions of the chapter. Other than that, questions will come from where? Very few questions will come from the seed and apomixis, polyembryony. Very few questions will come. Mainly questions will come about the ploidy level, about the embryo sac, about the pollen grain, about the generative cell, the shape of the nucleus, all these questions. Okay? Yes? Tell me. Be honest. No, no? Okay, very good. I'm proud of you people. Okay. Now, megasporogenesis. Megasporogenesis means what? Ma'am, you already formed the male gamete. Now, what are you thinking, ma'am? We have to form the egg. We have to form the female gamete. So, we have to do megasporogenesis. So, there we did microsporogenesis and now we are going to do megasporogenesis. Okay. Formation of megaspore from megaspore mother cell. So, there also it is MMC. Here also it's MMC. But what is the difference? One is the microspore mother cell. One is the megaspore mother cell. Done, done, done. Okay. Yes. Ploidy level I'll teach you. Okay. Now look here students, this is the stigmastoidin ovary, and inside the ovary the ovule can be present. Now the ovule, how many numbers of ovule, what is the placentation, that is differently you will study in morphology, right? Placentation you have already studied depending on the arrangement of the ovule and how many will be present in one locule, etc, etc. Now students, if I take an enlarged structure of this, this is how my ovule is going to look. You'll be like, ma'am, why have you put the ovule upside down? Because your ovule is going to be an anatropous ovule. Now it's not necessary that you draw it upside down. You can also draw it this way like shown in your NCERT. Now what does it mean by anatropous ovule? Anatropous ovule means, students, remember, you have chalazal end, micropylar end and the funicle. If the chalazal end, micropylar end and the funicle comes in a straight line, they are going to be a different ovule. Okay, they are going to be different. In case they do not come in the same line, we see something like this where the micropylar end, chalazal end and the funicle is towards one side. This is called as anatropous ovule. I have taught you different types of ovule in my detailed class. So that time you can just go through the ovules, but it's not necessary. Questions will not come like that. I'm just telling you why you call it anatropous ovule. Now, first PYQ question that can come, the notch. Okay, a notch or the portion where the ovule is attached to the funicle. What is your answer? What is your answer? Come on, tell me. Come on, come on, come on, come on. Yes, answer. Faster, faster. The portion, okay, the portion where the ovule is attached to the funicle. Question, it's a PYQ question. The answer is going to be what? Hilum. Again, you have one more hilum in excretion, that is the notch. Yesterday I taught you the notch from where the ureter, nerves, all of that enter, okay. This is the portion where the funicle is attaching towards the ovule, okay. Now, if you go further, students, you understood this is a stalk-like structure which is going to hold the entire ovule together. This portion is a micropylar end, the portion where the egg is going to be present, okay, egg apparatus is going to be present, and the portion where there is an opening, that will be called the micropylar end. Now, two integuments are there to cover it. Very good. Two in the kidney noda, here you have to tell. In there it is concave shape, notch and all that, okay. Here you see it is hilum, just a connection. Now here students, there are two types of integuments, inner integument and outer integuments, which are ultimately going to form what? Seed coat, testa and tegumen, okay. That is the fate of your outer and inner integument. So in case the question comes, what is the fate of inner and outer integument? Your answer should be testa and tegumen, okay. Now, inside this, there is one full layer of a special cell. What is that special cell called as? Nucellus, okay. What is that special cell called as? Nucellus, okay. Not nuisance, nucellus. These nucellus, one of the cells of the nucellus will be like, you know what, I am going to become the megaspore mother cell because I am capable, and that nucellus, one of the cells, will form the megaspore mother cell. That megaspore mother cell will undergo megasporogenesis to form your egg. Is this clear to all of you? Yes or no? Answer quickly in the chats if it's clear. Hmm? Yes, excellent. Excellent. Okay, new syllabus. Okay, now going forward. Ayyo. Okay, one second. Viability will finish after embryo sac. Okay, yeah. Now megasporogenesis. What happened? One of the nucleus cell took up the initiative that I am going to become the megaspore mother cell, and they came forward. And students, ploidy is going to be 2n. Okay, 2n is going to be the ploidy. There also the ploidy was 2n. Now the megaspore mother cell will undergo meiosis, and even she wants to form a tetrad. Even she wants to form a tetrad, but unfortunately what happens? 3 of them will degenerate, only 1 will become functional, and the one that is going to be functional is towards the chalazal end. Okay, this is not, I don't think a question will come out of it, but it's good to know. Okay, that is the one which is present towards the chalazal end will become functional, and the rest of the 3 will degenerate. Okay, which she's very sad about. And then that kind of development is called as monosporic development. Monosporic means what? One of them, okay, mono, single, one of them is going to undergo development. Even though 4 we formed, only 1 is going inside. Okay, so 1 becomes functional, and that will undergo mitosis division. Okay, students, so meiosis happened. After this, mitosis division is going to happen from 1 nucleated to 2, 2 to 4, 4 to 8, like that. 3 mitotic division will happen for us to get a 8 nucleated stage. Now chumma, if I leave like this 8 nucleated stage, will that be okay? Now how do I know which is the egg, which is the antipodals, which is the synergids? So this 8 nucleated stage will undergo a division, like a maturation, to get separated, to move towards the pole, and to be present in the center to form your entire embryo sac. Okay, very good. 8 nucleated, 7 cell stage. So this 8 of them is going to again mature, align themselves. Okay, align themselves like that. You know what? I will become antipodals, I will become this, like that. They are going to assign or align themselves. And please remember, your antipodal cells are haploid in number. Okay, here also your egg and synergids are going to be haploid in number. Only your polar nuclei is going to be diploid in number, right? Because 2 of them are there. Clear to all of you? So here what is going to happen, students? 3 of them will move towards the chalazal end. How will you remember this? I told you, AC, you bought it in EMI. Okay, you bought AC because it's summertime in EMI. What do I mean? A for antipodals. Okay, A for antipodals. Okay, C for chalazal. Okay, E for egg, M for micropilar end. Okay, micropilar end. So you bought AC in EMI. Okay, you bought AC in EMI. So A for antipodal, C for chalazal, E for egg, M for micropilar. I took for depth. Okay, I took I from the bank because I wanted to complete the statement. Now, antipodals are going to move towards the chalazal. 3 of them will align themselves there. Okay, now 2 of them will be like, you know what, I want to be the center of attraction, so I will be in the central cell, and this will form a central cell, and between them there is going to be, students, the polar nuclei. Polar nuclei is very, very important for us because we are going to learn it in double fertilization. Okay, clear to all of you? Now, and 3 of them will move towards the micropilar end, telling that we are going to form the egg apparatus. Egg apparatus is going to have what, students? It is going to have the egg. It is going to have 2 synergids. Okay, again, synergids are going to be haploid in number. So synergids are going to be there, egg is going to be there. Now a PYQ question that can come for all of you is that what is the function of filiform apparatus, or filiform apparatus is present in which component of the embryo sac? Your answer should be synergids. What is the function of filiform apparatus? It is going to guide the pollen tube during double fertilization or fertilization generally. It will tell the pollen tube, come this way, this is where your egg is going to be there, come this way, it will tell, and the pollen tube is going to go that way. Clear to all of you? Yes or no? Yes or no? So again, a very important PYQ question is 7-celled 8 nucleated. Students, these are going to have nucleus, but they are going to consider it as 1 cell. So 7 cell, 1, 2, 3, 4, 5, 6, 7 cells. But how many nucleus? 1, 2, 3, 4, 5, 6, 7, 8. 8 nucleated, 7 cell stage. Clear? Yes or no? Yes or no? Clear to all of you? Clear to all of you? Yes, very good. Okay, very good. Now, moving forward, the viability. Now, we have already formed the gametes. Is there any student who has a doubt with the gametes? Not at all. We have already formed the gametes. Now, when we talk about the gametes, students, next thing we have to talk is, ma'am, if the gametes are formed and let's say this pollen grain is going outside, what is the validity? Now, when in our phones also, students, let's say we are using credit card or we are using Swiggy or we are using Zomato, we will get an OTP. Okay, as a confirmation. Now that OTP will only be valid for 5 minutes, or some of the OTPs are only valid for 1 minute when it is too confidential. Okay, be it Aadhaar card, PAN card kind of things. OTP will be valid for 2 minutes or 1 minute. Now, what does that mean? That means that OTP is valid only for 2 minutes, and after 2 minutes, if you are entering the same OTP, you will have to degenerate the OTP. That is, you have to do it once again. Same way, if I am going to release the pollen grains, if the pollen grains have already left the plant, then there is a viability. That means there is a validity for this pollen grains to be active. If the validity is over, then these pollen grains are of no use. Okay, so viability means ability of a pollen grain to germinate on the stigma. That means with this time period, if the pollen grain does not land on a stigma and stigma does not accept it, then the whole process is waste. Whole process is waste. So here they have given few examples. Again, they can ask as a direct PYQ question. What is it? Cereals. Okay, like your rice and wheat, they have 30 minutes viability. That means if the pollen grain is released within 30 minutes, it has to go and land on a stigma. Otherwise, gone, students, gone. Okay, then no done will happen, gone will happen. Okay, now members like rosole. Rosole is a Hindi word, is what I believe. Okay, because of my extreme Hindi knowledge, I think rosole is a Hindi word. Any students who are who knows Hindi, please answer that in the chat box. Okay, rosole, students, it will have viability for months. Now, what is the rosole full form? Rosaceae family, Solanaceae family and Leguminaceae family. Okay, like your bean family and all of that, pea, bean. So, those families will have the viability for a month. Okay, for a month. Okay, so remember like this, rosole. I think one song was there. Okay, now look here, students. But see, even though viability is there for 30 months and 1 month, there are some consequences, like in the sense there are some factors that depend, no? That factors also we have to take into consideration, okay? Yes or no? Okay, all of you are like me only, all illiterates in one class, okay? No one knows Hindi, okay? Anything I tell, they'll tell, yes ma'am, this is only Hindi word. Congratulations, Gopika ma'am is multilingual, okay? Nice to have students like this, clear? Very good. Okay, now it depends on temperature, humidity, and very, very important question again goes here, students, a PYQ question. It was a PYQ question, is that how do I store the pollen grains? Now, just imagine, I know that, the sunflower or let's say this orchid season comes only during the marriage time. Okay, it is usually in the month of May. Now, I want to protect that pollen grains and keep, and their viability is too short. Now, what do? I have to make sure that I store it, no? Like how we have blood banks and all of that. Same way, I'm going to store it at minus 196 degrees Celsius in liquid nitrogen. Very important. How much? Minus 196 degrees Celsius in liquid nitrogen. Will you remember? Yes. Don't tell proud to be GMAs. Okay. Don't spoil my name. Don't spoil my name. Okay. Cryopreservation. At least I know it is the Hindi word. You people don't even know that. Okay. Whatever trick I give, they'll be like, ma'am. Some new language if I write and give also, you people will think, oh wow, Gopika ma'am found a language. Cryopreservation. Okay, cryopreservation. Clear to all of you? Minus 196 degree at liquid nitrogen. Clear to all of you? Done. Okay. Now going to the next topic, pollination. Okay, now gametes are formed. We understood the validity of the gametes. Now we have to think of an option how we can do exchange of this gametes. What is the point of doing microsporogenesis and megasporogenesis and sitting and thinking that, okay, what am I going to do with these people? No, we have to call people to do the exchange of them. So now if pollination is going to happen self, that is like same stigma, same anther. Okay, one flower has stigma and anther, exchange has happened, it is self-pollination. Different stigma, different anther, like this pollination has happened, cross-pollination. But one different one is there, gaetogamy. We will go into that. So students, transfer of pollen from anther to stigma is called as pollination. Pollination is of two types. You have been studying from 7th standard EVS. Okay, that is going to be no, क्यों नहीं आती? Okay, yes, self pollination and cross pollination. Okay, self pollination, students, two types are there, autogamy and gaetogamy. Cross pollination is xenogamy. Auto means what? In your phone also, if you set an auto mode, it will continue, it will make you fair. Okay, it will make you look like Aishwarya Rai. Brightness will be increased, contrast will be increased, right? So that is auto mode. That means everything is set by the phone itself. Okay, everything is set by the phone itself. So that is autogamy, and then we have gaetogamy. Gaetogamy, is what, students? This is autogamy. That means same stigma, same flower, same anther, exchange is happening. Geitonogamy is different flowers of the same plant. You understood? Different flowers of the same plant. Imagine same family but different brother, sister, like that. Okay, like that one pollination is going to happen. That is when you get married inside the family itself. Okay, mama punna, mama payyan, you get married. No, same family only. Just that he's mama punna and he's mama payyan. Okay, he's not born to your parents or anything. He's born to your parents' brother, sister, or someone like that. Okay. So that is exactly geitonogamy. Understood? So here in geitonogamy also you cannot expect that, okay, you know, same family you married, you cannot expect Shah Rukh Khan genes there. You can expect your own family genes. No, same way here also, students. Variation is going to be there, but not to an extent of a cross-pollination. Any genetic disorder, anything that runs in the bloodline, anything that runs inside the family is going to be carried forward to the kids. Okay? Yes? Clear to all of you? Yes or no? So, different flowers but same plant. Okay? Different flowers but same plant. Okay? Yes. Now look here, autogamy and geitonogamy is done. Genetic variation will not be anywhere close. Okay, genetic variation will not be anywhere close. Okay, yes, very good. Okay, okay, very good, very good. Okay. Going to cross-pollination, you know, no, different stigma, different anther. Okay, so from this stigma, I have taken the pollen, from this anther, I have taken the pollen grains, added to this stigma. These two people are not related by any ways. Okay, now, autogamy, students, under autogamy, you have again chasmogamous flower and clistogamous flower. Now, here, what can be the question? They can directly ask you about the flower. They can ask you statement-based question here, okay? Statement based question here, very important. So please make a note of this. Okay, please make a note of this. Okay, clear to all of you? Clistogamous flowers means they do not open, students. They are going to do autogamy. They do not open. Then what can they expect, right? Autogamy only will happen. They're like, I don't want to talk to you. I don't want to talk to you. I don't want to talk to you. I don't want to be compatible with you. I am happy with my own self. Okay. So they will not open. So here what is going to happen? Only autogamy will happen. Anther is there. Stigma is there. So autogamy will happen. Inbreeding depression is pakka. If you sit in a closed room for a very, very long time, what is going to happen to you? You will go into depression. That's why you should talk to other people. So even the plants also, students, not only you have depression, plants also have depression. That is inbreeding depression. Now look here, chasmogamous flowers. They open. They have exposed stigma and anthers. Now, these people can do both. Cross-pollination, geitonogamy, autogamy also they are capable of doing. But on one plant itself, there will be chasmogamous flower and clistogamous flowers. Okay, these flowers will look something like this. There's a diagram given in your NCERT, you can check. Now students, example, you will remember COVID. Okay, COVID's co you will remember. Okay, co you will remember. Commonilla, oxalis and voila. Okay, Commonilla, oxalis and voila. Now, I told you that just by making the male gametes, you cannot just sit and think, okay, like this, oh, what to do. We have to call agents, okay. Now, when two marriages have to happen also, they call agents, or they call them what? Brokers, or they put their profile in the matrimony, like that only. Here, the agents are going to be biotic or abiotic. That means living or the other way around, okay. Now, biotic can be insects, humans, that means imagine, now, mainly we cannot do it because we are not taking the pollen grains and going. But if it is to spread the seed, we also are responsible for it. But here, biotic, you are going to study insect. Okay, entomophilites, insects. Abiotic, you have wind and water. That means wind can take the pollen grains and go, or water can take the pollen grains and go. Or main thing, insect, we give it. The flowers give nectar and pollen as a reward to them. Right, all of you remember the reward system. So, this is given as the reward system. Biotic is insect, abiotic is wind and water. Clear to all of you? Now, students, here, what you have to study is, you have to study the characteristics. Okay, don't study now. Just revise it before the exam. Okay, because you will not remember it for a long time. Now, you only chumma think and imagine insect. Okay, you think you are an insect. Okay, let's take Chintu, Meghana, all of you are insects. Now, if you are an insect and you see a flower which is not at all colorful, does not have any nectar, okay, chumma sitting like this, will you like the flower? You will not like the flower. You will expect the flower to be colorful, having lot of nectar, and these two things have to be given to you. At the same time, the pollen grain will have to stick to you. That means, let's say you're a honeybee and you're going, and you will notice that, oh my god, such a beautiful colorful flower. So, the characteristics of insect pollinated flowers has to be, they should have large colorful petals. This is where essential, non-essential parts come into place. Corolla, petals are going to do the main job. Okay, now let's just imagine about wind. Do you think wind really cares? That okay, let's take another example. Okay, Niharika is there. Okay, and Bunty is there. Okay, Niharika and Bunty is there. Yes. Anemophily and hydrophily also is there, entomophily also is there. Okay, now students, do you really think Niharika will be bothered? Niharika is the wind. She will not be bothered if the flower is beautiful or not. She will only be bothered if they have an exposed stigma, exposed anther. That means wind should be able to take and go. At the same time, the pollen grain should not be sticky, it should be lightweight. All are these of the conditions that a wind pollinated flowers have. Water pollinated flowers usually, even though they can go through water pollination, they will not go through water pollination. They will wait for wind or insect pollination, like your water hyacinth or vallisneria. They'll be like, you know what, this water here, when will this gamete go reach? And there are chances that the gamete sink. There are chances that some other organism consume it. All these can happen. So in water pollination, what happens, students? The pollen grains will be coated with a mucilaginous sheath so that it does not soak the water. Clear to all of you? These are the general things. Okay, these are the general things that you have to do. Now, I told you that if you sit in a closed room for a very long time, you're going to have depression anyways, right? Now, plants also, because of continuous autogamy, continuous self-pollination, because there's no variation, they will go through something called as inbreeding depression. To avoid inbreeding depression, you have to do outbreeding devices. You have to use some outbreeding devices. You don't have to do anything. Plant will do it by itself, okay? Look here, students, if the self-pollination continues, it will lead to inbreeding depression. To avoid inbreeding depression, there are some outbreeding devices which are used by the plants to avoid self-pollination from happening. Okay? Yes or no? Now look here. Change the position of the anther and the stigma. So let's take example, students. At the first, anther was on the top, so the pollen grains could land on the stigma very easily. Now, don't you think self-pollination will happen? All of you tell me yes or no in the chat box. Come on, quickly. Quickly. Yes, prevent from wetting. Very good. Collaborates us with honeybee. Students, if you are in my class, I'm going to, make you any kind of animal that I'm talking about, okay? That is what zoology class is all about, right? I make you the example, okay? Yes, come on. Yes, that is, students, here what is going to happen if the anther is above. Understand, all of this have different terminologies which you don't have to study. Okay, you don't have to study these terminologies. You only stick to the conditions. Okay, now here what is going to happen, the anther is going to fall on the stigma. So what will the plant do? It will change the position of the anther, making the anther short. Now it has to go against the gravity, which will not be possible. So that is the first thing that they have done. Okay, second thing, unisexual flowers. They are like, okay, why to even take tension? I will only make a flower which is pistillate, or I'll only make a flower which is staminate. That means only stamens are there, or only carpels are there, or only pistils are there, right? Stigma style ovary, together you call it pistil, or you call it carpel. So together I'll only make the female part, or I'll only make the male part. So then problem is sorted. Correct. Next thing what they do, different time of maturation of stigma and anther. That means if both of them mature at the same time, only compactability will happen. If one is going to mature late, another is going to mature fast. That means receptivity is different. Then no problem at all. No, they'll not go for post-fertilization events. Simple as that. So this is the third thing that they'll do. Last thing is self-incompatibility. I told you that whenever you're going for a marriage also, the first thing is compatibility. If the boy and girl are compatible. Same way here also, stigma will decide if the pollen grain is compatible for me or not. If the pollen grains are not compatible, the stigma will not allow pollen tube germination to happen. Clear to all of you? They have a chemical that will help in pollen tube germination, which will stimulate. Okay, like how a catalyst work, no? They will do that. But in case there is no, okay, like stigma is like, hey, I don't like this fellow. Okay, then there is no compatibility going to happen. So what we do, plants sometimes do self-incompatibility. That means if the pollen grains are fallen from the same plant, they will tell A, I reject you. Okay, A, I reject you. Yes. So this is the 4 steps that is taken up by a plant for doing outbreeding devices. Okay. Now students, we can also do artificial hybridization. Okay. Now let's take an example that Harshine. Okay, Harshine. Hey, this is so connected to marriage. What to do then? As if I am interested, you're telling. This is so much connected, easy. Because you people will understand more easy if I talk about marriage, if I talk about, things that are relatable, right? Serial story, if I tell, my students are like, oh, Hyperactive. Okay, if I tell students this is the word, you people will sleep off. Okay, so what you are interested in, I'm saying. Now look here, artificial hybridization, students. That is, let's take example. Gopika, okay, there's one Gopika in the chat box. Okay, Gopika wants to get a very different kind of a flower, or she wants to increase the yield, or she wants to make sure that unnecessary pollen grains does not fall. She can do artificial hybridization. Now what is artificial hybridization? It happens in two main steps. Okay, emasculation and bagging. Now what is emasculation, students? With the help of a forceps, let's say Gopika Shri is removing the anther. She's carefully removing the anther, and that step is exactly called as emasculation. Okay, exactly called as emasculation. That is, desired pollen will be allowed to land on the stigma because we already removed the anther from it. There's no way that the pollen grains will fall. Then what we will do, she will be like, okay, what if another pollen come and falls on this? So what I will do, with the use of a butter paper or a plastic paper, I will cover this stigma and I will tie it. That process is called bagging. Now after that, she wants her own variety. No, so what she will do, she'll dust the pollen grains on the stigma and then she will do rebagging. So two steps happen, emasculation and bagging. Emasculation is where you remove the anther with the help of a forceps, and then you bag the stigma and keep, so that there is no unwanted pollen grains coming and falling on it. After that, once you add the desired pollen into it, you do rebagging. Okay, clear to all of you? Yes or no? Okay, clear? You people will come and subscribe, no? If I start something like that. You people are interested, just openly accept it. Okay, you people are very interested in serial kind of things. Okay, yes or no? You are very interested. See, he's able to remember breathing and exchange example that I gave. Now if I ask him what is the sliding filament theory part, no one will remember. Okay, stories you people will remember for longer time. Students, you shouldn't make studies boring. The moment you make studies as studies, then it becomes boring. Always, okay, always make it simple. Bagging is nothing dear. So what happens now? I removed the anther. Now I want to protect the stigma. So what I will do, I will take a bag and cover the stigma like this, so that no other unwanted pollen grains will fall or land on it. After I add the desired pollen grains, again I will rebag it. Okay, I will rebag it. Now main, again, storyline 2. Okay, part story 2 is coming, that is double fertilization. So I told you that stigma has accepted the pollen. Okay, stigma is like, okay, I want this doctor fellow only. So he has accepted, or she has accepted the pollen, not he, she. She has accepted the pollen. She has allowed. So compatibility means what, students? First they will have chemical dialogue. They'll talk to each other, no? So they'll have a chemical dialogue. Stigma will then accept the pollen. Then the pollen will start forming pollen tube. The pollen tube is going to grow and go where? The pollen tube has what inside them? They have the vegetative cell and the generative cell, right? That generative cell is going to have the male gamete, which is ready to fuse with the egg. So for that, what we have to do? We have to allow pollen tube germination. Now when the pollen tube germination is happening, please do remember one thing, that 60% of the angiosperm, 60% of the angiosperm is going to dehiscent. Okay, at a two-celled stage. Two-celled stage means what? One generative cell, one vegetative cell. One generative cell's male gamete will go and fuse with the egg. Problem sorted. Okay, problem sorted. Okay, now the rest 40%, again this is an approximate value, it's not like 60-40 exact, we are just doing. Okay, this is given in your NCERT, so remember this number. Rest of the 40% student, they are going to dehiscent at a 3-cell stage. Now when I am saying 3-cell stage, what do I mean? One generative cell will undergo mitotic division and form 2 male gametes. Actual marriage was supposed to happen with the first male gamete and the egg. But then what happened? Generative cell will undergo one more mitotic division when the pollen tube germination is happening, leading to the formation of one more male gamete. So now we have only one bride. We need one more bride. So what we will do? Here is the solution for it. That is, one male gamete will fuse with the egg to form zygote, which is called as syngamy. One more male gamete formed. No, this generative cell, without asking our permission, it formed one more male gamete. Now for that male gamete, there is no bride. No, it's not like that. There is a bride. Who is the bride? One male gamete will fuse with the polar nuclei, which is present in the central cell, to form primary endosperm nucleus or endosperm. Now students, please do understand, this endosperm formation is not like how I'm telling joke, okay, like go one more male gamete, not like that. This endosperm is going to provide the nutrition for the growing zygote. Clear? For the growing zygote. So, double fertilization students, it's syngamy plus triple fusion. Syngamy is what? Normal thing. One male gamete, one egg will fuse 2N. Clear? Simple. Okay, diploid will form. Here what will happen? One male gamete from the 2N will form 3N. So, this becomes a triple fusion. Okay, this will become a triple fusion. Clear? Yes? Okay, no problem. Okay, yes, clear to all of you. So this is exactly what is double fertilization. Syngamy plus triple fusion. Syngamy is one male gamete fusing with the egg, and another male gamete shouldn't be left alone. No, for that one male gamete, we will tell the primary, that is the polar nuclei, to fuse, and it will form the primary endosperm nucleus. The fate of the primary endosperm nucleus is to form endosperm. That endosperm will be utilized by the growing zygote. Clear to all of you? Yes or no? Okay. Yes. Clear? Done. Okay, now these two diagrams, students, they can ask you for labeling. So please learn these two diagrams for labeling. What is A? What is B? A is going to be a dicot. Okay, dicot. And B is what? Embryo of a grass. Okay, embryo of a grass. Grass is a monocot, right? So here what you have? Plumule. Plumule will ultimately form the shoot. Okay. Then we have cotyledons. Two cotyledons will be there. Hypocotyl is there. Radicle is there, which will ultimately form the root. And since this root has to go through rough, hard surfaces, there is going to be a root cap for protection. Okay. Please learn this diagram. I have added in the notes so that you learn this diagram before going to the examination. Okay. They can ask you labeling of the scutellum. Scutellum is actually something that will separate the endosperm and the embryo. Like that separation will be proper. Then we have coleoptile, again to protect the shoot. Okay, then epiblast is there. Radicle, root cap, coleorhiza is there. So to protect the radicle, we have coleorhiza. To protect the shoot, we have coleoptile. Okay, coleoptile. Will you remember this? Yes or no? Yes or no? Now look here, students. This is your, okay, dicotyledon. Okay, dicotyledon. Now both the cotyledons are there. And you see an extension. Okay, you see an extension. Now what you have? You will have a radicle and you will have a plumule. That plumule will become the shoot, radicle will become the root. Okay, and then what you will have? One middle one layer will be there, which is the embryonic axis. Okay, embryonic axis, both the side cotyledons are going to be there. Clear to all of you? Now very important PYQ questions are here. Okay, examples, direct examples they will ask you. Nucellus. What was nucellus supposed to do? It was supposed to provide the nourishment for the growing embryo sac. Simple. Remember this. Now, three people we have studied who is giving nourishment. First of all, you have your vegetative cell, who will have all the reserve food materials for the generative cell. Then we have tapetum, who was providing the nourishment for the growing pollen grains. Then we have nucellus, who is going to provide the nourishment for the growing embryo sac. Then we have the endosperm, who is going to give the nourishment for the zygote. Now here all of you look. Nucellus is persistent and the persistent nucellus is called as perisperm. Example is going to be BB house, that is your big boss house. Okay, beet and black pepper is going to be the example. Okay, I have told you this before also. BB house. Okay, big boss house. Okay, nucellus is going to be persistent. That means in big boss house, okay, noise is persistent. How much ever you remove people, how much ever you throw the contestant, even if you give last two contestants, they will also be fighting. So noise is persistent, okay, in a big boss house. So remember like that. Nucellus is persistent, it is called perisperm. Perisperm example is going to be beet and black pepper. Okay, now students, seeds can be albuminous or exalbuminous. Albuminous means they retain some amount of endosperm. Usually endosperm have to be utilized. Right, now my mom also, let's take your mom also example. We bought a birthday cake. We are supposed to finish the cake on the same day by giving it to everyone and eating for ourselves. But what will mom do? She'll cut the pieces and first only she'll keep it in the fridge. Then only she'll allow us to eat the cake. So endosperm is supposed to be utilized. But in some seeds what will happen? They are also little confused like how you people are without liking the video. They will retain some amount of endosperm. Example, cafe coffee day. Okay, cafe coffee day. Even if you haven't gone, you have to study about it. Okay, C for castor, C for coconut. Day is just a happy day. Okay, now exalbuminous students, no endosperm. All the endosperm got utilized. That is us. Okay, that is us. Okay, now no endosperm is going to be there. PUBG you can remember. P for P, B for beans, G for groundnut. Okay, G for groundnut. Clear? Yes or no? Done. Okay, yes, very good. Okay, last. Parthenocarpy, apomixis and polyembryony. This also examples only will come question. They will not ask you, please write the definition, students. They will not. Okay, yes. Okay. Parthenocarpy is fruit without fertilization. Okay, fruit without fertilization. Parthenocarpy. Example, banana. Apomixis, seed without fertilization. Okay, seed without fertilization, that is citrus and mango. Here what is happening, students? The egg is going to be like, you know what, I will only directly do meiosis and I will only form the seed. You don't take my help and all. So egg will undergo, instead of going through the entire process, egg will directly form the seed. Okay, egg will directly form the seed. Polyembryony, students, occurrence of more than one embryo. Here what is going to happen? Remember the nucleus cell, one of the cell told that I will become the megasperm mother cell. But after some time, some of the nucleus will start getting little jealous. Okay, there's so many nucleus will start coming in and they will form multiple embryos. So that is called as polyembryony. Okay, citrus fruits like orange, you would have seen in orange, no? Many embryos will be there. Okay, clear to all of you? Yes or no? These examples, can you remember? Okay, now reproductive health will come into the last because we have only 2-3 things to study here. We have art, technology and IUDs to study, from where every year question will come. Okay, we'll come to that last. Okay, now we'll start with molecular basis of inheritance, because if I didn't do this, no, that's all, you people will, people will come home. Parthenogenesis, we tell, formation of new organisms, no? So it can be, if you generally see parthenocarpy and parthenogenesis, the first difference they say is one is in animal, one is in plants. But here we are talking about plants, so we tell separately. Okay, separately. Yes, ready for molecular basis of inheritance, your most traumatizing chapter. Okay, if there was a chapter that was given award for making my students traumatize, okay, this chapter it will be. How many ever times I teach them, no use. They will still tell, ma'am, we can't understand, ma'am. That's because you haven't studied. Okay, don't think that, oh, ma'am, if as if what is that? One person from space comes and teaches this chapter, you will understand. Not like that. You don't understand. Understood? Okay. Yes, enough of scolding for the day. Okay, I'm happy. Now we will continue. Okay. If you understand the chapter is easy, you should understand, no? Okay? Thank you. Easy chapter. Okay, we'll see. Okay. Come on, let's start. Molecular basis of inheritance. Okay, we will start with the first introduction itself. What is that? They will ask you a question that who was the person who gave the word nuclein? Okay, who was the person who gave nuclein? So here, first itself, you start with a person's name called Friedrich Mischer. He was the person who worked on white pus cells, which you don't need to know. But he was the person who called that there is something that has this, that holds all the genetic information of a cell that allows inheritance to happen. That is why some people tell that, some of you look like your mother, some of you resemble like your father. How are they so sure about it? It is because this one thing holds all the genetic information of your parents and it comes to us. Okay, now look here, students. Friedrich Mischer gave the word nuclein, but Altman was not happy. Okay, Altman was like, halt. Altman was like, halt a minute. Nuclein has some acidic properties, so we need to call it nucleic acid. Okay, today my humor sense is coming above. Okay, maybe because of lack of sleep, students. Okay, nucleic acid. Clear? So nuclein, okay, was found by who? Friedrich Mischer. And then Altman came and he told, wait, give a halt. Okay, there is some acidic property in this nuclein, so let's call it nucleic acid. And that is when, okay, that is when we came to know that there are some people who can hold all the genetic information of a cell and pass it on, pass the paternal, maternal, information to the, to the younger ones by the help of genetic materials, that is RNA and DNA. So the two nucleic acids that you're going to study is going to be RNA and DNA. Unfortunately, students, the RNA structure, what is the full form? Ribonucleic acid. RNA structure, the second group, there is one O extra. Okay, when ribonucleic acid was doing some busy job, one O came running. It was running and came and it joined. Now what has happened? Because of that OH group in the second carbon, ribonucleic acid is not stable. Okay, just imagine, students, someone runs and comes into your life, okay, and you're not no more stable, okay. So same thing happened here. This ribonucleic acid is not stable. It is not chemically, structurally stable, because of which RNA is not considered the genetic material for all the organisms. There are organisms where RNA is the genetic material, like your TMV viruses, okay, HIV, TMV viruses. But majority of the organisms will have DNA as the genetic material, which is deoxyribonucleic acid. Okay, clear to all of you? Yes or no? Deoxyribonucleic acid, in the second position, there is only one H group, which leads to the stability of this fellow. Clear? Stability of this fellow. Now, what are this nucleic acid made up of? Right, made up of what? You study, cell, tissue, organ, like that. Here, this nucleic acid composition, when you're trying to study, there's something that they're made up of. That is going to be what? Sugar, phosphate group, sugar and nitrogenous base. Okay, so SPN is what is going to be there. Phosphate group, sugar and nitrogenous base. Two types of sugars are there, students. What are the two types of sugar? Ribose sugar, okay, which is present in RNA, and deoxyribose sugar. Deoxyribose sugar. What will be the difference? Tell me quickly. Okay, what will be the difference other than that it is present in RNA and DNA? Give me the major difference. Come on. Yes. See? That's why I tell stories, okay? Aditya is able to remember what I told last year. Imagine. Last year what I taught. He's able to remember because of stories. Okay, stories are very important in life, students. Okay, no masala, no memory. Come on. Yes, I told you, people, don't give me that. Tell me what is the difference here. Now, nitrogenous base, students. Nitrogenous base also, we have two types of nitrogenous base. Purines, okay, and pyrimidines. Purines and pyrimidines, okay. Done. Now, phosphate is the simple fellow, okay. Yes, very good. Presence of, this one has the presence of OH group in the second carbon. This fellow has an absence of that O group in the second carbon. This is the main difference between these two people, making them chemically and structurally stable and unstable. Now, look here, students, if you have to study more, you have to study more about nitrogenous bases. You already know that purines and pyrimidines are there, but that information is not enough. You have to study a little more for NEET level. See, purine, students, they are a 9-membered ring. That means what? Name small, but actions are bigger. Think like this, okay? They tell in Kannada something I forgot. Name small, actions are bigger. That means purine, 9-membered ring. Pyrimidine, 6-membered ring, okay? So, this 9-membered ring, students, they have in the first, third, 7th and 9th position, they have nitrogen groups, okay? What do I mean? In the first, third, 7th and the 9th position, they are going to have a nitrogen group. Question can come. Now here, pyrimidines, big name, Kutti ring, okay? 6-membered ring, 1 and 3rd carbon, there is a nitrogen group. You all know odd numbers and even numbers, no? 1, 3, 7, 9. Can you remember? 1 and 3, can you remember? Yes, ma'am, I can remember, okay? Yes. So, 1, 3, 7, 9 and 1, 3 nitrogen groups are present. Now, who are purines, who are pyrimidines? Purines, you're going to remember pure as gold. P for purines, A for adenine, G for guanine. Done. Okay, now pyrimidine, ma'am, if gold is there, you have to cut the gold, you have to sell the gold. That is what you're thinking at. So, purine is pure as gold means pyrimidine is going to be cut. Okay, cut. So, CUT, C for cytosine, U for uracil, T for thymine. Now, question will come. One more question which I saw in KCT, I was shocked that, okay, NEET students doesn't have this question. So, students, I don't know if it has asked in some 2004, 5 and all, but see, C for cytosine, U for uracil and T for thymine. Do you know what is the other what is that? You know, thymine. Okay, what is the formula? It is going to be 5-methyl uracil. Did you know this? That if you put on the 5' one methyl group, CH3 group, you will get thymine. So, question has been asked that what is the one thing that is present only in DNA is the question. What is the one thing that is only present in DNA? And they hadn't given option thymine. Many students wrote adenine, guanine and all of that, but they are present both in DNA and RNA. The only thing that is going to be present in DNA is going to be thymine. So, the other formula or the other way to write thymine is 5-methyl uracil. Okay? Yes, I think all of you know, no? Very good. 5-methyl uracil. Now, if in case this year, let's hope this question comes. Okay, fingers crossed. All my NEET English students will be able to answer. Now, okay, here, look here, students. Now, there is something called as Chargaff rule. So, Erwin Chargaff came and told that, you know what, ratio of purines and ratio of pyrimidines have to be equal no matter what. That is, if I am trying to do a dance in the class, there are 5 boys and 5 girls. It's easy to pair them. Yes, ma'am, it's easy to pair them. Imagine there are 6 girls and 4 boys. Not easy to pair them. 2 girls will be left alone. So, here what we have to do, we have to make sure that when bonding is happening, these 2 people have to be in same numbers, right? Adenine has to bind with thymine. Okay, guanine has to bind with cytosine. They both have to be in same numbers, correct? So how will you remember that? At Gopika ma'am's class, okay? At Gopika ma'am's class. ATGC. At Gopika ma'am, Guru Dakshina should be inside, okay? At Gopika's class, okay? So A will always bind with T, G will always bind with C, adenine will bind with thymine with 2 hydrogen bonds, guanine will bind with cytosine with 3 hydrogen bonds. Again, mini satellite, micro satellite regions I have taught you before. So there you know there are adenine rich regions and guanine and cytosine rich regions, right? That and all. Now let's not think about it. We are doing revision, so we cannot go into the depth of all that. Now bonding, okay, bonding, right? Very good. Bonding, students, very easy, very simple, don't need to break your head. So now we understood that many nucleotides. What is a nucleotide made up of? Sugar, phosphate and nitrogenous base. Many sugars combine together to form your polynucleotide chain. That polynucleotide chain itself forms your nucleic acid. But how do they bond with each other? Sugar is one side, phosphate is one side, nitrogenous base is one side. It will not bond. So there are 2 bondings mainly which is happening inside them. So that we will learn first, okay? Yes. Now look here, students, nitrogenous base plus sugar. I have told you this example, nucleoside. Okay, nucleoside means you're pushing one person to the side. Whom are you pushing to the side? All of you answer me quickly. Who are you pushing to the side? Yes. I know, Shimon sir tells that. Faster. Students, if you guys want to meet us after exam, okay, chill pill session you want to do in Chennai, Hyderabad, please let us know in the comments, okay, where do you people stay so that we can come there. Not to your home, students, like if there is a VLC center nearby, we'll come there, okay. Excellent. Whom are you going to push to the side? You're going to push phosphate to the side. So that is called as nucleoside. And very important topic is the suffix, okay. Ine will be added. That is adenosine, okay. Adenosine. That means what? Ine is added. That means it is a nucleoside. There is no phosphate in that. Now, nitrogenous base plus sugar plus phosphate, you already know it is called a nucleotide. But let's say Pradeep is telling, no ma'am, I do not want to write nucleotide. I want to write nucleoside monophosphate. Now, can I say Pradeep is wrong? I cannot say Pradeep is wrong because it is exactly the same. If one phosphate is added to a nucleoside, I can call it nucleoside monophosphate. Simple, no? If 3 phosphates are added, I will say nucleoside triphosphate. So that is the same thing, okay? Nucleotide or nucleotide triphosphate, okay? Chacho. Now, look here, students, the bonding, very important, okay, bonding. Look here, this is a sugar, you know, this is a deoxyribose sugar. Now, how do I connect the sugar to a nitrogenous base? A sugar and a nitrogenous base is always going to connect with an N-glycosidic linkage. N-glycosidic linkage. If the sugar is binding with a pyrimidine, it is going to be 1-9, okay, 1,9 glycosidic linkage, okay. You don't have to know the bonding exactly, but you have to know N-glycosidic linkage will be formed. Clear to all of you, yes or no? Now, look here, students. There is a sugar. Now, this sugar is going to combine with phosphate. If a sugar has to combine with phosphate, they have to form a bond between each other, which is going to be a phosphoester bond. What is the bond going to be? A phosphoester bond. So, 2 bonds are there. First bond is going to be between whom and who? Sugar, nitrogenous base, N-glycosidic linkage. Sugar, phosphate group, phosphoester linkage. Now, we all become one. We all became one. Now, one nucleotide has to combine with another nucleotide. They will form a phosphodiester linkage. What will they form? Phosphodiester linkage. Now, students, remember one more thing. On here, this here, phi dash phosphate is free. So, we call this as the phi dash end. Okay, we call the phi dash n. On the phi, okay, if the phosphate is free, because if this phosphate is free, we can do a one more bonding. Okay, now on this side, you notice that 3OH is free. Okay, 3OH is free. So we will call this the 3 dash n. That is how you write the polarity. Phi dash n to 3 dash n, 3 dash n to phi dash n. If you want a detail of this, you can watch it in Bio Club. Otherwise, this is the general understanding of it. Clear to all of you? Yes or no? So, if one nucleotide has to combine with another nucleotide, they are going to bond with a phosphodiester linkage. Diester. Okay, many students have doubt, ma'am, when will di come? When will phosphoester come? Phosphoester linkage is going to happen when one phosphate is combined with the sugar. I am the sugar. Okay, now I am a nucleotide, I want to combine with one more nucleotide, then we will use a phosphodiester linkage. Clear to all of you? Yes or no? Clear? Now, salient features of DNA. Very simple, students. What are the salient features? The backbone of DNA is made up of... DNA is a double helical structure, and who are the first people to find it out? There were 4 people, okay? Wilkins, Franklin, Watson, Crick. In that, Wilkins and Franklin were the first people to do X-ray diffraction to understand what was the structure of DNA. Later, Watson and Crick also came into it, and they 4 are the people who came up and told that, you know what, our DNA is a double helical structure. Done, done, done? Yes? Yes? Fine, no? Think. Okay? Okay. It's raining here, students, so like that lag and all will come. Okay, now this month and all, it was fine. Okay? Yes. Yeah, it's fine now. So, try to understand what I was trying to say. So, double helical structure, okay? Sugar, phosphate, this is going to be the base that is going to come inwards, okay? So, adenine will bind with 2 hydrogen bonds. So, they will come together like this and they're going to make the double helical structure. Now, who came and told that, yes, this is the double helical structure? Watson, Crick, Wilkins and Rosalind. Okay, Rosalind Franklin. In this, 3 people got the prize. Other Rosalind Franklin did not get, okay? That is the recognition. Okay, now adenine will bind with thymine with 2 hydrogen bonds, guanine will bind with cytosine with 3 hydrogen bonds, anti-parallel polarity. I told you. On the phi dash n, who should be there? Phi dash n, who should be there? Come on, tell me quickly in the chat box. Oh, you're getting 720. Then you might not get in GMC. Okay, because you know, 720 is like 2 less. So maybe you should try in IIT, try somewhere there. You might get pakka. Okay. Okay, done. Got it? Yeah, okay, done. Now, X-ray diffraction, you can confirm the structure. Students, one turn will have 10 base pair. Pitch of the helix is going to be 3.4 nanometer. Approximate length of the DNA is going to be 2.2 nanometer. Okay? Yes? Correct? Okay, very good. Okay? Yes. Now, how do you do packaging of DNA? Okay? How do we do packaging of DNA? Correct? Yes, exactly. Okay. So now look here, students. This is your entire 2.2 meters of DNA. You have to place it inside a Kuti nucleus. What will you do? You will take the help of histone proteins. Histone proteins are positive proteins. DNA is negatively charged. So it is easy to wind around it, right? So histone proteins are not going to come as a single person. Histone proteins are going to be how many, students? They are going to make an histone octamer. Okay. They are going to make an histone octamer. That is H2A, H2B, H3, H4. These, all the 4 people will become double and they will form an entire histone octamer, and that histone octamer is going to wound the DNA around them, and there is going to be one more protein. What is that one more protein? It is going to be H1 protein or the linker protein, which are going to keep everything in place. Can you see here? This is the linker protein. Clear to all of you? Yes or no? Okay, perfect. Yes, excellent. So H1 protein is the linker protein who is going to link all of them. Now students, what will you call DNA plus histone octamer together as? Quickly in the chat box. What will you call DNA plus histone octamer together as? Come on. Faster, 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 faster. No time, no time. Okay, so here one more question that can come for all of you, the amino acids. Okay, you know proteins are made up of amino acids. The basic amino acids which are going to be lysine and arginine. Okay, lysine and arginine. Yes, excellent, Dr. Cubicle. Okay, so sure, histone octamer from with the DNA together, you call it nucleosome. One nucleosome will have 200 base pairs. Again, a question that can come. One nucleosome will have 200 base pairs. And students, if you are seeing this nucleosome under the microscope, it will look like a bead on a string structure. Now you will have a question, ma'am, how do they ultimately form the chromosomes, right? Look here, students, like this, many nucleosomes will condense together. They will form the chromatin fibers. That chromatin fibers will condense to form your chromosomes. Clear to all of you? Now, we take the help of additional set of proteins which are called as non-histone chromosomal protein. That is, we need to take additional set of help. Let's take an example that I'm shifting my house. Okay, when I'm shifting my house, I will not be able to carry the almara, the fridge and go, because I'm not that Aditya Birla's that ad person. No, I cannot take and go. So I will take additional help from packers and movers, telling that please come, and we have to take help from them. Like that only. Here, non-histone chromosomal proteins are going to be additional set of proteins which we are going to use especially in eukaryotic organism for higher coiling. Done, done, done. Okay. Yes. Clear to all of you? Clear to all of you? Okay. Okay. Now you will lack marks in the molecular basis of inheritance. Okay, talking to each other. Then you will lack everything in your life. Now study here. Okay, 40 marks chapter this is. Now, Griffith's experiment. Ready all of you? So Griffith experiment, we will only stick to the important points. Question point of view, what will come? Because I have taught you this chapter 100 times and I have taught you Griffith experiment more than that. Okay, Griffith only will be tired. How many times this lady will teach me anta? Okay, so Griffith experiment, students, 1928, he was doing bacterial transformation. So when I taught you biological classification, I told you bacteria can do transformation. That means what? If there is a DNA which is walking around like a ghost, okay, no one to catch, no one to, no protein code, nothing is there, then immediately the bacteria will pick it up, or from the surface itself they will pick it up. So same thing has happened here. What has happened? Griffith was working on an experiment with Streptococcus pneumoniae, which causes pneumonia, or Haemophilus influenzae, both you have studied. Here he is using Streptococcus pneumoniae, which has two strains, S strain and R strain. S strain is smooth strain, that means this will have a proper mucopolysaccharide coating, and people believe that that mucopolysaccharide could have been the reason for them to be virulent. Okay, so this has become virulent, and there is a rough strain that is non-virulent, that means it does not cause any disease. So what he was doing, he first injected the S strain, obviously the mice died. Anyone has doubt in this? Okay, then he injected the R strain, the mice was alive. Okay, the mice was alive. Then what did he do? He was like, okay, let me do one more experiment. I am going to heat kill. Okay, I am going to heat kill the S strain and I am going to inject it into the mice. What you would have expected, students? The mice lived. Okay, the mice lives. Now he was thinking that, okay, let me take both the positive results. Okay, let me take this and let me take this together combination. Let me make a combination out of this and I will use it on the mice and see what is going to happen to the mice. Okay, so what is going to happen? He used heat killed S strain and he used live R strain and the mice died. Now if you were Griffith, you tell me, won't you be shocked? Yes, if I was Griffith, I would be shocked. I'll be thinking what happened, what went wrong. Okay, same way Griffith also was confused, but later he was smart enough that he did not know exactly what happened. So to be on the safer side, he was like, I am going to call this the transforming principle. What exactly happened? The DNA which was lying around was picked up by the R strain and R strain became virulent. Clear to all of you? Yes or no? So here what happened, students? He called that the transforming principle and he stopped the experiment right then and there. Then came Avery, McLeod and McCarthy. Their experiment was not a hit. Why? Because the experiment did not have a clear conclusion and many people were not agreeing to the fact that, you know, DNA is the genetic material. Clear to all of you? Yes or no? Okay. Pakka understood? Okay. Now, who gave the confirmation? Who gave the confirmation that DNA is the genetic material? That was Hershey and Chase. Hershey and Chase used bacteriophage. What is bacteriophage? A virus that infects bacteria. Clear? Again, this is the step that happens in transduction. So, bacteria can do sexual reproduction by conjugation, transformation, transduction. In transduction, what happens? We use a bacteriophage, we use a virus and we bring that virus, okay, to take the genetic material and insert it into the cell. Same thing here they did, students. They used a bacteriophage virus that infects bacteria with radioactive label. Now, let's take example. Okay, let's take example. I've told this example before also. There is, Madhumati and there is Meghana. These two students are there. Now, Madhumati and Meghana are not really friends, okay? They go to a shopping mall and both of them like this one white kurti, okay? So, Madhumati also wants it. Meghana also wants it, but there is only one piece. Now, what will Madhumati do? She'll take the kajal from her eyes and she'll put a dot on that. That is called as what? Labeling. Now, when she comes back, okay, and she will, what is she going to do? She's going to show Meghana. She'll be like, see, this has a black dot here. I think this is a very bad idea. Let's just give this cloth here only and go. And Madhumati will later go and buy the same cloth, okay? Sorry, Madhumati. So, what is happening, students? Madhumati has labeled it. Now that black dot indicates that Madhumati has labeled it. Now Meghana also got an idea. Meghana has gone and she has put a lipstick mark. Okay, she has taken a bit of a lipstick and put a pink dot on it. Now you are able to differentiate exactly. So how are you going to be able to differentiate? Madhumita does not put lipstick and Meghana does not put kajal. So this way you will be able to differentiate who made the label. Exactly, that is what is happening here. That is radioactive sulfur, which is not present in DNA. So, if radioactive sulfur is there, you will confirm that it is the protein. And if there is radioactive phosphorus, which is only present in DNA, not present in protein, you will be able to confirm that DNA is the only genetic material. Yes or no? Yes or no? Okay? Yes or no? Come on, tell me. Yes. Someone is like, at least buy the dress. Okay, they'll buy, students. Yes, tell me. Clear to all of you? So, why did I tell that example? I just told that example to make you understand that what differentiates Meghana and Madhumati. Okay, same way here also. Sulfur, which is only present in protein, is not present in DNA. So, if you see sulfur 35, you have to conclude that that is a protein. And if you see phosphorus, you have to conclude that that is only present in DNA, it is not present in protein. Clear to all of you? Okay? Yes, boys will not understand, doesn't matter. Girls have understood, let's go forward. Okay? Yes. So, after the infection of the bacteria, students, only radioactive DNA entered the bacterial cell, not the protein. How did I confirm that? Because I noticed that P32 was seen inside the cell. P32 was seen inside the cell. What I did not notice, I noticed that S35 was seen in the supernatant. Okay, it was seen in the supernatant. Now tell me the 3 steps that are involved in this process. Quickly in the chat box. The 3 steps are going to be infection. That means the bacteriophage is going to infect the E. coli. Second step is blending. That means to remove the protein coat. Third thing is centrifugation. By centrifugation, the heavier particle is going to settle down and the lighter particle is going to be in the top. Clear? Yes? Okay? Perfect. Perfect. Okay, done. Hershey and Chase experiment is clear. Now we will learn about the machinery. Don't faint looking at this. It is very simple. Okay? Come on. Yes, let's put some fire emojis in the chat box. Energy is coming low. I need some energy. Faster. Okay. Yeah, don't be sad. It's okay. Chill. Okay. They understood. Girls understood the example. Okay. Done. Pakka. Replication fork. Okay. You're getting excited like we are going to eat some noodles with fork. Okay, why you people so excited about replication fork? Okay, come on. Let's learn this DNA replication. Okay, now. Yeah, water break. Take. Fast. So before that, friends, I hope all of you know your DNA replicates in a semi-conservative manner. Okay, DNA replicates in a semi-conservative manner. Semi-conservative means what? You are going to get hybrid DNA, right? You are going to get hybrid DNA. Example, this is the parent DNA. Okay, this is the parent DNA. Now, usually what we will do, we will give the parent copy for xeroxing. Okay, I have given the siblings example also like this. Okay, siblings example also like this. So, this parent DNA is going to act as a template. So, both the parents, one strand is going to be separated, another strand is going to be separated. This separating process is what you are studying in replication fork. Okay, that the whole process, machinery. So, this is a parent. This is a parent strand. Okay, both are template strand. Now both the template strand are going to help us form the new daughter DNAs. Okay, but instead of going back, instead of the parent strands going back, what is going to happen? They are going to ultimately combine to form the hybrid. Okay, they are going to combine to form the hybrid. So this is called as semi-conservative, where you have one parent strand, one daughter strand, one parent strand, one daughter strand, leading to hybrid formation, which was proved by Michelson and Stahl. Okay, hybrid, which is proved by Michelson and Stahl in N14, N15 medium. Okay, done. Okay, perfect. Okay, now look here. Yes. Good. Okay. Yes, now this is done. Now we will learn the machinery. Now how do I separate both the strands? Okay, how do I separate both the strands? First of all, I need to bring someone who can unzip. Both my strands are like this. I need to start unzipping. So I will bring an unzipping enzyme. What is that enzyme, students, in the chat box? Come on. Yes. Come on, quickly. Unzipping will happen with the help of helicase enzyme or an unzipping enzymes, right? Helicase enzyme. Now I did unzipping. So helicase cannot unzip the entire 2.2 meter of DNA. So what it is going to do? It unzipped here. Now it will unzip here. Like this, it is going to continue. So that is how you end up getting a replication fork. This structure that you got is a replication fork. Now, if replication has to happen, they should have an ORI site or an origin of replication site, which is an this mic, students. Okay, ORI site. Without an ORI site, you cannot do origin of you cannot do replication, which again you studied in vector biotechnology. Okay, very good. Helicase. Now students, helicase has started moving and they started unzipping. Now it formed the replication fork. Now what is the second step that I have to think about? I finished separating. Now I have to think about using the template strand, using the parent strand, how I am going to make the new template. Simple. I have to make the daughter strands. For that, I have to bring whom? I have to bring DNA polymerase. DNA dependent DNA polymerase will come. But he has some conditions. The condition is that he is going to do polymerization from 5' to 3'N. That means he is going to form 5' to 3'. Okay, polymerization is going to happen 5' to 3'. That means we have to work on a strand which is 3' to 5'. Okay, this is the first condition he told. Second condition is he is like, I will only work on a single strand. Single strand is not a problem for us. Why? Because we have already separated both the strands. Now look here carefully, students, what is going to happen. To do the entire template, to add on the template, okay, to add the template, we need to bring DNA polymerase. But DNA polymerase has a problem. Actually, to be technically talking about it, we need that 3OH group. Okay, we need that OH group to form the entire, for the template formation to happen. That is not there with us. So I cannot take a DNA strand. Like imagine I'm like to lead DNA polymerase, I'm taking a DNA molecule. After some time, these two DNAs will come together. I cannot take it. So I am going to take an RNA primer. You understand me? I'm going to take an RNA primer, and that primer will be like, hey bro, it's okay. This fellow is blind. I am going to lead you. You come. So primer will be added on the starting, and then the DNA polymerase will continue to form the strand. Clear to all of you? Yes or no? Yes, very good. So primer is going to do the job of leading or showing the pathway for the DNA polymerase. Why? Because we don't have that extra OH group to start the template formation. That is the technicality of it. Okay, if it's too difficult, you can remember simple way. So we will add primers. Why are we adding an RNA primer, not a DNA primer? Because if I add a DNA primer, DNA will get attached to the template. Then I will not be able to do proper transcription, translation, or the entire central dogma will be disturbed. So to avoid that, I am going to give a RNA primer. Okay, because RNA primer I will be able to differentiate. Now DNA started forming a continuous strand, that is from 5' to 3'. Can you see the arrow mark? 5' to 3', continuous leading strand is formed. Now on the other side, okay, on the other side now there is a problem, because this fellow will do polymerization 5' to 3'. Second strand, we cannot do that. We cannot do that. So what we are going to do, we need to take the help of primer again. Primer will be like, okay, let's do one thing. Let's not listen to this fellow. I will start attaching from the reverse. I will start attaching from the back side, and let's make sure that we continue this. Since students, this is going in a opposite direction, we need more energy. So we are going to get fragments. We are not going to get a continuous strand. Okay. So primer will add, DNA polymerase will do the work. Again primer will add, DNA polymerase will do the work. Again primer will add, DNA polymerase will do the work. This will keep continuing, leading to the formation of a discontinuous strands, and these fragments are called as Okazaki fragments. What are these fragments called as? Okazaki fragments. Okay, clear to all of you? Okazaki fragments. And students, the energy form here is dNTP. Okay, energy form here is dNTP. This will be giving us the energy by breaking that phosphate molecule to yield us energy. Done, done? Yes or no? Now, after the work gets over, DNA polymerase will be like, yeah, you know what? Remove that primer. I do not want this primer to be with me. Just throw the primer out. So we will remove all this RNA molecule out, and to join the portions, nucleotides addition will happen with DNA polymerase only, but there will be gaps. To fill or to join those gaps, we will take the help of whom? Ligase. Okay, so we have main hero DNA polymerase, we have sub hero primer, we have a person who is going to join all the portions where this fellow did not act properly or where this fellow did not fill properly. Joining will be done, but please do understand, ligase do not have the ability to add a nucleotide. Ligase will only do the gluing, like a gum. Now, if you tear the paper, will gum produce new paper and give? No, it will just stick the two papers. Clear to all of you? So, ligase, yes, exactly. DNA is very unfaithful to primer. Okay, after the job is done, he's like, throw the primer out. That is why first itself we were intelligent to keep a RNA primer. If we would have kept a DNA primer, they both would have joined together and we wouldn't be able to differentiate them. Okay, so ligase will do the gluing. Is this clear to all of you? Now there are two other enzyme, students, additional information, topoisomerase and SSBP. Topoisomerase will avoid the supercoiling, and SSBP is single stranded binding protein. They will make sure that both the strands are separated because they were together for such a long time. They will have the feeling of coming back together. So to separate them, we will keep SSBP. Clear to all of you? Yes? Yes. Okay. Done. Shall we study transcription? Okay, I have not taken Michelson and Stahl experiment. Okay, Michelson and Stahl experiment I have done beautifully in my molecular basis of inheritance revision. I have made you do numericals as well. So please check out those videos for Michelson and Stahl. Okay, because without doing a numerical, you will not understand Michelson and Stahl experiment, but otherwise the experiment is very simple. You take E. coli, replication will happen in 20 minutes, you start with N15, then you dip it in N14, after that you will start forming hybrid strands. After hybrid strands, starting it will be 100% hybrid, 50% hybrid, 50% light, 75% light, 15% hybrid, like that it will continue. Clear? Yes? Come on. Now students, transcription. Okay, let's take a water break. Okay. I will take one, my throat is paining, students, we will take one Vicks. Vicks is the secret of my energy. Okay, no one is giving money for ad, I am only doing. Yes. Killer, pakka, semi-conservative understood? Semi-conservative understood? This is semi-conservative, parent, daughter, it will lead to hybrid, okay? Michelson and Stahl experiment, what will happen? First we will get 100% hybrid, okay, because we had dipped it in N15 and then put it in N14. Then after 20 minutes the DNA will start, okay, then we will get 50%, okay, 40 minutes, yeah, 50% light, 50% hybrid. Then again students, what will happen? 75%, 25%. 25% hybrid, 75% light. Again what will happen? Around 87.5%, okay, light, and then we'll get around 12.5% hybrid, okay, like that it will continue. Clear? Exactly, full kitch is coming, okay. Okay, transcription. Ready? What is transcription? First of all, tell that, okay, by then this Vicks will melt faster. Transcription, what is transcription? Dinesh, you really think you people making me famous? No, never happening, okay. Yes, very good, okay. DNA to mRNA, okay. DNA to mRNA. So central dogma, we now study DNA, okay, forming its own copy by replication, and the replication is going to be semi-conservative, okay. Now DNA to mRNA, mRNA to protein, okay. So now we are going to do what? This step we are going to take care. That is transcription, okay, transcription. Clear? Done. Okay, now students, transcription, two things you have to remember. 2024 one easy question came. What is the easy question? What is the transcriptional unit? This year don't expect such questions, okay. By mistake they put that question. Transcription unit is going to be promoter, structural gene, terminator. Transcription process is going to be initiation, elongation and termination. Now, do I need to take an entire DNA to make my structural gene? That means to make my mRNA? No ma'am, what are you saying? You take a small region. The small region which is going to form my mRNA is called as the structural gene region. So here if you see, initiation is going to happen. This initiation, what is going to happen students? We have to take okay, now look here. Initiation, what is going to happen? We are going to first of all take one hero here. We need one main character to do the transcription. Yes ma'am. Whom are you going to take? You are going to take a DNA dependent RNA polymerase. Why? Because you are going to read the DNA strands, right? From the DNA strands you have to form an mRNA. So you cannot take RNA dependent RNA polymerase. You have to take DNA dependent RNA polymerase. Clear? So you have taken DNA dependent RNA polymerase, and there is one problem with this RNA polymerase. It is capable of doing all the functions, but it does not know where to start, where to stop. Like my students in the chat box does not know when to talk, when not to talk. Same way, RNA polymerase also does not know. So what we will do, we'll become sigma, we'll start blocking them, right? Not like that. So here what is going to happen students, we are going to give sigma factor to RNA polymerase, telling that you go with this fellow, you combine with this fellow and you start the initiation process. So initiation is going to happen with the help of RNA polymerase combining with sigma factor and starting the initiation. Correct? Okay. Then elongation. This is the actual step students. That is, RNA polymerase has come to study. But what is RNA polymerase doing? Asking about lunch, dinner. Here RNA polymerase is exactly going to do what it is come to do, that is to form the newly formed mRNA. So when the mRNA formation happens, RNA polymerase, the sigma factor will leave. Okay, sigma factor will leave. Okay, then newly formed mRNA is coming. Okay, last step is going to be termination. Termination, what is going to happen? Again, DNA dependent RNA polymerase does not know when to stop. So what we will do? We will tell, ho gaya, bas. Rho factor. So here we are going to give a rho factor combining with RNA polymerase to reach termination. Clear to all of you? Yes or no? Transcription is clear. Isn't it very easy? This is termination. So you started with initiation in the promoter region. Now you have one more thing. Okay, you have one more thing here where you have, I think all of you would have studied this, no? These two strands. Out of these two strands, students, you do not, please understand, in your central dogma, you will not take both the strands of the DNA. You are going to take only one strand, and the strand that you are going to use is going to be a template strand. But for replication, that was not the scenario. Yes or no? For the replication, that was not the scenario. Here, students, out of the both DNA strands, you are only going to take one strand. Okay, these are your two DNA strands. You are only going to take one strand as the template. The strand that is not going to be a part of transcription is going to be called the coding strand. Okay, the coding strand. Ma'am, then why did you keep the name coding strand? Don't ask me. Okay, coding strand. Now, this template strand is going to ultimately help me form the mRNA. And the sequence on the mRNA is going to be similar to that of the coding strand, where thymine will be replaced by uracil. That is the only difference that you will spot. Is this clear to all of you? Yes? Okay? Yes, Pramod, I'll try. Okay? Yes, tell me this. Tell me this. Yes. So, template strand will help me form the mRNA. This strand, the other strand is going to be coding strand. The coding strand will have exact sequence of mRNA where thymine will be replaced by uracil. Okay. Now, students, question comes for you about the upstream. So, when they ask you about the upstream, your answer should be in relation to the coding strand. Okay, in relation to the coding strand, you have to answer. That is, your promoter is going to be present in the upstream. Okay, your promoter is going to be present in the upstream of your coding strand. Okay, so you should tell it is present in the phi dash end. Okay, of the coding strand. Clear to all of you? Upstream end is going to be what? Okay, this portion which is present on phi dash end of the coding strand. Same thing goes with terminator region. It will be present on the 3 dash end of the coding strand. Done, done. Okay, clear? Clear? Yes, very good. Okay, so this question will come. Why we are not using both the DNA strands to form mRNA? If I use both the strands of DNA to form mRNA, just imagine, students, this strand will give me mRNA. So let's call it mRNA 1. Okay, this strand will form me mRNA. Let's call it mRNA 2. Now, these both are complementary to each other. These strands are going to immediately start binding with each other. That is, they are complementary. Since they are going to be complementary, do you think I am going to be able to make protein synthesis out of this? I will not be able to synthesize protein out of this, because according to me, I have to make sure that this one single mRNA goes for coding. Clear to all of you? Yes? Yeah, you can write. Okay, so I do not want a double-stranded RNA. Okay, I do not want this, because this will ultimately not form protein for me. This will stop my translation. You have studied it in Melidogyny Incognita. So it will not stop. It will stop my translation from happening. Clear to all of you? So these are some important informations. Now coming to the next topic, RNA processing. I'll give you a break after this chapter. Try to listen now. Okay. So far, did you understand? Can I get a thumbs up? So far, if you understood, please give me a thumbs up quickly. So far, easy. Any doubts? Okay. So far, easy. Any doubts? Yes, quickly. Awesome. Awesomings. Oh my God. Ratha spelling should go to dictionary. No doubts. Are you finding the chapter fine? Fine, done. Okay. Now I'll go forward here. Okay. Look here, students, this is called as RNA processing. First of all, you should know one thing. RNA processing is only done. Okay, RNA processing is only done in eukaryotes. Okay, it's done in eukaryotes. Okay, it is not done in prokaryotes. Why? Prokaryotes do not have a complex gene. Okay, complex gene. So here, the mRNA that came out of the structural gene, can you see the same thing is coming? But unfortunately, in eukaryotes, the gene is going to be a split gene. What gene? A split gene. A split gene means what? They are going to have coding plus non-coding sequence. Ultimately, my goal is to get a coding sequence that is going to form my protein. Translation. Simple. Okay. Now, this split gene, students, they have both introns and exons. Now in that only exons are the coding ones. Introns are the non-coding ones. Do I need introns? Ma'am, you don't need introns. But students, I have to teach you, so we need to take it. Okay. So I am going to do a process which is called as RNA splicing, where we are going to remove the introns, and add the exons. That is, we are going to attach the exons together to form a proper gene. Okay, proper gene. Now, remember, this splicing is done. Then we are going to get a completely new gene, but we are going to make sure that we are going to undergo that process. Two more processes are going to happen. First one is called as capping. Okay, capping. And another process is called as tailing. Tailing. Students, you have to understand that all this while whatever happened, that is replication. Okay, replication happens where exactly? At the S phase, no? Replication, transcription, all this was happening inside the nucleus. Even the RNA processing is going to happen inside the nucleus. Now, after this, once I get my new mRNA, I am going to send this mRNA to cytoplasm. Why? Because I need my ribosomes, all of these people, to do translation for me. So, I am going to send this newly formed mRNA to the cytoplasm. Clear? Okay, very good. Yes, okay? Okay, very good. Now, look here. Now, look here, students. To do capping and tailing, we are going to take the help of, okay, we are going to take the help of methyl guanosine triphosphate. Now tell me, is it a nucleoside or a nucleotide? Okay, methyl guanosine triphosphate. And for tailing, I am going to do adenylation. Okay, adenylation. That means I am going to add the A groups. Okay, I am going to add the A groups. Why? Because so that to make sure that this will go through proper translation. At the same time, since this is going out of nucleus to the cytoplasm, we are going to make sure that no other attachments are going to happen. Is this clear to all of you? Yes or no? Huh? So what has happened, students? The gene that came out was a split gene which had exons and introns. Some nonsense people in your life, you are going to remove them, right? Same way, non-coding sequence, I do not want to do anything with it. So I am going to remove the non-coding sequence with a process called as RNA splicing, and I am going to add all the exons together and get a new mRNA. Okay, that new mRNA is going to go through a process of capping and tailing, where I am going to do methyl guanosine cap, and tailing is going to happen with adenylation, that is poly A-tail. This too will ultimately give me a newly formed, a very good mRNA. Very good mRNA means what? Not like good looking, okay? The mRNA which will have all the exons that are going to help in coding for my protein. Now, one question has come again in KCET. The question was, which is the component that goes through transcription but does not undergo translation? Can you answer the question? Yes, can you answer the question quickly in the chats? Faster, then we will do genetic code. The component that has gone through transcription but has not gone through translation. Faster. Excellent, Malar Kodi. Hey, Malar, you're my old student. My old student. Okay. Yes. Very good. Very good. My new students, old students, I can see all of them. Very good. Introns. They have gone through transcription, but they have not gone through translation. They are not going to go through translation. Why? Because we are going to remove them before they undergo translation. Clear to all of you? Yes or no? Yes. Very good. Excellent. Now, students, genetic code. Now, genetic code, you don't have to study the boxes. The questions are going to come from this highlighted words. These highlighted words are very, very important. Clear to all of you? Yes or no? Now, look here. The codons are triplets. So, students, who was the person who came up with all this? George Gamow. Okay? George Gamow. See, with George Gamow, please remember Hargobind. Okay? Hargobind and Khurana. Okay, you have to remember all these people, and Marshall Nirenberg. Hargobind Khurana and Marshall Nirenberg, you have to remember, they made homopolymers and they also made protein synthesis without cell. Okay? Yes? Okay. Yes, come on. A. Okay. Now look here, George Gamow was the person who told that, okay, let's do one thing. We have 4 nitrogenous base. Yes or no? What are the 4 nitrogenous base that we have? ATGC. ATGC. And he was like, okay, let's do one thing. Let's make combinations out of it. First, they tried 4:1. We had 20 amino acids. Okay, so in his mind, he had 20 amino acids. 4:1 only gave us 4. No use. 4 to the power 2, it gave us 16, but we were less because we had 20. Then we came up with 4 to the power 3. Now, what am I trying to say? 4 to the power 1 means using only A, only T, only G, only C. 4 to the power 2 means AT combination, GC combination, AG combination, TC combination, like that. Okay, 4 to the power 3 gave us 64. And students, that time it was like 64. What are we going to do with 64? But later he understood that out of the 64 of them, 61 are coding for amino acids and 3 are stop codons. Okay, remember the stop codons, it's important. Now, this question has come, what is degeneracy? Okay, this question has come, so please make a note of this. Please make a note of this. What is degeneracy? That is, some amino acids are coded by more than one codon. The code is called as degeneracy. Okay, now the codon is read in the mRNA in a contiguous fashion. That means it is continuous, no full stop, no punctuations. Okay, you will not read, you have to read it AUG, UUU, UAG, okay, UCC, like that. You cannot read it AUG, comma, UUU, comma, like that. You are not supposed to read. Now, the codons are nearly universal. Again, exceptions are there. This can come as a question. Where is the exceptions? It's in the mitochondria. Okay, exceptions. From this box, except like all the highlighted topics, questions are going to come. Okay, don't break your head in learning that entire box. Okay, whatever question point of view, I am already teaching you. Now, students, here, bacteria to humans, UUU will code for phenylalanine. Okay. Now, AUG has dual function. This also can come as a question. It has coded for methionine. At the same time, it also acts as an initiator codon. That means, if AUG is present in the starting only, the entire translation will start. Done, done, done. And these are the codons. So, remember like this, UAA, UAG, UGA. A is present in both the centers and then G comes in the center. Okay. Done. Now, translation. Ready? Ready, steady, go. Pakka? Okay. Now let's start. Okay. Translation. Students, translation, you have to remember mainly few things. I'll tell you all the things that you have to remember. First of all, you have to remember about tRNA. Okay, you have to remember about tRNA. Okay, let me just duplicate this file. Okay. Yes. So, okay, look here. This tRNA, students, is very, okay, this tRNA is very, very important. What is very important about this tRNA? That these people have a very special structure. What is the special structure? The special structure is that these people have an amino acid. Okay, they have an amino acid acceptor site. So, this region is an amino acid acceptor site. Ma'am, why do they need an acceptor site? Because students, on the mRNA, what are you seeing? You are seeing the codons. To read the codons, you need someone, no? Imagine I start talking to you tomorrow with letters, okay? W-I-T-H, H-O-W, who are you? Now, I am not joining the words. I am reading each letter. Now, to translate that, you need someone. Same way here also, translation means we are translating the codes that are present on mRNA to attach the amino acids, so we can form polypeptide chains, polypeptide protein, that is polypeptide chains, which are going to ultimately decide our phenotype and genotype. Okay, yes, clear? Okay, perfectly clear? Okay, ma'am, please teach in English. Ma'am, I can't understand. Okay, I should teach you English first, then I should teach you biology. Two things I can't do now. So for English class, later we'll schedule a class. Okay, now translation, students, here you have an amino acid acceptor site, and down what you have here a person who is going to do the anti-codon. Okay, anti-codon. That is, let's take example. This is an mRNA. On this mRNA, you saw AUG. Who saw? tRNA saw AUG. Okay. Now, against this, A will code with what? A will code with U. Okay. U will code with A. G will code with C. So, it made an anticodon. So, that reading will become easy. Reading will become easy. Clear? Yes? Okay. Very nice. Now, anticodon. Okay. Anticodon. One anticodon loop. One amino acid acceptor site. Done, done, done. Yes or no? Okay. Now, students, remember these two things mRNA doesn't have. Amino acids cannot directly come and be like, oh, AUG, I am methionine, I will come and code. They cannot do self-attendance, no? So, to keep these two people in place, we need what? We need what? tRNA. We need what? tRNA. Okay. Now, with the tRNA, we need two more people, that is, one more person, that is your ribosome. And students, this ribosome has two units, okay? One subunit, okay, one smaller subunit and one larger subunit. Now, question has come in the previous year. Joining of smaller or larger subunit will start the translation. Your answer should be what? Your answer should be what? Okay, come on, tell me. Tell me. Smaller subunit or larger subunit when it comes and joins, translation will happen. Yes. Yes, tell me. We'll make one, what video? One roast video, no? Full. One series only we'll make of. Okay. Yes, good job. So, when a smaller subunit comes and joins only, the translation will start. Okay, the translation will begin. So, it's very simple. I need a reading frame. Okay, I need something who is going to read. Okay, so this is my mRNA. My hand is the mRNA. On the mRNA, there are codons. Now, to read this, I am going to take the help of two people. Who are they? A tRNA and a ribosome. They are going to read, attach the amino acid. They are going to read, attach the amino acid. Ultimately, I'll get a polypeptide chain. Ultimately, I'll get a polypeptide chain. Yes or no? So, here, simple translation is going to happen. Okay? Clear to all of you? Now, look here, students. Now, look here. This is your mRNA. Okay? 5' to 3' mRNA. We got the mRNA from transcription. We took the template strand. This codes will be similar to that of the coding strand. All this we learned. Now, smaller ribosome, larger ribosome. Larger ribosome with the tRNA will come and sit. Once the smaller ribosome attaches, the translation will start. So, what is going to happen? On the tRNA, the CA, that is anticodon, is going to start. See, one is already ready. AAU, UUA, correct? Anticodon is already ready here. According to the anticodon, they have already attached the amino acid also. So, tRNA is already ready. Now, what is tRNA waiting for? tRNA is waiting for to enter the ribozyme. To enter the ribosome. Correct? Sorry, ribozyme, no, ribosome. That is, students, on the ribosome, remember, okay? Ayyo. 1 second. This is your ribosome. Okay. On the ribosome, this is the lower unit. On the ribosome, there are 3 units. Okay. 3 points. Okay. Listen to me carefully. This is the only part that is little difficult for you people, but it is going to be very easy. See. EPA site. Okay. Yes. No, it's okay. Fine. I'm too old to study what is sarcasm now. Okay. You study. It's okay. Okay. Now look here, students. EPA site. EPA site. E for exit. Okay. E for exit. A for acceptor. And P for peptidyl site. Okay. Peptidyl site. Correct? Yes. Correct? Okay. Now look here. These are the 3 sites. Consider me as the tRNA. I am the tRNA. Okay. This is my anticodon. Okay. And this is my amino acid. Okay. This is my amino acid. Now, I have made the anticodon. I have attached the amino acid. Now, what am I waiting for? I am waiting to enter the A site. I am waiting to enter the A site, correct? So, A is going to be the acceptor site. So, let's say I got in acceptor site. Okay. Now I don't know, people will think what is this teacher doing in the class, okay? So I got into the A side. Now what am I waiting for? I am waiting for that person. There's another person. Let's say Chintu is waiting here. Chintu has doing bonding. Chintu is doing charging of tRNA and amino acylation. So after Chintu gets up only, I can come to the P side. Okay, so what you're going to remember, students? Gopika ma'am is waiting here. Okay, let's say Gopika ma'am entered inside. Okay, Gopika ma'am is waiting here to come. It got acceptor side. Now let's say Chintu is doing the bonding. Once Chintu moves, okay, to the exit side, immediately Gopika ma'am will come and sit here. Correct? Yes? Okay. Now what is going to happen? Okay, Chintu has got up. He has done the bonding. He has done the charging of tRNA. Now I will go with my codon amino acid and I will attach to the chain that Chintu gave me. Okay, I will attach to the chain that Chintu gave me. So this is my amino acid. Okay, I'm a tRNA. Every amino acid will have specific tRNA. So this is one. Another one will. So look here. This diagram will give you understanding of the same thing. Look here. This fellow is waiting to come. It has got accepted. It is waiting to come to the acceptor side. This fellow is doing what? He is in the peptidyl side. This is Chintu. He is in the peptidyl side. What is he doing? He has attached valine. Now let's say Mintu was here. Mintu is going to give this entire chain to Chintu. Why? Because we have to form the polypeptide chain. One person comes and attach. He has to attach it with the main chain. He has to attach it with the main chain. Clear to all of you? So Mintu will come. Mintu would have finished it. Mintu is exiting. So Mintu will give this chain. Clear to all of you? So one person is waiting outside to come to the acceptor side. One person is already in the peptidyl side. One person will exit. One person has already exited. This is exactly what happens here. Clear to all of you? So in the EPA side, each tRNA will come and join, attach, join, attach, join, attach. Okay? Yes? Clear? Okay. Thank you, Chari. Okay. Yes? Now, remember, this is clear to all of you? Yes or no? Is this clear? So, students, let's take an example of you being in a bus. You being in a bus. Okay, you have a book, you have a bag. So, imagine your bag is the anticodon loop and in your head, you have already decided, okay, let's say you have bag plus a luggage. Okay, one luggage is the anticodon, one bag is the amino acid. Now, you're waiting, you're looking for that seat. Okay, one lady is sitting in that seat and you're waiting for her to get up. So what you will do, as soon as she gets up, she is planning to change the seat. So what she will do, you will sit on that seat and she will give you her things. She will give you her things. Now what has happened, you have the entire polypeptide chain and you are waiting to get the charging done. Okay, now what is going to happen? Your stop has come. You're planning to exit. So when you're planning to exit, you will give this thing to the next person who is sitting, carry forward. Like that, entire polypeptide chain will be formed. Did you all understand? Huh? Yes? Yes, tRNA will help in reading the anticodon, attaching the amino acid and charging. Now I'll tell you about charging. Okay, now I'll tell you about the charging. Now students, first ever step of translation. First ever step of translation is called charging of tRNA. Now you will be thinking, ma'am, why does tRNA wants to charge? Students, that is because charging of tRNA or amino acylation of tRNA is done because tRNA needs energy. Okay, tRNA needs energy to get attached or to form this peptide bond. Okay, so charging of tRNA means, or amino acylation of tRNA means, it is where your amino acids have to attach with energy to come. Like tRNA will not chumma take the amino acid. They have to give energy. Energy should be required for attachment. So charging of tRNA happens so that we can form the peptide bond. How? I'll tell you. You are waiting for that. Okay. You are, thank you Aruna, you are waiting for that seat. Now, if you don't have an eye contact with that lady, now let's imagine that seat is there. You'll be like keep my bag. That's your eye contact. Otherwise, you both will not have a rapport. Someone else will take that seat. Exactly like that, students. If this tRNA has to give this entire polypeptide chain trusting you, imagine that lady has to give you her bag trusting you. You both should have a bond. You both should have a bond. Exactly. Same way here also. If this tRNA has to give this entire polypeptide chain, okay, they both should form a peptide bond. And two uncharged tRNA cannot form a peptide bond. Two charged tRNA can only form a peptide bond. So, charging of tRNA is necessary for peptide bond formation. Clear to all of you? Clear to all of you? Peptide bond formation will only happen if both the tRNAs are charged. So, the first ever step is charging of tRNA, or in other words, amino acylation. Okay, clear to all of you? Here an amino acyl synthetase enzyme will be used. ATP will be broken down into AMP. All that process is going to happen. This is an energy draining process. Clear to all of you? Yes. Thank you Harsha and thank you Madhumati. Aruna. Pakka clear? Okay, so please read it once. Please read it once and then come back. Okay? Thank you Aditi. Yes. Yeah, you can't avoid these aunties. Okay, these aunties are helping us learn. So, translation is clear. Now, in translation, students, we need to stop the process, no? We need to stop making this polypeptide chain. For that, we are going to take the help of two people again, three people actually. First is going to be, this is your mRNA. Students, please remember, tRNA is specific. Can you see each of them are coming for each amino acid? They are specific, and there is something called as initiator tRNA. Only if the driver gets in, the bus is going to start, no? So, the initiator tRNA is going to start the entire process. Now, how do I stop the process? How do I stop the process? You will stop the process. When your stop comes, you will get up and go. Now, to stop the process, in the mRNA, there is going to be UAG. What is UAG? Stop codon. So, the first way to stop the process is, once they read till there, they will understand that, okay, stop codon has come, I need to stop. But still, to increase the efficiency of translation, we have added UTRs. That is, some of the sequence which have got untranslated. That means they will not undergo translation. They are present, okay, they are present before the start codon, okay, before AUG and after the stop codon. After the stop codon. Why, students? To increase the efficiency. To increase the efficiency, UTRs are present, untranslated regions, a sequence that does not get translated, which are present before the start codon and after the stop codon to increase the efficiency. With this, we also give one release factor to end the entire process and to release the polypeptide chain. To release the polypeptide chain. Clear to all of you how we made the protein? This polypeptide chain is what? Protein only, no? What were we attaching so far? Amino acids. Amino acids are made up of protein. Correct? Huh? Correct? He didn't tell ma'am is a, this one, okay? Ma'am is the auntie, he didn't tell. He just told that we have to remove these aunties from the story. All Ardha Bardha you people will hear. Okay? All Ardha Bardha you people will hear and you will start attacking each other. Okay. Done? Yes? Clear to all of you this one? So, we are basically taking three people's help to stop the process. We are taking, what is that? Stop codon. We are taking UTRs and we are taking release factors. Okay, then only we will be able to release this entire polypeptide chain. Okay, now regulation of gene expression. Okay, regulation of gene expression. Regulation of gene expression also is super easy, students. What is going to happen? Some genes have decided that I don't want to work today. I want to put her off. Okay, I want to put her off. That means what? I do not want to work today. I want to be switch off. Okay, I want to be switch off. So, if a gene has decided to switch off, there should be some components who are leading to the switching of the gene. So, regulation of gene expression happens in eukaryotes as well as in prokaryotes. Now, question will come, where does it happen in eukaryotes? It happens in four places. First one, when the DNA is becoming mRNA. That means transcription. Second step, when the mRNA is undergoing RNA processing. Okay. DNA becomes mRNA. mRNA is going through RNA processing. That time gene can decide to switch off. Then remember, tata bye bye, we are saying mRNA to go outside to the cytoplasm. That time also, during the transport of the mRNA also, gene can switch off. And ultimately, during translation, the gene can decide to switch off. But in prokaryotes, it's more simple. In prokaryotes, students, it is more simple because transcription and translation, okay, I'm not writing the full, and translation is coupled. Is coupled means what? It's going to happen continuously, simultaneously it is going to happen. So the only place where a prokaryote can decide to switch off is during transcription and translation. Clear to all of you? Yes or no? Yes or no? Come on. Come on. Faster. Good. Yes. So here what is going to happen, students? DNA to mRNA gene can switch off, mRNA to RNA processing, capping and tailing they can switch off, transport time they can switch off, or during translation they can switch off. Okay? Yes? Okay, listen carefully once again. Once again. When can a gene switch off? When it is going through some process. You are working. That time only you can take holiday. Chumma, if you're sitting at home, can you take holiday? That's the simple thing. Okay. First work is going to happen during transcription. DNA to mRNA. First time. Gene can decide to switch on or switch off. Second thing. When mRNA is going through capping and tailing. That is the RNA processing. Okay. Third step. When we made the mRNA and we are transporting it to the cytoplasm, that time also the gene can decide to switch off. Then when translation happens. When translation happens. Clear? So these four places the gene can decide to switch on and switch off, and operon model is given only for prokaryotes. Students, in prokaryotes only one step the gene can decide to switch on and switch off, that is transcription and translation, because they are coupled. Okay, break I'll give you. They are coupled. Okay. Operon model is lac operon, val operon, histone operon. So this is all depending on what is present and absent. Lac operon was given by Jacob and Monod. Okay, Jacob and Monod. Okay, we'll finish off this and then I'll give you a break. Faster. Don't give up. Okay. Can we stop having the conversation? Anbu and Choco edits. Can you listen to the class? Huh? Come on. Now, look here. Represent. Now, lac operon concept means what, students? That is, in the presence and absence of lactose, what exactly happens? Simple. Let's keep it. Let's keep it very simple. You're going to write PYQs. You're not going to write storytelling. Right. So, what we will do, we will make sure that we are going to study exactly what is from exam point of view. Now, you have to remember Pipo ZYA. You have to remember Pipo ZYA. In that, these are your structural genes which are going to release the enzymes, and these are your regulatory genes. That means who are going to regulate the entire process. In that, I gene is going to release repressor mRNA. That repressor mRNA is going to form repressor protein. Normally, mRNA will form what? Protein. Okay, understood? Now, repressor mRNA will form repressor, and that repressor will go and bind with the operator when lactose is absent. When lactose is absent. So students, when lactose is absent, can I say that the gene is switched off? Gene is switched off. Now look here carefully. Here RNA polymerase is coming. Why RNA polymerase is coming? To do transcription. When RNA polymerase comes till here, he notices that there is a big block there. Okay, there is a big block there. Okay. Because there is a block, can RNA polymerase do transcription? Can RNA polymerase continue with translation? No, ma'am, they cannot do it. So what we are going to do? What we are going to do? Here we decide that RNA polymerase will come all the way to do transcription. He'll get upset and he'll go back. So here the gene has decided to switch off. Now let's take a scenario when lactose is present. When lactose is present and lactose is going to act as an inducer. Lactose is going to act as an inducer. So again, same thing will happen, students. I gene will form repressor mRNA, repressor mRNA will form protein. This protein will be waiting to go and bind with the operator. Again, same thing. RNA polymerase will be coming to do transcription. This repressor will not go and bind with the operator. Why? Because this inducer is going to attach with the repressor and make the repressor inactive. Make the repressor inactive. Clear to all of you? Now, this RNA polymerase will go forward happily. It will do transcription. Okay, sorry. It will do transcription and we will get lac mRNA. Okay, and the structural genes are going to release enzyme like beta-galactosidase, which is going to break down lactose to galactose and glucose. It's going to release permease, which is going to increase the permeability of E. coli to take in more lactose. It is going to release trans-acetylase and ultimately translation also will happen. Understood? Lac mRNA got formed. mRNA will form your proteins. The proteins are going to ultimate translation happen. Okay? Okay? Clear to all of you? Done, done, done. So, when lactose is going to be present, your gene is going to be on. Okay, gene is going to be on. Correct. When lactose is absent, the gene is going to be switched off. Why? Because transcription and translation will not happen here. Here, translation and transcription will happen. Clear to all of you? Yes or no? Huh? Perfect. Understood? Clear. Okay, moving forward to your students, I'm not going to do HGP. Okay, HGP, you have to do it by yourself. In that HGP, please study dystrophin is the largest gene. Okay, 2.4 million, and study about chromosome 1 and chromosome Y. Okay, these three things please study. Methodologies, you know it is sequence tags, express sequence tag and blind approach. Okay, sequence annotation. These two words you study. Enough. Okay, yes. Why they switched off? They switched off because RNA polymerase is not able to go further. If RNA polymerase is not able to go further because repressor is bound with the operator. Imagine, Suvra, imagine someone is coming and sitting in right front of your house. You're not able to exit the house. You're not able to do any daily activities. That means you will get inside and sit, no? You will switch off yourself. Same thing here also. RNA polymerase is not able to go further. Why? Because repressor went and bound with the operator. Then the RNA polymerase cannot go further because those are the regulatory genes. If those people are not working, the structural genes also will not work. Understood? Yes or no? Students, this is the last thing. After this, I'll give you a break. Okay. So, what is this? How to do our DNA fingerprinting. Okay. Questions have come from here. These steps are given as a picture. Okay. So, first we will do extraction. So, imagine one crime has happened. Okay. Chintu, Mintu are the criminals. Chintu and Mintu. Okay. Okay, I'll put Mintu with blue hair. I'm torturing myself. Okay, blue hair. Now, Chintu and Mintu students, they have done stealing. Okay, they stole something and we got, let's say, one hair sample or fingerprint from there. Now, we have to prove among Chintu and Mintu who is the criminal. So, here what is going to happen? First, we will do extraction of the DNA. So, if we have got a hair sample, we will take the hair sample. If we have got blood from the sign, we'll take the blood. Okay. After that, with the help of a restriction enzyme, what is a restriction enzyme? Molecular scissors. We are going to cut the portion that is going to, see, Chintu and Mintu, remember, Chintu and Mintu, 99.9% DNA is the same. They are the bulk DNA. What makes these two people different? They are maternal and paternal DNA. That means the satellite DNA, that 0.1% makes them different. That is the satellite DNA. Okay. Micro satellite and mini satellite. So, I want only this portion which is different in Chintu and Mintu. So, I am going to use restriction enzymes and cut them and take the DNA samples and I am going to make it into small fragments. Okay, small fragments. And I am going to run a gel electrophoresis. That is, gel electrophoresis is a thing like it's a machine that we use to separate the DNA according to the size. Okay. After I do electrophoresis, I will transfer it to a membrane with the help of southern blotting. This is called as southern blotting because I cannot keep it there for longer time. So, I will transfer it to a nylon or a nitrocellulose membrane, that is called as southern blotting. Then I will incubate it with probes. Why probes, ma'am? Because that 0.1% students, they are repeating units, correct? They are repetitive sequence. That to find that repetitive sequence, to confirm is Chintu or Mintu the villain, I have to make sure that I am making a probe which is complementary to that. Okay, complementary to that. So remember, let's say AGAATTC. Okay, this gene is repetitive sequence. Let's say this is repeating 500 times. Okay, 500 times in Min2. I will make a probe complementary to that T. Okay, G will code with C, A will code with T, A will code with T, A, C. Now you tell me, will this go and attach to Min2's DNA? Yes, ma'am, this will attach to Min2's DNA. So I will be able to notice it in an X-ray, that is in an autoradiography. The probe, which is radioactively labeled, will be shown. Clear? Yes? Perfect? Clear to all of you? So who is the criminal? Min2 will be the criminal. Why? Because this sequence have correctly gone and coded with Min2's DNA, and we will understand that this person is the criminal. So that repetitive sequence is more than enough for us to understand a crime. Okay? Even in identical twins, there are changes. Okay, there are changes. Clear? So, we understood isolation of DNA, digestion of DNA by restriction endonuclease, separation of DNA fragments by electrophoresis, transferring them into a nylon or nitrocellulose, hybridization using labeled VNTR probe, variable number of tandem repeats, detection of the hybridized DNA fragments by autoradiography, a schematic representation. Clear? Yes? Okay? Blue hair, you have a problem, huh? Now evolution, before evolution I'll do biotechnology. Okay, first I'll finish biotechnology. No, I'll do human health and diseases, then I'll come to biotechnology. Okay, because evolution 2 questions only will maximum come. Okay, evolution is not a high weightage chapter. It is like 2 questions max to max, 1 question. Chalo, let's start human health and diseases. First we'll start with the most important diseases. Okay, we are going to do the diseases which has been asked in the past years. Okay, we don't have to do everything, we will do the ones that has been repeating in the past years. Done. Okay, chalo. So typhoid, students, it's caused by Salmonella typhi. Will they ask you which is the causative agent? No, they will ask you what mode of transmission, or they will ask you the symptoms like sustained high fever 39 degree to 40 degrees Celsius. They will ask you that which of the diseases have sustained high fever 39 to 40 degrees Celsius. Your answer should be typhoid. What is the other question that they can ask you? What is the test that is the confirmatory test? Okay, Vidal test or Vidal test is the confirmatory test for typhoid. All of you haven't marked your attendance, quickly mark your attendance or else I'll stop the class now. Okay, mark your attendance quickly, conjuice. Okay, so mode of transmission, it enters through contaminated food and water. So questions will come from here, students. This and causative agent, again rare question will come. Now pneumonia. Before going to pneumonia, please remember Mary Mallon, who was a cook in different houses. She was a carrier of typhoid, so she's called as typhoid Mary, or a carrier of disease. Okay, now pneumonia, students, it is caused by Streptococcus pneumonia and Haemophilus influenzae. It affects the lungs and alveoli. Now question will come from here. Lips and fingernail turns grey. You would have seen this question in a lot of mock paper. If lips and fingernails are turning grey in color, that means that is a symptom of fatal pneumonia. Okay, fatal pneumonia. How will you get it? By droplets and aerosols. Clear to all of you? It is a respiratory problem. It is a respiratory problem. So questions will come from the portions where I have underlined. Yes. Now, most important one is malaria. Will they directly ask you what is malaria, who causes malaria? No. They will ask you the life cycle, questions from the life cycle. So let's learn that. So students, the causative agent of malaria is Plasmodium vivax. Other causative agents can be Plasmodium malariae, Plasmodium ovale and Plasmodium falciparum, which is very, very fatal. This can come as a PYQ question. Okay, this can come as an MCQ. Okay, MCQ. You don't worry about question practice. We have already planned entire question practice. Okay, every single day you will have mock papers and question practice. So don't worry. Okay, don't worry. Yes. Now look here. Plasmodium vivax is the causative agent of malaria. Now it is a digenetic host. That means it needs 2 hosts to complete the life cycle. First host is going to be man. Second host is going to be female. Okay. Now second host is going to be female Anopheles mosquito. Man, students, in man what is going to happen? Asexual stage is going to happen. Okay, in man what is going to happen? Asexual stage is going to happen, and female Anopheles mosquito, sexual stage is going to happen. Okay, sexual stage is going to happen. So remember that these people need 2 hosts, man as well as mosquito. Both are needed. In that, your female Anopheles mosquito will be the primary host, secondary host or an intermediate host will be your man. Done? Yes. Now look here. Very, very important, a PYQ and an MCQ question is sporozoites. What are sporozoites? Sporozoites are going to be the one that is going to, be transferred to the person. Understood? So, there is two questions that can come, students. Where is sporozoite stored in the mosquito? Answer is going to be S for storage, S for salivary gland. So, sporozoites are going to be stored in the salivary gland of the mosquito. Second question, where is the fertilization of sporozoites happening? That means taking the gametocytes, male and female gametocytes, where does the fertilization happen? The fertilization is going to happen in the gut of the mosquito. So this is a very important question. Storage in salivary gland, fertilization in the gut of the mosquito. I tell this 100 times, but still many students will make mistake. Many students will make mistake. Okay, now let's learn the life cycle of malaria. Okay, let's learn the life cycle. What is the life cycle of malaria? Look here. In man, Plasmodium vivax has entered. Now, it will release the sporozoites with the first bite to a healthy person, and that sporozoites will directly go to the liver cells and it will do asexual reproduction there. Liver cells are otherwise called as hepatocytes. So from the liver cells, it will burst open the liver cells and it will go into the RBC. In the RBC, asexual reproduction in the RBC will take place. Again, many cells will reproduce and it will burst open the RBC. Bursting open of the RBC will release a toxin called as hemozoin, which is the reason for having fever and chills. Okay, which is going to be fever and chills. Correct? No, biotech will happen here. Ecology will happen in part 2. So, an infected mosquito, okay, an infected mosquito has gotten Plasmodium vivax. That mosquito will bite a healthy person and it will release the sporozoite into the body. From the body, it will directly go to the liver cells. In the liver cells, it is going to multiply, and from there, it is going to directly multiply. It is burst opening the liver cells and it is going into the RBC. In the RBC also, it will burst open the RBC and it will release a toxin called as hemozoin. Got it? Yes. Okay, hemozoin, and that hemozoin will cause fever and chills for the person. Okay, so the fever and chills is going to be recurring fever and chills. Every 3 to 4 days, the person will experience the fever. Now, students, in the RBC, there is also release of gametocytes. That means female and male gametocytes will be formed, but in man, asexual reproduction can only happen, sexual reproduction cannot happen. So, we will not fertilize the gametocytes. Instead, what is going to happen? Those gametocytes are going to be taken up as a blood meal. Okay, those gametes are taken up as a blood meal by the mosquito. Okay, in the blood meal, they are going to take it up and fertilization will happen in the gut of the mosquito. Look at this, gut of the mosquito, and that will lead to the formation of zygote. Zygote will end up forming sporozoites, and that sporozoites will be stored in the salivary gland, and this entire cycle will continue to happen. Okay, yes, clear to all of you? Clear to all of you? Yes, because of the release of hemozoin. Very good. Okay, very good. Okay. Yes. Done? Yes. Very nice, very nice. Okay. So, infected mosquito releases sporozoite. That released sporozoite will go to the liver, liver to RBC. RBC will form gametes. RBC also will release hemozoin. That hemozoin causes recurring fever every 3 to 4 days. That then the gametes will be collected by the blood meal by another mosquito or the same mosquito, and the gametes are going to undergo fertilization, leading to the formation of sporozoites, and that will be stored in the salivary gland. Clear? Yes or no? Understood? Easy, no? Yes. Okay. Next is innate immunity. Questions have come from innate immunity, physical, physiological, cellular and cytokine barriers. Physical barrier, students, skin that lines our entire body. Skin is the first physical barrier. Second physical barrier is mucosal lining. Now you tell me, from where and all organism can enter, pathogen can enter. What is disease? Disease means you are at unease. Okay, no, you're not feeling at ease. That means you are being affected by what? You have been affected by a pathogen. Pathogen is the disease causing organism. Now, a disease causing organism enters through your nostrils, to your mouth, or through your UI, that is your urinary tract. These three places, there is mucosal lining. Why? As a protection. So, physical barriers are going to be skin and mucosal lining. Mucosal lining are going to line your what and all? It's going to line your tracheal system, that is your Okay, it is going to line your digestive system, respiratory system and your urinogenital system. Now, physiological barrier, students, like your HCl in the stomach, which kills the pathogens in the food. Okay, lysozyme, the tears. Okay, sweat and oil glands, HCl in the stomach and cerumen in the ears. These are all going to be what? Physiological barriers. That means the barriers that are going to protect you from entry of organism. If the organism has entered also, they also have a mechanism to kill them. Okay, so it's good to cry sometimes but not every day. Okay, now cellular barrier, students, cells which are going to act as the soldiers. Okay, cells which are going to act as soldiers. First you have natural killer cells or NK cells which are going to kill the pathogens. Next you have macrophages which are going to do phagocytosis, engulfing of the microorganisms. Then you have monocytes. You already know WBC itself is going to help with fighting. In that, your macrophages are one of them. Monocytes. And then students, you have PMNL. They can ask you for full form. So remember, PYQ question, it is MCQ. Whenever I tell PYQ, that is MCQ. Okay. Yes. Now, PYQ, polymorphonuclear leukocytes, other name is neutrophils. Okay, neutrophils. So, 4 cells, natural killer cells, monocytes, macrophages and neutrophils. Okay, now you come to cytokine barriers. Again, a very important question. What happens, students? 5 cells are there. Let's imagine 1, 2, 3, 4, 5 cells are there. First cell got affected by a virus. That cell will not be selfish. Okay, that cell will be like, okay, anyway, I'm going to die. Why to even signal someone? No. That cell will release interferon. That interferon will signal the other cells telling that I have sacrificed my life. Okay, I have already done a problem. What is that? Okay, so your new NCRT will be applicable for 2026 aspirants, not for you people. Okay, 2026 students, not for you people. Now what will they do? A change. That to all small changes, students. So 1, 2, 3, 4, 5. So this will be, interferons will be released. This interferons will signal the 2, 3, 4, 5 cells telling that, you know what, I have been affected by a virus. You please save yourself. So they will release antiviral protein. Okay, they will release antiviral protein. Clear to all of you? Yes or no? Okay, so that is innate immunity. Then you have acquired immunity. Under acquired immunity, you have B cells and T cells. B cells are a part of humoral immunity. They release antibodies. Antibodies have 2 heavy chain, 2 light chain. All of you know that. They are made up of 16 disulfide bonds. There is an antigen binding site. Paratope, epitope, all of that I've taught you, but questions are very rare from those topics. Okay. Now, next question, very common question comes from lymphoid organs. Lymphoid organs are primary lymphoid organ and secondary lymphoid organs. I've always told you this. Primary lymphoid, one second. One minute. Yes, 1 second. Okay. Yes. Okay, one person has to go. Yeah. So here what is going to happen, students? Primary lymphoid organs are like the military. Okay, where the actual training is going to happen. Okay, actual training will happen. Okay, no, Christina, all of you will run away. So actual training will happen in the primary lymphoid organ. That means origin and maturation will happen. Secondary lymphoid organ is where the actual fight is going to happen. That means these people are going to be exposed to the antigen. These people are going to be exposed to the antigen. So here you see primary lymphoid organ, origin and maturation is going to happen of who? Your B cells and T cells, who are part of the cell mediated immunity and humoral immunity. Humoral immunity means fluid based immunity. Okay, so that is going to be B cells who are going to release antibodies. T cells are going to help B cells release the antibodies. They are not going to be directly involved. Okay, bone marrow, students, origin of B cells and T cells happen, but maturation of T cells will happen in the thymus. So remember T for T cells. Okay, that's not the actual meaning, but still remember like that. Okay, remember like that. Okay. Ma'am, please say human liver fluke has how many hosts? Liver fluke, what are you talking about? Fasciola. Fasciola will have two hosts. Some of the exceptions are there which has 3 hosts. I think human and snail is one host. Human, fish and human is, three hosts is there, two hosts is there. Two hosts will be human and snail, and one more will be fish also will be involved. Okay, yeah. So I don't know which one you are talking about. Tell me the exact species. Okay, here secondary lymphoid organ, students: Peyer's patch, tonsil, spleen, lymph nodes, and MALT. Okay, MALT. MALT ka full form they can ask you. Secondary lymphoid organ is where the actual fight is going to happen. Here only origin and maturation was happening, differentiation was happening, but actual fight where they are going to face the antigen is going to happen in the secondary lymphoid organ. So that is why I tell this is the battlefield, this is the military training. Okay, so Peyer's patch, tonsil, spleen. Spleen, students, all of you know, graveyard of RBC. Okay. Lymph nodes and mucosa associated lymphoid tissue, MALT, MALT. Okay, MALT. Okay, that is going to cover 50% of the all the lymphoid organs. Okay, MALT, mucus. Now, active and passive immunity. Lot of questions have come from active and passive immunity, so please learn it. Now, let's take example of again Chintu and Mintu. Okay, so this is Chintu. Okay, Chintu will have pink hair. Okay, pink hair. Chintu. Okay, then we have Mintu. Mintu will have yellow color hair. Okay, now this is Mintu. Now students, what is going to happen? Let's take example. Chintu and Mintu has to go for a party. Okay, has to go for a party. Now, Chintu will tell that, no, you know what, I am going to go for ready-made. Okay, ready-made. Ready-made dress. Okay, I'm going to go for, this has become ready-made. Okay, so ready-made dress. And Mintu will be like, no, I am going to buy the cloth and I'm going to stitch it myself. Okay, Mintu is very efficient. Okay, I'm going to stitch it myself. Okay, so here what's going to happen, students? This fellow, who is that Chintu, is actually passive. Chintu is not wasting any energy. Chintu is going to the shop, getting the ready-made cloth and wearing it. Correct? So here what is happening? This is going to be a passive immunity. But on the other side, Mintu is going to the shop, buying the cloth, getting the measurement done, then stitching it. It is more of an active immunity. So active immunity means we give the time for the body to make antibodies. Okay? Antibodies. And on the other side, passive immunity means we are going to take the ready-made antibodies into our body. Now let's see example. Active immunity, students, the first one is going to be natural, and then we have, so under natural, artificial and passive, you have natural and artificial. Okay, so under active you have natural and artificial. Natural means self-infection. Self-infection means what? You got an infection. Okay, Chintu does smart work, you can't say. Mintu, you have to support. You're in Mintu's class. I'll hit you people now. Okay, so what is going to happen here? So active immunity means, students, natural and passive. Natural means what? Natural means you are the infection has happened, body recognize the infection and they are making antibodies against it. Okay, it's like primary response, then if the infection comes again, secondary response, because memory will be there. Now, artificial means what? You are giving vaccinations. Vaccination means what? Weakened antigen. The activate antigen, no, we are not giving that because that will be harmful for our body. We are going to weaken them. Okay, we are going to weaken them and we are going to inject them into our body. So this way what happens? Body will recognize the antigen and start making antibodies against it. But both the times what is happening? Body is still making the antibodies. Now, passive immunity, buying ready-made clothes like that. Passive immunity means preformed antibodies. Preformed antibodies means ready-made antibodies. Again, natural and artificial. Natural means, students, colostrum. Mother gives to the infant, which is rich in IgA antibody. Okay, artificial means anti-venom or tetanus, that is where we do not have the time to make antibodies. Our body will, the person only will die. So what we will do? We will inject it into a horse, take the antibodies from the horse, inject it into us. So that is called as artificial passive immunity. Clear to all of you? Why this is natural? Because you are not injecting anything into the mother. The mother is naturally making the colostrum. Okay, naturally making the colostrum. Clear? Now, AIDS. AIDS. Okay, AIDS is, it is a deficiency of immune system. It is caused by what, students? Human immunodeficiency virus. Again, MCQ. Okay, MCQ question. That is a retrovirus. What is a retrovirus? Having RNA genome which can form RNA to DNA. RNA to DNA and combine with the host and manipulate the host. AIDS was first reported in America and people thought it was a it was a gender, like depending on the sexuality the disease was caused, but later they noticed that no, actually everyone anyone can have AIDS. Okay, now in last 24 years it has killed over 25 million people. Okay, transmission, students, sexual contact with an infected person, transfusion of contaminated blood or blood products, okay, during tattoos, injections, that kind of thing. Okay, sharing of infected needles from infected mother to the child through placenta. Clear? Yes or no? Okay. Now, this is the only diagram that you have to study properly. Okay, this is the only diagram that you have to study properly. Okay. Yes. Acquired immunodeficiency syndrome. Very good. Now, students, a retrovirus, what is the capability of a retrovirus? It is going to do one job. If it has RNA, it is capable of making DNA, right? It is capable of making DNA. So, this retrovirus has injected, okay, that means it will leave its genetic material inside. So, it will leave the viral RNA is introduced into the cell. Viral RNA will be converted to viral DNA with the help of reverse transcriptase, right? I have drawn the diagram and taught you clearly, right? So, all of you will know. Now, okay, viral DNA produced by reverse transcriptase. That viral DNA will be incorporated into the host genome. So, why did it make the viral DNA? So, we can manipulate our body. Our body will be able to differentiate the RNA. It will not be able to differentiate that DNA has gotten. So, they have done viral DNA incorporates into the host genome, and that viral DNA, it will tell the viral DNA that, you know what, do mRNA, do protein, everything you do according to me. It will manipulate, okay. So, like how we manipulate the genes of a transgenic animal. So, new viral RNA is produced by infected cell and that will end up forming new virus. All of this is going to happen in your macrophages, okay, because macrophages are the outlet, okay, it's like a factory outlet of HIV, okay, macrophages. But students, when the same thing happens with T helper cells, they will kill the T helper cells. Okay, they will reduce the number of T helper cells, and this way what will happen? Our immunity will reduce. Okay, our immunity will reduce. Clear to all of you? Yes or no? Yes or no? Tell me quickly. Okay, my voice is giving up. Done? Yes, macrophages, correct. Vaccination and immunization. Immunization and vaccination means what? Vaccination means you are giving a, I'm giving you, let's say, anti-tetanus injection, and you are going to be what? Your body is going to understand that, okay, now what happened, students? Vaccination is the active process, okay, immunization is the result of it. That means you become immune to that disease because you have got vaccination. Your body have already formed antibodies against it. Done? Clear to all of you? So, this is what happens, students. Now, diagnosis. What is the diagnosis? ELISA. They can ask you the full form. Enzyme linked immunosorbent assay. And you can also give antiretroviral drugs. But please do understand, these drugs are only for increasing the lifespan, not like in the sense just to increase or let's say reduce the cause, but not like cure the cause. Okay. So, antiretroviral drugs can be given, okay. They are partially effective, okay, just to prolong the life of patient. Now, prevention of AIDS, students, first of all, educate the people. They should know that they should not have sexual intercourse with multiple partners. So, for that we have NGOs, okay, many NGOs are there, and we have also NACO, okay, NACO means National AIDS Control Organization, and make blood. That means if you are taking blood from someone in the hospitals, you have to check the history of that person, okay. Then use disposable syringes when you are doing tattoos, when you are taking injection. Please make sure that the needle that they are using is a new one, okay. And advise safe sex, that is using condoms or contraceptives, okay. Regular checkups for HIV is susceptible, okay. Microbes chapter will be taken up by Baswa sir, okay, because it's actually a botany chapter. Now, students, cancer. Cancer is what? Abnormal division. Cancer means abnormal division, continuous, uncontrolled division, right? Normally, cells will happen, normal cells. Let's take example, okay? normal cells, yes, hum do, hamara do. So these are the normal cells. These normal cells, students, they have something called as contact inhibition. When one cell comes in contact with another cell, they will immediately know that they need to stop the division. Okay, no division. But this cancer cells are not like that. These people do not have, they lack contact inhibition, because of which they will keep growing. Okay, they will keep growing. Understood? So remember this one thing, normal cells show contact inhibition, but these cells have uncontrolled growth. They have lacked the property of contact inhibition. Clear? Now students, there are two types of tumors, benign tumor and malignant tumor. Benign tumor means what? It will be in one place. Okay, it will be in one place like this. Malignant is not like that. If it is here, okay, it is going to spread to this place. Malignant is the one why most of the people have recurring cancer. It will spread like this everywhere. It will spread like this everywhere. Okay. Okay, benign tumor confined to the place of its origin, and it does not spread. Most of the time they are not cancerous or painful. Okay, tumor means a mass of cells. Okay, it's also called as neoplasm. Now malignant tumor, students, mass of proliferating cells, neoplastic or tumor cells, which grow rapidly. Like imagine I am going from here to this place. Here also I make friends. From here I go to this place. I make friends. From here I go to this place. I make friends. Now this condition shown by your tumor cells is called as metastasis. That means they are spreading and growing there. Spreading, growing. Clear? So they grow rapidly, invade and damage. And not only that, they also starve the normal cells. They will starve the normal cells. How, students? By competing. That means they fight with the other cells for nutrients. They fight with the other cells for nutrients. Also, they also have a property of making their new blood vessel for themselves. Okay, blood vessel for themselves, and this condition is called metastasis, where they rapidly grow and divide. Okay, clear to all of you? Wherever the cells go, they are going to form a new tumor there, and that condition is called metastasis, which is only seen in malignant tumor. Okay, malignant tumor. Okay, Aditi, thank you. Okay, you saw Mohit asking break. Suddenly you are like, yeah, even I want break. Mohit became the trigger point. Same way here also. In our body, there is proto-oncogenes. They are just waiting for a trigger point. The moment you are exposed to tobacco, UV rays, X-rays, ionizing radiations, non-ionizing radiation, immediately the proto-oncogenes will get activated to oncogenes or cancerous. Understood? Yes or no? Okay? Lagging, huh? Now fine? When some teacher takes no class, my class will go. Will get activated to oncogenes. It is fine now, no? It's fine now? Yeah, now it's okay, right? Yeah. So what I was trying to say, I was telling that Mohit asked for break. If Mohit asks for break, there will be students who are waiting for someone to ask for break. They will get a trigger point. Same way here also, students. Biological agents, that is proto-oncogenes, are present with our normal cells, but they just need an activation. The moment they get a trigger point, they will start getting activated. So biological agents like oncogenic viruses or proto-oncogenes, when proto-oncogenes are activated, the cells become oncogenic. That means they become cancerous. Okay. Now, chemical agents, students, the biggest problem is tobacco smoke. Okay. Tobacco is a big reason for cancer. Nicotine, caffeine, mustard gas, caffeine also. Okay. But still we all have caffeine. Nicotine. Now, physical agents, ionizing radiations like X-rays and gamma rays, non-ionizing radiation like UV rays. That is why we get skin cancer. Okay. Skin cancer. Clear? It's raining here. That is why it's buffering for you. Okay. It doesn't have to rain in your place. Now, students, to study drugs, I have made an entire notes for you people. So, please use this notes to study. Okay. Please learn from this notes. I have made the entire short notes. Okay, like see, opioids. Action binds to opioid receptors in the CNS and gastrointestinal tract. Example, morphine, heroin and brown sugar. Morphine, it is extracted from Papaver somniferum, okay, or opium poppy, used as a painkiller in surgery. Heroin, AK, smack or diacetyl morphine, is bitter crystalline obtained from acetylation of morphine. All question based. Okay, question based I have made here. Okay, yes, you will get the notes on, where's my Telegram channel? Yeah, oh, I didn't put my Telegram channel, only link. Since where's my Telegram channel? It's not there. You will get it on Vedantu NEET English Telegram channel, as well as I changed my name. Okay, Telegram channel Gopika Biology. If this is too big, we will put it as a link in the description box. Okay, official. Okay, Gopika Biology official. You will get it on the Telegram channel. Okay, yes. Oh, Maharashtra, a lot of heat. Okay. So students, can you study from this notes? Cannabinoids I have put exactly how it should be studied. Okay, coca alkaloids I have put, and medical use like barbiturates, amphetamines, all that I have put. So please study from this notes. Okay, can we start biotechnology? Okay, biotechnology, whatever you can do. Okay, whatever you can do for yourself, I have given. Okay, brown sugar also is a kind of opioid drug. Okay, opioid drug. Okay, I already followed. Okay, very good. You will get the notes there. In case the file is too big, I'll put a link in the description box. That link also I'll share it on the Telegram channel. Okay, done. Let's start with biotechnology, principles and processes. All the high weighted chapters we are finishing. Okay, then we will come to the low weighted chapters depending on the time. Because if I make it too late, then Diksha ma'am will make it late, then Baswa sir will sleep at 5 o'clock. So that's why I'm trying to speed up. Okay, yes. So students, what is this biotechnology? Basically, you have genetic engineering is happening and bioprocessing is happening. That means we are taking the genes of our desire, inserting it into using a vehicle or a vector, we are inserting it into the host organism. This is basically the heading of it. Now the first diagram that I am going to teach you is this one. Okay, this one, that is foreign DNA. That means your desired character. Now you want to be tall. Okay, you want to be tall like this. Okay, now you are only this much. Now if you want to be tall, you need to get the desired gene, right? You need to get the desired gene. Let's take an example. Okay, another person is tall. You want this fellow's gene. So what you will do, you will take the desired gene and you will insert it into your body and you will also automatically become tall. This is what is happening. Now for all this to happen, it will not just happen like, okay, I will look at the gene and you will eat the gene. It's not like that, no. You need a proper process. Okay, you need a proper process. Okay. Now, okay, now look here, foreign DNA students, vector DNA. So vector is basically a vehicle. Because without a vehicle, you cannot enter the host organism, right? You cannot enter the host organism. So foreign DNA and your vector DNA. Now I have cut a portion of the foreign DNA which is going to make you tall. I am going to insert it into this vector. Now after insertion, I got a recombinant DNA molecule. Recombinant means what? I got a foreign DNA with the vector DNA. Now I will use this to do transformation into the host organism. Now you became tall. Now you became tall. Okay. That is sir student. Okay. That is a NEET aspirant who is studying with you people. He is the one who is sending all that messages for you people. Okay. Come on. Oh. Okay. Yes. Come on. Next one. What is it? Transformation. Okay. Now, so understood now what is biotechnology? Basically, if you want to do something, okay, you want to do something, then you can, okay, then you can take that desired gene, insert it into a vector, that is a vehicle, and add it into a host. Understood? Add it into a host. Okay. Now, look here students, first question that will come for all of you is about restriction enzymes. Okay. Okay, restriction enzymes. Clear? Now, before I go here, let's go here. Okay. Yes. Now look here students, restriction enzyme. So what happened? No, when the bacteria was affected by a bacteriophage, that means a virus that infects bacteria, people noticed that this bacteria is not actually getting affected by the virus. People were shocked. How come? Okay, people got to know that this bacteria has the ability to do methylation, at the same time cut the DNA strands. cut the genome of the virus into pieces. So everyone was very eager to understand, and that is when they came to a conclusion that there is something called as molecular scissors or restriction nucleases. Okay, two types are there, exo and endo. Nucleases which have the ability to cut. So look here, when a bacteriophage was affecting a cell, there was no expression. Why? Because these people were doing self-defense, and during the self-defense they secreted methyl groups which added to make them not understand, okay, that okay, this is the genetic material, and cut the DNA strands, and this is called as restriction enzymes. Okay, now under nucleases, students, you have endonuclease and exonuclease. Endo means cuts within, exo means cuts at both the ends. So always exo means outside, endo means inside. So endo means within, exo means outside. So these restriction enzymes are called as molecular scissors. These restriction enzymes are called as molecular scissors. Chari, no, these notes are not enough for NEET. You need to learn from my other notes. Okay, all my notes are available on the Telegram channel. You download those notes and study, because that has all the lines of NCERT. Okay, in this some topics are skipped. So I do not want you people to learn like that. Like if you're finished studying all of it, you're doing a revision, then this notes is more than enough. If you're studying for the first time, study from the actual notes. Okay, now naming of restriction enzyme, students, very, very important for all of you. Look at this, Eco R1. How do you label it? Now look here. Here, E stands for the genus name, coli stands for the species name, R stands for the strain, Y that is 13 stands for the number. Okay, number. So I will show you here exactly. Now hind 2. Okay, hind 2. Now look here. H stands for the genus name, that is going to be Haemophilus. Okay, IN stands for influenza, that is the species name. D stands for the strain, and 2 stands for the discovery of the enzyme. So they will ask you a question, how do you do the nomenclature? How will you tell the nomenclature? Genus, species, strain, number. Genus, species, strain, number. Can you remember this much? Yes or no? So same thing goes with Eco R1. Euchneria, coli, R strain, and 1 is the number. Okay, 1 is the number. Here Haemophilus, influenza, strain, strain D, and Roman number 2. Roman number 2. Here same thing has happened. Discovery, RY13 is the strain number. So they will ask you exactly how will you do the nomenclature. Now students, as I told you, exonucleases removes nucleotides from the ends. Okay, ends of it. Endonucleases within the DNA. Okay, within the DNA, Eco R1. Okay, so restriction enzymes are necessary in your vectors, and it is restriction enzymes are very necessary during every process. Now DNA fingerprinting also we saw, right? DNA fingerprinting also we saw. Now here one more most important thing is, where do these people cut? Now I am telling that these molecular scissors are going to cut, but I did not tell where do they cut. They cut exactly where, students? They cut at the palindromic sequence. Each of the restriction enzymes will have specific palindromic sequence. What is palindromic sequence? Like mom. That means both the sides, if you read this way or this way, if you read, both of them reads the same. Same thing goes with wow. Malayalam, okay, madam, okay, like that, many words. Okay, Christina, is there alive? It is only for a microsecond. Okay, don't worry, I'll be back. Yeah, tata, wow, everything. So restriction enzyme, students, these are molecular scissors. Okay, some portion got cut. Okay, it will be fine. It will be fine. Don't worry. Molecular scissors cut the DNA at specific palindromic sequence. Example, Eco R1 cuts the DNA at 5' to 3', GAATTC, and leaves sticky ends. What are sticky ends? Who are ready to mingle. Okay, mingle. That means, students, they cut a little away from the center. They cut a little away from the center. So instead of cutting like this, okay, this will lead to blunt ends. This will lead to blunt ends. Instead of cutting in blunt like this, what they will do? They will cut like this, leaving a little away from the center. Clear? Yes or no? Yes or no? Hey, how is Tata? Palindromic sequence. This way you read Tata. This way if you read, it is ATAT. It's not a palindromic sequence. Okay? Not a palindromic sequence. Now, Removes from ends, cuts from specific locations. Clear to all of you? Now look at this. This is what they told. Sticky ends, they will ask you. Blunt ends, they will ask you. Look here. So GAATTC, you should know this by heart. They will ask you question that eco R1, which is the restriction, which is the palindromic sequence. Okay, palindromic sequence. So your answer should be what? The enzyme cuts both the DNA strands at the same site. Okay, vector also, foreign DNA also will be cut at the same site. Otherwise, stickiness won't come. Understood? Correct? No. If I cut one like 2 by 3 and 1 by 3 by 2, will they be same? No, they both have to be cut by 2 by 3. So here, remember that eco R1 cuts the DNA between the bases G and A only when the sequence is GATTC. Okay. So instead of cutting like this and forming blunt ends, he will cut like this. He will cut like this, leaving this people separate. So now what you will get? You will get GCTTA and AATTCG, and these two will be ready to stick with each other. So sticky ends lead to more mingling. Students, sticky ends are the ones who are ready to mingle. Okay, sticky ends ready to mingle. Sticky ends ready to mingle. Okay, understood? Now you saw vector DNA and foreign DNA joined very easily with the help of DNA fragments joined at the sticky ends. Correct? So they'll ask you eco R1 cuts at which palindromic sequence? You have to say GATTC. Will you tell? Will you tell GATTC? Palindromic means from both the sides. If I read it, it is the same. Okay, right to left, left to right. Now, characteristic of an ideal vector. That means if I am trying to buy a vehicle, I am thinking of purchasing a BMW tomorrow. Now I have already decided it's BMW. Okay, no money, students, jokes. Okay, imagine I am thinking that I need to buy BMW. Why did I decide that I want to buy BMW? Because of the inbuilt quality, because of the mileage, because of the other things. Okay, now how did I come to a conclusion? Because I want to know what are the characteristics. So same way, if I am thinking of a vehicle, there are few characteristics. First of all, ability to self-replicate. If they do not have an ORI site, if they are not capable of replicating, how can I use a vector? It has to get transformed into the cell. It has to replicate into the cell. Okay? Yes? Okay? What if it comes to, true? Okay? That also is not coming. Okay? I don't know. I was just telling. Okay? Mileage. Now don't attack me because you people know so much about car. I do not know. Okay? Why will I think when I don't have money about it? Tell me. Huh? Sitting here and scrolling phone. You will think of 720 marks and sitting in AIMS. Doesn't make sense, no? Like that only. So here, link with the host. It should be suitable for the host. Then they should have cloning site and they should have selectable markers. Selectable markers are the most important because we will be able to know exactly which cell got transformed, which cell did not get transformed. Okay? Yes. Okay? Yes. Okay. Now look here. What is this, students? Plasmid. Plasmid is the most common vector. What is a plasmid? It's a chromosomal circular DNA. Okay, it is a carrier or a vehicle. Is the most common vector is plasmid. It is a small chromosomal circular DNA which is present in most of the bacteria. Clear? Yes or no? Why you people then telling me? That's why I roasted. Okay? Yes. Okay. Now look here. So for an host to buy a vehicle, okay, to hire them as a vector, first of all, it should do replication. Second of all, I should be able to pay the EMIs like that. No, same way it should be suitable for the host. Third thing, it should have cloning sites. Okay, it should have cloning sites. Fourth thing, it should have selectable markers. Done. Yes. Okay. Yes. Recognition sites should be single specific. It should not have multiple sites where the cutting will happen. Now, vehicle to transfer the foreign DNA into the host is called as the cloning vector. Common one is plasmid, which is a circular strand of DNA which is present in bacteria. Okay, and then we can also use bacteriophage. Now, must have origin of replication, selectable markers and cloning site, and recognition sites for restriction enzymes. Students, recognition sites have to be specific, otherwise restriction enzymes will cut everywhere. Okay, it will cut everywhere and it will make it like that, what is that, like tone genes. Okay, so we should not do that. Okay, now look here, PBR 322 question will come from here for you. Look at the PBR 322. You have an ROP. Okay, again helping with the replication of the plasmid. ORI site, origin of replication. Near ampicillin site you have PP. Okay, you have PP, that is ampicillin resistance site, PST1, PVU1. In the middle you have eco R1, Cal1 and Hind3, and here to the tetracycline end what do you have? you have Bam Sal. Okay, it's like one sambar that I made, Bam Sal, that is Bam H1 and Sal 1. Okay, so PBR 322 students, here we can do insertional inactivation, which I'll teach you now. Restriction sites, which are the restriction sites? HIND 3, Eco R1, Bam H1, Sal 1, PVU1, PSG1, Cal 1. ORI site is the antibiotic resistant genes are there, that is ampicillin and tetracycline, which are selectable markers. Okay, ROP codes for the protein involved in replication of the plasmid. Correct? Yes or no? Class 11 PDF is already in the description box. The PDF is too big, so we have made it a link and uploaded. Okay? Yes, quickly smash the like button. Come on, your friend is telling. Now, students, what is insertional inactivation? First of all, you should know how did the PBR 322 name came. P for plasmid, B for Bolivar and Rodriguez, 322 is the sequence. Okay? It was the first artificial vector. Now, you all know what is insertional inactivation, but still let's learn it once again. Now students, insertional inactivation means, let's take an example. Christina wants to do insertional inactivation. Okay, that means what? She wants to make sure that this tetracycline is not working anymore. Working anymore means what you will do? You will put a gene here. You will put your desired gene. Okay, we told her don't put it here, but she's like, no, I want to put it here. So she added her desired gene here. Now you tell me, will tetracycline resistance be active on this PBR? No, it will not be active. Why? Because she inserted something in between that. It is not possible to work. Right? So this is called as insertion. Because you are inserting something, this portion becomes inactive. Simple words I am breaking down. Now, why does insertional inactivation make sense, or why is selectable markers necessary? Because you will be able to know exactly if a cell is transformant, recombinant or not. Now let's take example. Amazon delivery guy. He is a vector. Okay, all of you should give me thumbs up if you understand. Now let's say Amazon delivery guy is there. Okay, if Amazon delivery guy, okay, let's take example. Okay, PBR 322 is Amazon delivery guy. Okay, if he has entered into the workplace, that means he has gone to take your parcel. He has entered into the warehouse. That means the cell becomes transformant. Some transformation has happened. That means something, the genetic material has entered into the cell. That means Amazon guy entered the warehouse. Now let's take example. The Amazon delivery guy entered into the warehouse, came out of the warehouse without the parcel. Okay, he got into the warehouse and he came out without the parcel. That means he did not bring your desired product. If he did not bring your desired product, is he recombinant? He is not recombinant. You call it recombinant only when the desired gene is inserted. Correct? Now let's take example. He went into the warehouse. He came out of the warehouse with your desired gene. That means he becomes transformant and recombinant. Now let's take example. Amazon delivery guy is not at all there in your life because you didn't order anything. That means you are just a non-transformant cell. So here students, what is going to happen? Listen carefully. PBR 322 have ampicillin and tetracycline resistance. Okay. Now to understand a cell got transformant or non-recombinant, when you look at cell A, what has happened? It has the nucleoid and it has the plasmid. That means PBR 322 entered the cell. So I can say the cell has gone through transformation. Something has entered the cell. Transformation happened. But they are non-recombinant. Why? Because there is no desired gene. No desired gene. Okay. Let's take cell B. Transformant. Okay. Transformation happened because plasmid has got in there. Recombinant also happened. That means you have done insertional inactivation at the tetracycline resistant area. That means you inserted your desired gene. You inserted your desired gene near the tetracycline. Okay. Yes. Now, third scenario, the plasmid itself did not enter inside. There is no delivery guy only. So it is becoming non-transformant. Now, how do I differentiate who got transformant, who got recombinant? Now, I told you, but we have to do a test. That test is going to be what, students? That test is going to be what? Here, see, if I grow this medium in ampicillin, if they are ampicillin resistant, they will be able to grow. If they do not have ampicillin, then they won't be able to grow. So, cell A will grow in ampicillin, cell B will grow in ampicillin, cell C won't grow in ampicillin. Why? Because they don't have the PBR 322. They don't have ampicillin resistance. Are you all understanding? Yes or no? Now, Tetracycline resistant. Now what did we tell Christina? We told don't do insertional inactivation. She's like, no, I want to add my desired gene where tetracycline is there. So tetracycline became inactive. Okay. Now when I grow the A in tetracycline, they are tetracycline resistant. They will be able to resist it. So they will grow. But B won't grow. Why? Because Christina made tetracycline inactive. So if they are not tetracycline resistant, then they are not going to be able to grow. So cancel. Correct? Yes or no? Then here what is going to happen, students? There is no PBr322 only. So this also no. Is this clear to all of you? Please check the box and tell me if you are able to understand. You are able to understand? Yes or no? Tell me faster. Okay, possible? Understood? What is going to happen? Yes, Bhavana. So, students, simple. Keep it very simple. PBr322 have ampicillin and tetracycline. Both are selectable markers. What is the meaning of selectable markers? We are able to select which is transformant, which is non-recombinant. Simple. Scenario 1. Plasmid PBr322 got inside. That means these people are going to have both ampicillin resistance and tetracycline resistance. Correct? Transformation has happened, but they are non-recombinant. Why? Because there is no foreign DNA. Correct? Here what has happened? Transformation happened. That means plasmid got inside. They are also recombinant. Why? Because desired gene is inserted near tetracycline. Okay? Recombinant. Now, third scenario, no plasmid only. No plasmid only. So how will they be? They will have nothing they have. They are just a normal cell. Now if I grow them in ampicillin, A will put a tick mark. Why? Because PBr322 have ampicillin resistant markers. Okay, so they will grow. B also, yes. Why? Because I did not inactivate ampicillin. Ampicillin is still active. So B also will grow. C won't grow. Why? Because there is no PBr322 only. No delivery boy only. Okay, yes or no? Yes. Now, tetracycline when I am growing it in a tetracycline medium. Here also tetracycline resistance is there. So, this also tick mark, it will grow. Here it won't grow. Why? Because we have insertional inactivation of tetracycline we have done. So, it will not grow here. I means insertional inactivation. This will not grow anyways. Why? Because there is no vector at all. Done? Now you understood? Yes. So, this is what is the use of a selectable marker. Okay, selectable marker. Look here. When a foreign DNA is inserted within a gene of a bacteria, the gene is inactivated. It is called insertional inactivation. Here, the recombinant plasmid loses the tetracycline resistance. Understood? It loses tetracycline resistance due to insertion of the foreign DNA. When the plasmid are introduced into the E. coli cell, three types of cells are obtained. What are they? Non-transformant, transformant with non-recombinant, transformant with recombinant. Non-transformant means they have no plasmid. Okay, that means they will not have resistance to neither tetracycline nor ampicillin. Best notes you can have. Transformant with non-recombinant means what, students? They are resistant to both tetracycline and ampicillin. No, they do not have the gene. Okay. Transformant with recombinant means they are resistant only to ampicillin. Understood? Recombinant plasmids can be selected out from the non-recombinant by plating them on ampicillin medium. Then transformant are transferred to the tetracycline medium. So you will understand which is recombinant, which is non-recombinant by using them in ampicillin medium but not in tetracycline medium. Clear? Yes or no? Huh? Yes. Okay. Now the last one is again under insertional inactivation about your chromogenic. Okay. So look here, students. What is going to happen? By this type of selection of recombinant, it is difficult procedure because it needs simultaneous plating on two plates. That is, they are telling, if I have to do amphicycline, tetracycline, amphicycline, tetracycline, it will take a long time because two plates. Okay, two plates have to be used. So, what we can do is an alternative selectable markers have developed based on their ability to produce color. Okay, in the presence of chromogenic substrates. That means in the presence of a substrate, these people will be able to make a color. Okay, now in this, a recombinant DNA is inserted into a coding sequence gene of an enzyme, that is beta galactosidase, so that the gene is getting inactivated. I have taught you PUC8. In that, LAC-Z is there. LAC-Z you have studied in Lacopron. LAC-Z will release beta galactosidase. Now, if I do insertional inactivation on LAC-Z, then beta galactosidase won't be formed. Correct? Beta galactosidase won't be formed. So, now they are saying that wherever insertional inactivation happens, such colonies do not produce any color. They are going to be white. Okay? They are going to be white. These are identified as recombinant colonies. That means we have understood that the foreign particle has entered into the cell. How? I inserted. So, Christina inserted it into tetracycline. I inserted into LAC-Z. LAC-Z which is present in your PUC18 or PUC8. So, to that I inserted a gene. Now, LAC-Z will not be able to produce beta galactosidase. If they cannot form beta galactosidase, then the colonies that we are going to get is going to be white in color. The colonies that I am going to get is going to be white in color. Let's say I did not insert a foreign gene, then I am going to get blue color. So, this is non-recombinant. Non-recombinant, this is recombinant. Clear to all of you? Yes or no? So, if the plasmid in the bacteria have no insertion, okay, it gives blue color, and if there is insertion, it will give white color. Clear? Yes or no? KCD, how was it? How was it?
Sorry, I can't help that. You can learn more about logging your health data.
Sorry, CD got activated. Now, process of biotechnology. Okay, process of biotechnology. What is going to happen, students? First, you will do isolation of DNA, and you have to use lysozyme, cellulase, depending on what you are trying to extract. Like if you are doing plant cell, you will use cellulase, right? Like that. Purifying using centrifugation and chemicals. Cutting of DNA, you will use restriction enzymes. You will get sticky ends or blunt ends. Amplifying, you will use PCR chain. The step is DE. Okay. Denaturation, annealing and extension. Denaturation, annealing, extension. So, you will be using this step to amplify the gene of interest. Okay, that is PCR, polymerase chain reaction, and you will use a primer, Taq polymerase, which is extracted from Thermus aquatis bacteria, which is very thermostable. Okay, which is extremely thermostable. You will use a DNA template and nucleotides. Okay, yes. Now, students, annealing 50 to 60 degree, denaturation 90 to 92 degree. That's why we are not using DNA polymerase, because DNA polymerase is not thermostable. Okay, and then extension at 72 degree. Insertion into vector, students, you will use DNA ligase to join the foreign DNA with a vector. Then transfer into the host by transformation, that is chemical, heat shock, electroporation, all these techniques you can use. Selection of transformant by using markers. Okay, amphicycline or tetracycline. Clear to all of you? Okay. Primers are added during annealing to do the extension process. Okay, forward primer and reverse primer will be added during the annealing, that is your oligonucleotides, and they will do the extension part. Clear? Yes. Done. Now look here. Other methods, that means competent means what? How do I insert this foreign DNA into the host? Okay, for that, first I will do micro injection. That is, in this, the recombinant DNA will be directly injected into the nucleus of the animal cell. This is very important, animal cell they are telling. Gene gun, in this the cells are bombarded with high velocity microparticles of gold and tungsten coated with DNA. This method is suitable for plants. Now the question will come, which among the technique is useful for plants, which is useful for animals? Your question will be like this. Okay. Now, disarmed pathogen vector. That means, students, we know that this fellow is a big criminal. Okay, but he can diffuse locks. Okay, so what I will do, let's take example. Okay. Vidyarthi, okay, name only is Vidyarthi. Vidyarthi's house, there is some very precious documents that the government needs. So we are going to find a criminal who can diffuse any kinds of locks. So we will send that criminal telling that on you we have put CCTV camera, okay, we have a pen camera, and we have also linked the map, what do you call for that, yeah, location, like wherever you are, I forgot the word, wherever you are we will be able to sense you, okay. So we use that criminal, we disarmed that fellow. We know that this fellow is dangerous, but we disarmed him. How? By keeping a track on him, where he is, what he is doing, everything, okay. Now he will get into the the house, he will take from Vidyarthi's home the documents and come. Now this is called as disarm pathogen. That means we are using their good capabilities by disarming them, okay. Yes, so disarm pathogen vectors, they infect the cell and transform the recombinant DNA into the host. Example, Agrobacterium tumefacium, which is a tumor inducing plasmid, okay. Clear? Tumor inducing plasmid. Students, done. Chapter is done. Biotechnology applications ready. Biotechnology applications ready. Faster, 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 faster. We have to finish this chapter in 10 minutes, 15 minutes. Okay, only main things we'll study. So, main things from biotechnology principles is going to be PBR 322, transformant, non-transformant, competent DNA, microinjection, gene gun, as well as disarmed pathogen, and heat shock, okay, 42-degree heat shock, ice shock, heat shock, ice shock, okay. Yes, then what they will ask you? They will ask you PCR, okay, exonuclease, endonuclease, nomenclature. Yes, ma'am, ready, full energy, can't take rest, what to do? We have to finish the class. 700 likes, not yet, huh? We haven't reached 700 likes, 700, my tongue is twisting, 700 likes, huh? Wow, it's going to be a 4 hours class, come on, let's do it. Okay, biotechnology and its applications, okay, biotechnology and its applications, okay, yes. Now, first topic that we are going to study is GMO, genetically modified organisms, okay. That is like GMA, Gopika ma'am army, like that we have genetically modified crops. What are they good for? They increase the yield, nutrition, resistance to pests, diseases, herbicides. Example, BT cotton and golden rice. Golden rice, what are we doing, students? It is going to be rich in vitamin A. We are going to extract it from daffodils plants, okay, daffodils, using Agrobacterium tumefacium. Okay, we are going to insert it into rice and make it vitamin rich for people who have color blindness and other things. Okay, done, done, done. Then look here, students. It contains crygene from Bacillus thuringiensis, which is a crystal proteins which are toxic. Okay. Now, students, genetically modified crops or organism, basically we are doing gene manipulation. We already studied about how we can manipulate the genes. Now, we learned no foreign DNA we can cut. Now, we are going to learn how we can utilize them. Okay. Now, RNA interference, that is gene silencing. This is Melidogyny incognita. RNA is gene silencing. So, one way we can do gene addition, one we can do gene subtraction. Clear to all of you? Now, let's take example. Okay, let's take example. Tomato. Tomato gets always very fast ripened. So, what we will do? We will remove the gene that causes the ripening of the tomato. So, this way we do gene subtraction. And then we have example of golden rice where we are trying to increase the vitamin A. So, that is what I am telling you. BT cotton contains crygene from Bacillus thuringiensis. This is addition. Okay, addition. This is subtraction. We are basically minusing, or we are telling that gene, please don't get activated. Calm down. Okay, yes, beta carotene, which will be a precursor of vitamin A. Gene silencing technique to stop the expression of a harmful gene. Example, Melidogyny incognita resistance. It causes what? Root knot disease. It causes root knot disease in tobacco. Understood? So, we will do gene subtraction. Clear? This is very important for all of you. Okay. Pest resistant withstands abiotic stress. Nutritional value will increase. Post-harvest losses decrease. We can do gene addition, BT cotton and golden rice, gene subtraction, RNA interference or Melidogyny incognita, modification of gene ADA, gene therapy. Okay. Gene therapy. Now first gene addition, students, what is happening? Pest resistance. So many a times, okay, let's take an example. Okay, Rathas was a cotton farmer. Okay, he was doing cotton farming and he was doing continuously, but there was no, every time when he is trying to do harvesting, all the cottons were damaged. So he came to me and he told, ma'am, I'm facing this problem. So what did I do? I told him, don't worry, I will give you BT toxin. You spread, like mix it with water and just put it on the cotton. What is this BT toxin going to do? It is going to enter into the larvae. The larvae's gut is alkaline, so it will make pores in the larvae of the larvae's gut and it will kill the larvae. Okay, so here pest resistant Bacillus thuringiensis, self defense. For self defense, this was releasing crystal proteins. This crystal proteins was capable of doing perforation, so we use that BT toxin to protect our cotton. Okay, to protect our cotton. So it was able to protect us from beetles, leptoterans, diphterians, corn borers and bollworms. Okay, done all of you. So this is what Rathas was facing, that the larvae was entering inside and eating the cotton. Okay, eating the cotton. So he wanted a solution and I told him that, you know what, this bacteria does self-defense. It releases crystal proteins which are actually capable of killing the larvae. Then Rathas asked me, ma'am, if the bacteria is releasing a toxin, will it not kill the bacteria itself? Then I told Rathas, ayyo, not like that. It will only kill. It will only get activated in an alkaline pH. Alkaline pH is present in whose gut? In larvae's gut, not in our guts. Okay. So students, what happened? Larvae will go and sit on the cotton. BT toxin is already sprayed by Rathas. So it is an inactive form. It will become active in the gut of the insect by coming in contact with alkaline pH. And the toxin will get activated. It will do perforation of pores in the gut, causing swelling and lysis and the death of the larvae. Clear to all of you? Yes or no? Okay. Yes. Very good. Okay. Very good. Okay. He'll give you cotton after the class. He'll give you cotton. You people build a mattress with that. Now, genetically engineered medicine, that is humulin, growth hormones and vaccines. Gene therapy, you have ADA deficiency. Okay. And molecular diagnosis, students, we use it to detect PCR, ELISA, and for early diagnosis detections also. Okay. This question has come. This is the PYQ. They have asked a statement-based question that serum and urine, will they give us early detection? The answer is no. Early detection is not possible by serum and urine. We need to do ELISA or PCR. Okay. I'll come to this. Wait, let's keep a hold. Yeah. Genetically modified insulin. So what happens, students? Lot of people nowadays have diabetics. So let's say two doctors were thinking what to do for this. They were like, okay, fine, insulin is not getting formed. Let's use cattle's to get our insulin. But the problem was when we used cattle's insulin, it started causing allergy to people. Because it was causing allergy to people, people started getting scared. So then they came, American company, Eli Lilly company. Okay, Eli Lilly company, they were like, okay, don't take tension, we have a solution. But the solution did not come out very fast. The solution took a lot of time. Why? Because of the structure of insulin. Look at the structure. A chain, B chain, A chain and B chain connected with the C chain, and these A chain and B chain is also connected with a disulfide bond. So when Eli Lilly company was trying to arrange this, to make the placement of this, they were not able to make the placement, and that is when they realized that, oh my god, we don't need C chain. Why? Because C chain is only present in the proactive form. C chain is present only in the proactive form. Okay, so extracting from cattles caused allergic reaction. That is when they came up with humulin. And normally, students, pancreas, that is islets of Langerhans, releases insulin, that is a peptide. So we cannot give tablets also. People thought, why don't we do tablets? We cannot do tablets because it's a peptide hormone. It will get digested in our stomach. Okay, so here what happened? Eli Lilly company in 1983. This date is very important, PYQ question. Okay, Eli Lilly company made humulin, that is they were having difficulty in assembling, but it was solved by removing the C chain. It was solved by not synthesizing the C chain. So what did they do? They took E. coli A, they took E. coli B, they made A chain, B chain, and they made A chain, B chain connected with a disulfide bond. They did not make C chain because they noticed that C chain is only present in the proactive form. In matured insulin, we only need A chain and B chain. Clear to all of you? Yes or no? Okay. Now, this is this one. What is that? RNA silencing. Okay. Nothing to worry, students. Already I told you, if we get double-stranded RNA, if we get dsRNA, that means translation will not happen. No translation. That is exactly what we are doing here. We are basically playing with the central dogma. We are not letting translation happen. Okay, so let's read through this very fast. A nematode Melodogyne incognita infects the roots of tobacco plant. Okay, because of which all the farmers were having problem. Okay, all the farmers were having problem. It can be prevented by RNA interference or RNA silencing. How? RNA interference method is a cellular defense. Okay, it is our body's defense in normal cases. So it prevents translation of a specific mRNA due to the complementary double-stranded RNA. We already learned this in molecular basis of inheritance that if we make double-stranded RNA, then we cannot go for translation because protein will not be formed. Correct? No? Diabetes mellitus is sugar. Okay, that means the sugar volume. Okay, hyperglycemia. Diabetes insipidus is because of the loss of water. Diuresis happen. Okay, yes. 20, 22, I forgot the chain numbers. Okay, I think it's 22 chains or something, A chain and B chain. A chain is smaller, B chain is longer. Okay, I'll tell you exactly later when I remember. The source of this complementary RNA is in the form of, is from an infection by RNA. Students, what is the source of the complementary RNA? It is neither from an RNA virus or a mobile genetic element called as transposons. Okay, that replicate via RNA intermediate. Now, isolate the nematode specific gene. It is introduced into the host plant, agrobacterium vectors. It produces both sense and antisense. Okay, so this double-stranded RNA, one will be sense. Okay, one will have sense, one will not have sense. No, not like that. Okay, one will be sense, that is like complementary, sense and antisense. Okay, now RNA in the host. These RNAs are complementary, so they form a double-stranded RNA. It initiates RNA interference and silences the specific mRNA of the nematode. Thus, the parasite cannot survive in the transgenic host. Clear? Yes. Okay. Clear? Yes or no? Perfect. Understood? So, basically, with the help of what we studied in a molecular basis of inheritance, we have utilized it here. Okay, even I need a coffee, student, so let's finish it fast. Now, the first clinical, so here it is gene therapy. That means where we can add a gene and remove a big problem can be prevented. Okay, so first clinical gene is in 1990 was given for a 4-year-old kid with adenosine deaminase deficiency. If adenosine deaminase is not there, then the person will have an immune problem. Okay, immune problem. This caused due to the deletion of a gene. What is the gene that got deleted? Adenosine deaminase. Okay, adenosine deaminase got deleted, an enzyme for the functioning of immune system. It can be cured by bone marrow transplantation, but again, students, nothing is permanent. Okay, enzyme replacement therapy. Okay, that is we keep injecting the ADA, but again it will get over. But these are not completely curative. Not completely curative. Okay, so what we will do? Gene therapy we have to do, that is we add a gene at the embryonic stage. Later if you add also, it is not going to work out. We have to add it at an embryonic stage. Okay, so gene therapy for ADA deficiency, collect the lymphocytes from the patient blood, grow it in the culture medium, introduce the ADA cDNA, okay, ADA cDNA into the lymphocytes using a retroviral vector. They are returned to the patient. This should be periodic repetition because lymphocytes are not immortal. Lymphocytes will get over. They are not immortal. They will die. So, every time when the deficiency happens, we have to keep on doing this. Okay? Yes? Yes, come on. Right? This is easier to understand. Notes are easier to understand. Yes or no? Basically, I took a summary. Like I put the snip of your NCERT and I took the summary. Clear? Yes or no? This is easy to understand. Actually, these notes are beautifully presented so you people can understand. Now, students, they are used to treat the disease. This is transgenic animals. In that, you have to study this paragraph, the most important. One more question that comes. 95% of the transgenic animals are who? Your favorite mouse. Okay. Now, this is the most important question from transgenic animals. That is, what are transgenic animals used for? Especially, they are used for treating emphysema by making a human protein. Don't confuse it with hormone. It's a protein, a human protein called alpha-1 antitrypsin. Emphysema is caused because of chronic disorder of smoking. Okay, continuous chain smoking. So, it's a chronic disorder. So, we are using a transgenic animals, that is to treat the disorder. Okay, transgenic animals means any animals whose gene can be manipulated. Mice is the most important. Okay, Mice is the most important. Used to treat emphysema. In 1997, Rosie, who? Not Tracy, Rosie, the cow. Okay, it was the first transgenic cow which produced the human protein enriched milk. This is a PYQ question. They have asked you how many per liter. 2.4 grams per liter. It contains what, students? Human lacta alpha lacta albumin, which can be given to babies instead of natural cow milk, because these are enriched in protein. Got it? Clear? Come on. Okay, I don't know what you're talking about. Okay. Yes. Human alpha lactalbumin, that is, first is emphysema, alpha-1 antitrypsin. How they will ask you the question? They'll confuse you with human protein and human hormone. Okay, human protein and human hormone, they'll confuse you. So make sure that you don't get confused. It's a protein. Alpha-1 antitrypsin, Rosie, first transgenic cow, that is protein enriched milk, 2.4 grams per liter. Okay. Wow, thank you. Yes, Akul. Oh, I'm so happy. Biology went well. Okay. Yes. Now let's come to, so that chapter is over. Now let's come to evolution and reproductive health. Okay, we will start with evolution. Evolution only main thing, students. Don't worry, full thing we can't teach. Okay, evolution, because only two questions come. So why to waste time first? Okay, evolution. So all of you know Big Bang theory. After this, you ask a break to Diksha ma'am. Okay, 10 minutes break. Okay, she'll give you a break. Yes. There is artificial colostrum, like colostrum you can't make, but you can make the same combination of the colostrum. Everything you can make, students, nowadays. Anything. Tomorrow you can make me also. Okay, you can make my same copy. So that is what I'm telling, anything you can make. Now, Big Bang theory, evolution, we have studied it like a story. So let's study it like a story. So all of you stretch yourself. I know it has been tiring, but stretch yourself. Let's do evolution, reproductive health, no problem. Okay. Yes. Big Bang theory, what happened? A big explosion happened that led to expansion, which led to cooling down. Cooling down led to condensation of gases, and that is how they say that gases were formed. So Big Bang theory, students, it happened in years are important. 20 billion years ago, Earth was formed 4.5 billion years ago. There was no atmosphere on the early Earth. That is why people could not survive. Okay. Water vapor, ammonia, carbon dioxide, methane, carbon dioxide, ammonia released from the molten mass covered the surface. So this was the only surface that was there. It did not have anything else. So people believe that when a UV rays, okay, when a UV rays came, this split the water molecules, okay, they split the water molecules into H2 and O2, and this O2 did not escape, but H2 escaped. This O2 went and combined with NH3CH4 to form water, carbon dioxide, etc. Okay, the ozone layer was formed. As it cooled, the water vapor fell as rain to form oceans. Okay, all this is story. Question will come only for 20 billion years ago. CH4, CO2, NH3, no atmosphere. Only that will come. Okay. 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 Exactly. My clone will not have same humor sense. What will we do? Okay. Diksha ma'am won't give break already, these people are telling. Okay. Diksha ma'am is very strict, students. Should I tell ma'am to be little less strict? Huh? Life appeared almost 4 billion years ago. That means what, students? Almost 500 difference is there. Okay. 500 difference is there. Now, different types of theory. I've put this note so that you people can study. Okay. You people can study. Theory of spontaneous generation, that is abiogenesis. Some person told that if you put the lab coat in one corner, if there is wheat, and if you leave it after 21 days, you saw mice. Okay, it did not come because of it, it was because of sweat and food resources. So some people told that life came because of dead and decayed, which is not true. Louis Pasteur proved it wrong by telling that life came from pre-existing cells. Okay, pre-existing cells. Okay, so Louis Pasteur disapproved this theory. And biogenesis, students, Reddy's, Plansky, this is not there for you people, but Louis Pasteur is there. They told that life originated from pre-existing life. Okay, pre-existing life. Then cosmic theory, still believed, still most favorite for some Greek thinkers, is that theory of panspermia. It states that unit of life, spores, were transferred to different planets including Earth. Okay, different planets including Earth. Okay. Okay, yes, I'll tell Diksha ma'am. Okay, yeah. Now look here, theory of special creation. They told that God created everything in a span of 7 to 8 days, and that is believed by Father Suros and people who believed in religions. Okay, then students, the most relevant theory was given by Oparin and Haldane. They told that life comes because of chemical evolution. That means some inorganic components with the help of thunder, storm and all of that, they will form organic components. That was proved by Urey and Miller. This experiment is very important for all of you. Urey and Miller experiment, students, CH4, NH3, H2O and H2. Okay, these gases were put into a flask and spark discharge was given at 800 degrees Celsius. Spark discharge was indicating the thundering that happened on Earth, and these gases indicate what is present in the atmosphere. So after a few days, they noticed that the gases got collected and they got a liquid. They got a water which was containing organic compounds, and that organic compound had all the amino acids: arg, alanine, aspartic acid and glycine. Okay, many other people also came and they got simple sugars, amino acids, nitrogen bases, fats, pigments, and all these combined to form what? Lipids, polysaccharide, RNA, protein and probions. Probions means the protocell. Okay, protocell. So here what happens, students? Oparin's and Haldane's theory, Oparin's and Haldane's theory was proved by Urey and Miller with an experiment, and that experiment, in the flask they took ammonia, methane, carbon dioxide and water molecules, and they put spark discharge with 2 electrodes, that is at 800 degrees Celsius, and the heat was so much that at 800 degrees Celsius these gases got condensed and they got a soup. Okay, Haldane soup. You can tell that Haldane soup had amino acids: arg, alanine, aspartic acid and glycine. Many other people also just changed the composition here and they started getting sugars, nitrogen bases, amino acids, lipids, fats. All this combined to form what? Lipids, polysaccharide, RNA, DNA, and that could have led to the formation of a first cell. Okay, first cell. Got it? Yes, 1953. Very good. Now, homologous and analogous, students, very easy. Okay, homologous means they have common ancestors. Structure is same but function is different. Humerus, radius, ulna, carpals, metacarpals and phalanges is same for cheetah, man, dolphin, but one is using it for holding, one is using it for running, one is using it for flying. Okay, common ancestors, divergent evolution. So, HDTV, AC room. Okay, homologous, divergent. That means from one point, all of you will migrate to your GMCs, AIMs, MMFs. I'm not able to remember the names also. Government hospitals. So that means what? You people are all diverging from one point. Okay, you're all diverging from one point. Okay, clear? HD, AC. Common ancestors, different functions. Analogous is going to be origin is different, structure is different, but same functions. Okay, like eyes of octopus and humans, wings of butterflies and bat flippers of penguins and dolphins. This is also you are from different places, but you are all coming to Vedantu NEET English. So that means you are convergent from different places. You are coming to one point. Clear? Example: sweet potato. There bougainvillea and cucurbitaceae, tendrils of cucurbitaceae and thorns of bougainvillea. Both are stem modification, but one is for protection, one is for climbing. Got it? Yes. Yes. Clear? You people only will come and talk. These people will not talk. Okay, they are good students. Yes. Now, AC radiation, adaptive radiation, students. What is adaptive radiation? Even though all of you stay in Tamil Nadu, some of you are in Chennai, some of you are in Pondicherry, different places you people are. That means what? From one point you have all radiated to different point, and because of which your adaptations also have changed. So adaptive radiation means process of evolution starts from one point and radiate to other areas, and this was proved by Darwin with the help of Darwin's finches. He saw in Galapagos Island. Okay, in Galapagos Island he noticed that these people are actually seed eating, but then what he noticed? He noticed that these people, one became insectivorous, one became, the beaks became longer, one beak became shorter. So that is when he understood, oh my god, these people have all become different. Okay, different. So Darwin was going in which ship, students? HMS Beagle. Okay, so Galapagos Island, he noticed that there were around 14 varieties of Darwin's finches which were originally seed eating. Originally, you people like sambar and rasam, but then because you stay in Pondicherry, you started liking French cuisine. Okay, French cuisine, that is the thing. Okay, yes. When other students come, I'll call you people good students. When only you people are there, I'll never call you good students. Okay, then you'll sit on our head. Yes. Now, Hugo de Very's, very important PYQ question. That's why I added this point. Hugo de Very's worked on evening primrose. that he told about how does variation happen. He told variation happens because of mutation. That mutation will be large, sudden, directionless and random. Okay, remember these words. And one step mutation is called saltation. If you don't remember this, no, gone. Large, sudden, random, no direction, random. Okay, and one step mutation. At one step mutation happens, it is called as saltation. Okay, saltation. This is same thing, adaptive radiation, but I want to stress on this one point here. When more than, okay, question can come, when more than one adaptive radiation is appeared in an isolated geographic area, it results in convergent evolution. Okay, so how will you remember? Ma'am likes burgers and sweets, okay, on weekends. Okay, on weekends, okay. So, sweets on weekends, correct? Yes, mole, anteater, mouse, lemur, okay, bomb, what is that? B for what, students? Bandicoot, okay, squirrel, flying squirrel, wombat, okay, yeah, bandicoot, wombat, okay. Now, so this is very important, please remember this. Convergent evolution means what? Placental mammals and your Australian marsupials, they are from the same geographical area, so they have become convergent, they have become almost same. Okay, yes, ma'am likes burgers and sweets on weekend. Okay, ma'am don't eat junk food, it seems. Only I am telling you, people are not buying burger and giving. You told after clearing need you will buy me burger and give. Where? I didn't see any of you in this area also. Adaptive radiation is the evolution of different species. This you already understood. So Darwin's finches is the example, Australian marsupials is the example, placental mammals is the example, and this is the most important line. Okay, most important line. Now students, Hardy-Weinberg principle, frequency of AA, that is dominant, frequency of small a recessive, and frequency of heterozygous 2pq. Now if they give you p is equal to 0.4, you will be able to find p plus q is equal to 1, you will be able to find q is equal to 0.6, and you will be able to find 2pq is 0.48. So like this problems also they can give you. Okay, like this problems also they can give you. Clear? This I have taught you, all of you know, no? If I am selecting only medium-sized individuals, then I am going to get a narrow graph in the middle. What is this graph called as? Fast tell me, what is this graph called? Fast, 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 fast. Okay, we have 7 minutes. In 7 minutes, I don't know what we will do. Answer, students. Yes, what will I do? If I select out of tall, short and medium sized people, if I select only medium sized people, I am going to get a graph which is narrower at the center. What is this graph called as? Very good, stabilizing graph. I've made you solve this question many times, 2019 question. Now if I select any one extremity, neither tall or short people, then I'm going to get what graph? I'm going to get a directional graph. Direction, okay, because I'm taking one of the extremities. If I'm going to select both of them, I'm going to get disruptive graphs which are going to be 2 peaks. Okay, 2 peaks. Okay, clear to all of you? Dinosaur chart, you don't have to waste your time, just go through it last minute once. Okay, one question has come in many years. Okay, one question has come in many years. And students, this box I have added for all of you. Please study this box. What they will ask you, they'll ask you brain capacity. 650 to 800 cc Homo habilis, 900 cc Homo erectus, 1400 cc Neanderthal man, and Homo sapiens starts with 1300. Don't think that, okay, Neanderthal man came above me, so above Homo sapiens, so their brain capacity. These people came after us, but still they have more brain capacity than us. Okay. So don't think that according to, you know, the maturation, brain capacity will increase. Nothing like that. Okay. Otherwise, we'll all be Isaac Newton. No, we didn't become anything. Clear? And this also they'll ask you. Where is it? Yeah. Buried, dead and used to hide body. One more question. This one. This also has come as MCQ. Okay. MCQ question. Java, what bones they found in 1981? It was Homo erectus. Okay. Homo erectus. How will you remember? Drahen. Okay, Drahen. Just take the first letter of all of it, you will get a trick. D for Dryopithecus, R for Ramapithecus, A for Australopithecus, H for Homo habilis, E for Erectus, N for Neanderthal. Okay? Yes. Clear to all of you? Yes. Don't be extra smart calculating. Okay, Homo sapiens came after Neanderthal, so their brain capacity should be more. They will give you purposefully to confuse 1400 and 1300. All the brilliant people in the world will go for this. Okay, you will have less brain capacity than them if you do this. Clear? Yes or no? Okay, evolution done. Okay, I don't think reproductive health I can do justice, but don't worry, notes are already here. Okay, all you have to study is here. Okay, first of all about the RCH program. Okay, reproductive and child healthcare program. This you have to remember. 1951, you have to remember about family planning. Okay, then I'll just tell you what is important here. Students, this one, that how was the reason for population explosion? Because of good healthcare facilities. This is very important. Maternal mortality rate and infant mortality rate rapid decline. What is maternal mortality rate? The number of mothers, right? Mothers who were, you know, like usually what happened, the midwives used to take the delivery. Because of it, the mother, anything, BP goes down, blood goes down, something like that. Because of that, what could have happened? What could have happened? They will die, okay? They would have died. But because of better hospital facilities, maternal and infant mortality rate decreased. So this is important for all of you. Then students, IUDs, types of IUDs, very easy, just know the names. Non-mediated IUDs, okay, they retard the sperm motility. Again, sperm motility will be retarded. Lippi's loop is the answer. Copper releasing IUD, copper T, copper 7 multiload 375, suppress motility again, and also fertilizing capacity, match the following income. Okay, whatever I am underlining is very, very important. Okay, yes. When are you going to see me again? Monday. Okay, no, Saturday. Hormone releasing IUDs, they make the uterus unsuitable for implantation and the cervix hostile to the sperm, LNG20 and progesterone. Okay, this, all the words which I have underlined is important. And students, assisted reproductive technology, blindly you have to know. Blindly you have to know, that is in vitro fertilization, test tube baby program, okay, embryo transfer, two types are there. What is it? ZIFT and IUT. ZIFT is within 8 blastomere stage, IUT is more than 8 blastomere stage. GIFT is gamete intrafallopian transfer. Intracytoplasmic sperm injection means you're taking the sperm and injecting directly into the egg. Okay, yes. Sunday there is no class. Why you want us to work on Sunday also, da? Who is that fellow? Harshine, you will not shine anymore, okay? Now, artificial insemination. Again, students, the semen is collected from the husband or the donor. This is when the husbands have low sperm count, okay? Intrauterine insemination. So, please study this. I have put all the notes just for you. So, today we have completed all the chapters, okay? My God, I feel like I have finished World War 4, okay? World War 4 is over with you people, because molecular, just imagine students, I need hats off today. Why? Sexual reproduction in flowering plants, 5 hours chapter. Molecular basis of inheritance, 7 hours chapter. Reproductive health, okay, leave it. Evolution, 6 hours chapter. Some teachers have taken it for 9 hours also, 6 hours chapter. Then biotechnology unit, both the units together, 10 hours chapter. I have done all of that in 5 hours. 5 hours, can you believe? With 30 minutes of break. Shreya's break also I gave, my break also I gave. Okay. So today I want all of you to comment down that I am the real warrior. Okay. Thank you so much, students. Don't worry, you will get the notes today. Okay. You will get the notes today in the description box as well as on my Telegram channel. But you please study from my main notes. Okay. These are all taken from my main notes plus some subscribed notes, I'm telling. Sorry. Some condensed notes. Okay. Those who are planning to write NEET and JEE for the next year, please take up 40% scholarship on all your VLC centers. Okay. Up to batches starting from 25th April. So please run and join. These are the cities where your VLC centers are there. Okay. Yes. Gopika ma'am, yes, okay. And I was awake for you people also in Basava sir's class, okay. So that's what. Bye students, bye bye. Okay, I'll be there in Diksha ma'am's class. I will request her for 10 minutes break. Okay, if she doesn't give, I will call her and ask for break. Okay, we will see, students. We will beg, ma'am. Okay, we both will beg. Bye bye. See you. Don't say here. Tell it in comments. Don't forget. Okay, I want to see all of your comments. Thank you. Bye bye. Take care. See you all on Saturday. We are going to start our first mock paper. Okay.